Hello. Hello. Check. Hello. 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 Check.
बोला सर बोला.
Hello. Hello. Check. Hello. Hello. Check. Check. Hello. Check. Hello. 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 Check. Hello. Hello. Check.
बोला.
Hello. Hello. Check. Hello. Hello. Check. अकबर तू बोल. Hello.
Hi Neil, this is Vivek. I'm Hi Neil, are you there? Hello. Okay, Neil, can you just switch on your video, please? Hi, Neil, can you just switch on your video for me? Hello. Hello. Yeah. Very good morning, one and all present here, all the dignitaries. I welcome you all on this Professor K.V. Nori Memorial Workshop. So please occupy your seats so that we will start within 2-3 minutes.
Hello. 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 Good morning. A very good morning and a warm welcome to all the dignitaries, including Dr. Preeta Bedekar, the HOD of Computer Science Department, STP, Professor Sahasra Buddhe, all the speakers, the participants who are present in person, and the participants who are present online. We are all gathered here for Professor Keshav Vittal Nori Memorial Workshop. So, just like me, to whom Professor Nori was a guide during my MTech thesis, and he has guided so many students, not just for their masters, but also for their PhDs. After joining TRDDC, he became, of course, a mentor. More than a mentor, he also became a friend to many of us. Of course, his thoughts about various aspects, not just programming or not just software, they were of the level of the philosopher. So indeed, we learned a lot. So programming and simplifying programming were definitely at the core of his heart. You know, that those are the areas that he really loved so much. He tried to apply these concepts in various areas, but I think he started off with compilers, uh, language translators, and many of the language processing tools that we built at Data Research Development and Design Center. His idea was not just to kind of build the compilers, but come up with the technologies and tools to build such softwares. In fact, so much so that he wanted to build or construct tools to construct tools. And this notion of meta tools is something that he imbibed in all of us in TCS research, also to the community outside. Now, going beyond programming, at least to my knowledge, he was very keen on business processes and their modeling. And some of these aspects, of course, carried on into the work that we do at TCS Research. Later on, he also worked on systems programming. And you would hear some of these things in today's subsequent activities and subsequent events. Now, while doing this work was one of his core strengths, he was very keen on giving all of this back to the community. Right? I mean, he helped us build bridges with academia. He encouraged many of us to teach at College of Engineering, Pune, at SPPU as well. And, and sort of this became the seed. So when Vivek Buzurg approached us from ACM Pune chapter, and he suggested that we should do a memorial workshop, all of us were, kind of a complete yes right away. So that was sort of the seed for the workshop that we are seeing today. So this workshop is trying to figure out, at least in some of the areas that Professor Nuri's professed all through his life, as to where these areas are today, what is the state of the art, and that's sort of the germ of the workshop that we're going to see today. So, with this few words, I welcome you all once again, and I invite Ms. Gitanjali Kare to take on.
Thank you very much, Mike, for introducing. Yeah, big round of applause for warm beginning of the workshop. Thank you very much. Now I request Dr. Smita Bedekar ma'am, who is the HOD Computer Science Department SPPU and kind host for the today's August gathering.
Good morning. It is my pleasure to welcome you all for this occasion, Professor Noori Memorial Workshop. As all of you are aware, Department of Computer Science was one of the pioneering departments in computer education, and under the able leadership of Professor Sahasrabuddhe, this department had done lots of things first in the country. Professor Nori was integral part of this department and in the team of Professor Suhasrabudhe, and he has guided many of the students from computer science. So it is a very apt occasion to have this event here, and we were much happy to collaborate with SCM and TCS for this event. I welcome Professor Sahasrabudhe, Ravindra Mehta of TCS Research and Hemant Pandey of ACM for this event. We have a gathering of eminent speakers who will be doing their job here. So I think I'll hand over now to Gitanjali Kai, and already this event has started a bit late. So we will continue with the talks.
On behalf of ACM, we thank. I think now I invite Dr. R.D. sir to introduce the next speaker.
I invite R. Venkatesh from TCS Research. So, scientist in Data Research Development and Design Center. Many of you know him. He really doesn't need much of an introduction. But he has also been one of the pioneers in the various areas that we talked about. And in fact, he's going to talk more about Nori and
Hey guys, be quiet, okay?
Yeah, so this is Welcome with Star, and as an initiative of ACM, so we are supporting from Green Earth. So we will be planting one tree with the name of each speaker. Slide is displayed. Speaker will get the dashboard with his name, and he can track the growth of the tree.
Hi, thank you everybody. Thanks to ACM for giving me this opportunity to be at this event. And thanks to ACM also for organizing pushing this. So, Professor Nori had the good fortune of both being a student as well as within my career. It's a great pleasure and a great learning experience for me. Many parts of me have been shaped by working with many philosophers. I try to put this even now. Have been shaped by, and I try to just two of the key philosophies that he really pushed. Well, one is a search for structure, be it in complex systems as well as in any complex. That's one part that he did. Whatever he saw, he structure that's part of it. That's how we can do modern that. I already mentioned modern. That's been what we have been following, trying to follow. And the second one is very early on he pushed this concept of a factory, where we try to automate as much of so these two key ideas that he professed has influenced me and many others at Idiomatic. We still try to practice it in one way or the other. And there are still tools that we can find out. So if you look at most of the work, it's always about some software engineering or creating models and meta model anything. More recently, there was a team that so this is a so it was more pushing philosophies rather than just being very technical or implementation. We used to just grab a bunch of us at work and say, come on, let's come to it. It could be things like, what is the difference between computer science and engineering? So it's this way of thinking, the level which is philosophy rather than implementation, something that is good, had a great influence. He wanted us to look for beauty in structure, whatever it is. One good example of it is when we work hard at pushing, trying to make us understand object list model of classes and objects. And if you have not seen it, you all must go and read up about the OPJ list models of classes and objects. It's and the way it very neatly bootstraps objects and classes, then everything starts from, and which is what is there in Python today. If you look at Python today, everything is an object, a class itself is an object, and so on. So that's which was there in OBJ Village, and we have implemented that in the ADEX, the meta modeling tool that we have. So that's one example of where he was just pushing beauty in structures, and that's something that we have tried to implement. So keeping this in mind, when we had started having discussions on what we should do in this memorial, and so we said that whatever we do, it has to highlight these aspects, the automation part of it, and also trying to looking for beauty in structures. And that's why we have put together a highly technical program, which in some sense presents the modern day automation of programming, the hardest of human tasks. So there are two talks here which will present automation of programming itself, and program synthesis by Neil and Saurabh Bansal. Both are very interesting talks, very highly technical, and automating the hardest of human activity. So, and Neil, one good thing about it is he was also in some sense my first boss at the RABC. So when I joined the RABC, he's the one who was tracking this on my first project, which was a C++ translator or interpreter, and Professor Srivijay also was instrumental in making that happen. So I'm very happy to be preceding Neil in this particular. So the objective of this workshop for me is twofold. There are very few platforms in Pune for highly technical people, professionals, students to exchange thoughts and ideas, technical thoughts and ideas. And we are hoping that this will be a precursor to many such events organized by ACM or individual other organizations, whatever it is. So this is just intended to be a precursor to many such events, and we thought a memorial in the name of Professor Nori would be an ideal way to get this going. So that's one of the objectives of this workshop. And the second one is that students and professionals in this country, not just in Pune, have very less exposure to the state of the art. To get exposed to state of the art, one needs to attend conferences, which are international conferences, which are both expensive and inconvenient for the computing professionals in India to access. And one of the primary roles of ACM is to make this happen. Get the state of the art and make it available, make it presented to all ACM members. That's one of the key roles of ACM. And we hope that this will be one of many workshops or conferences that are started by ACM Pune chapter and ACM India in general. ACM India already organizes a few conferences, ISEC being an example. But we hope that that number increases. If India has to progress in the field of computation, conferences play a very key role because they provide the platform where the state of the art is discussed and presented, and it's a seed for all future ideas, be it startups or whatever it is. So conferences play a very important role, and it is important that in India, so we start having many very high quality conferences. Today that is not the case, and this hopefully the two talks here are of Abhijit. So we hope this just gives all the glimpse of what this workshops on events that Pune and AC Media organizes. So coming to the community. And with that, I would like to end and again thanks to ACM for organizing this. A warm welcome to all participants and hope you all enjoy the event. Thank you.
Thanks, Ankit. So next speaker is actually will be live from US, and so let me introduce Neil. Neil actually, myself and Neil in fact also have interacted earlier because I was there in TRDDC for some work that I used to do. Neil Sudarshan is a Vice President of AI and Engineering in the Cloud and AI Division of Microsoft. Neil manages a team of AI researchers and engineers focusing on the areas of AI and data for cloud developer productivity and program synthesis. Prior to joining Microsoft, Neil headed the eBay Research and Data Labs, where he brought in innovations in machine learning at scale to create innovative products in search, recommender systems, trust and safety systems. He created eBay's economics, HCI and computer vision groups to bring in new dimensions of expertise into product and business decisions. Prior to that, he co-founded and successfully ran a network of CRM company, and prior to that was a research manager at IBM Almaden Research Center. So welcome Neil, and let's listen to him for a great talk on. So Neil, hand over.
Can you hear me, Vivek?
Yes, please go ahead.
Okay. So I hear a lot of static where, yeah, that's better. Now can people hear me? So they've disabled screen sharing, so I can't project my slides. Can you enable screen sharing for me?
It's done, sir. Please check.
Okay, thank you. So can you see my screen? So there is a lot of static coming back. So there's a lot of static coming back. Can you turn off? I think some speaker is on. Yeah, that's better. Now, can you hear me? Can you hear me now? Okay, thank you. So, yeah, thank you so much. I think I'll do without that static. So thanks again to Vivek and Venkatesh and Vinay and Ravi, everyone, for the invitation. I have to start with an apology. I would have loved to be there physically. You know, one thing is to give a talk, but another is to interact with people, have chai together, and talk about, you know, the past and what's happening in the future, and that's a big part of the engagement I'm going to miss. But you know, there'll be future opportunities, hopefully, to come and visit you and have more conversations. I also have to start with a confession that computer science was not my subject that I ever wanted to do. So for those of students who are kind of thinking about computer science, I kind of walked into it. It was almost like an arranged marriage where you had to do it because it was the right thing to do. And I didn't, while I enjoyed programming, I didn't really fall in love with the subject until I met these two people. And I have to dedicate this talk and owe a lot to both Professor Damdere from IIT Bombay, who was my advisor, and then Professor Nori, who literally, I think, like Venkatesh said, molded us into thinking the way we got to think, the way we got to shape literally the rest of our careers. And if you think about the personalities of Professor Damdere, for those of you who know him, and Professor Nori, for those of you, everyone knows him as well, it's like they were very different personalities. Professor Damdere was super organized. He had a plan. He worked in structures, and he taught the discipline of how to do well. And Professor Nori worked through inspiration. So Professor Damdere was an architect. Professor Nori was an artist. And I think being exposed to and being trained under both of them was a huge privilege. I think they've done tremendous things in their lives to, and passed it on to us and for us to carry it forward. So with that, I'm going to talk about this topic that had, basically, I'm going to use program synthesis in a very loose language. Everything about generating program, completing program, translating programs, etc. But one main theme, especially if you ask me what is common today, is all about productivity through software. So that's going to be the running theme of it. And frankly, Professor Nori was the first one who actually talked about productivity, and I'll kind of explain that to you. So very simple task. I mean, if anybody who ever worked at TCS maybe 30, 40 years ago, would know what is a typical task. There is some source. The source could be English text, the source could be data, the source could be a program. And the target could be, again, a text, data, or program. And the job was to translate one to the other. So you have to understand one, then you have to generate, then you have to translate. So this is kind of the three sets of tasks. And I break it down this way. I want to take the same theme to what we do today. So typically, if you go to a TCS office in Bombay, there is somebody sitting in front of a computer and translating one version of COBOL into another version of COBOL, and they have a bunch of, cheat sheets that they use to do that. And but then what about if you have a lot of programs from one language to translate into another language? What do you do about that? Well, simply this is what they did. They hired a lot of programmers to translate from one language to another, right? So, companies like TCS, there are many other companies, made a lot of money translating one version of a language or one language to another language. Now, Professor Nori, I think, came with a very, very different way of thinking. I think Venkatesh kind of introduced that pretty well in the beginning, but I'm going to repeat that now. Now, I said, why would you do that, right? So, of course, in computer science, we know there is something called, code generators. So you can write a program that takes programs in one language and translates to programs in another language. That's kind of the obvious thing to do if you're a computer science student. But what if you have lots of programming languages, and there are many source programs in each of these programming languages, M programming languages and N target languages? What do you do? Well, theoretically, you're supposed to write, M times N programs. So this was kind of the topic of my first dissertation when I got introduced to Professor Damdere. Well, you don't want to write M times N programs. You really want to translate that to M plus N programs. So you really want to translate them into some kind of a common intermediate language, and then from that intermediate language to the target language. So it's really M times N becomes M plus N. But, if you ever talk to Nori Saab or Professor Nori, he would say, well, why even write programs? You should not be writing programs. You should be generating programs. So the whole idea is you don't want to write programs, but you want to write programs that generate other programs. In fact, you shouldn't even be writing those program generators. You should be generating those program generators. The whole idea was never, ever to write programs, but just write specifications. And that's kind of how we were trained. In fact, my own exposure to this, practice was really within 2 months of me joining Pune, where TCS came and they kind of said, oh, we have got this massive project to translate HP's modular like Pascal language to C. And this is a 100 man-year project, which means we're going to hire a lot of programmers who will translate program in one language to Unix and C. And Nori was the CTO at that time. He wanted to sign off, and he said, absolutely not. We're not going to do this. And they pulled me in, and he said, well, here's a guy who can do it in 4 weeks. He's going to write this program generator that's going to automatically translate all the programs in Modcal into C. And guess what? He's not even going to write a program generator. He's going to generate a program generator. And then he looked at me and said, will you do it? And I was pretty scared. I'd barely been there for 2 months. And I said, yes, sir. And of course, I had the C specification book from Guy Steele, and I had a language manual. And then we didn't do it in 4 weeks, but we managed to do it in a few weeks, and it all worked. So this was the magic that he brought into work, where he thought about productivity way before anybody else thought about productivity. Right? He thought about automation way before anybody, and in a beautiful way. Right? He thought programs were trees, and any kind of program translator is a tree transformation, and you can write specifications which will do all the transformation for you. And that kind of stuck in my mind, and literally kind of I carried through in my career. And so a lot of the conversations I'm going to have today is kind of how I took it to the next step and the next step and the next step, even though I didn't really work in programming languages through my entire career. And hopefully you can see the connection. So literally a lot of the stuff that we did early on was using programming language grammars as foundation. And it allowed us to do, because we had the schemas, we could do a lot of these things automatically. They were rigid because they had to be deterministic. And even in the absence of grammar, we could take some examples and we can kind of create grammars. And then, of course, they didn't really work for big languages. It worked for smaller languages like regular expressions. But one thing we didn't notice, so for example, the project at HP where I said, he literally tore up the contract and actually used to have he was a great calligrapher, so he used to have a set of calligraphy pens, and he wrote the contract with HP in his beautiful handwriting. So it was a handwritten contract from TCS to HP, which basically said, we're going to charge you $80,000 to write this software, and we're going to charge you 25 cents per line of code translated. It was 3 or 4 of us working on it. We worked for a few months, and the company made a lot of money. So this was, we are talking about almost 35 years ago, how he thought so well ahead of time how we can automate things. And he was very bold in making these decisions and also challenging us through encouragement. So you can do it, and go do it. And we kind of just did it, right or wrong, and we figured it out. But again, this was that generation, and I went to the US. I got a PhD in computer science. I was writing compilers for, writing parallel compilers. And of course, this was all going to change because what really happened at that time, the internet happened. Now, with the internet, what happened was, you got a lot of data. There's a lot of markup data, image data, textual data, et cetera, et cetera. And one thing we lost in the process, even though Tim Berners-Lee talked about semantic web, et cetera, there was no grammar. We lost the schema of anything, right? So you hack up an HTML page, you put it up there. As long as it shows up in the browser, it's fine. It's working language, right? In fact, even SQL gave to NoSQL databases, right? So, but one thing we did have, we had a lot of data. So that's kind of how web mining was born. And I was working on shared memory compilers, and this was an IBM research, and they said, hey, would you like to write a search engine? I had no knowledge of search engine. I had never done mining classes or anything before. All I had this set of tools I picked up from Pune and my dissertation that I went there to do. But one interesting that happened with the internet was, the language, I don't know how many of you remember, this language called XML was born. And XML was kind of a meta markup language, which means you can write other languages, describe other languages, but these are mostly like markup languages in a structured language like XML. So this gave me a language to crawl the web, to mine data, put it in a structured form, create indices, and create a search engine. We could use XML as a transformation language. You could use XML as an intermediate language. We could use it as a specification language. And even when we want to kind of serialize XML, we could create compression and stuff like that. So ton of research, ton of product that were created, and ton of research that went along with it. And it was a lot of good time. It was also almost brought back memories of my time at Pune of working, generating programs from, again, specifications, or in this case happens to be markup language. Now, another thing happened with the web, as I said, there was a lot of data. So this was kind of the second generation, at least of my career, where I said we use data as foundation, and we can kind of see how we can make things, our software activity more productive, or how do we make people more productive. Now, there was this wonderful paper written by Peter Nori and Alan Halloway, for all the folks from Google, basically said when all we need is data, and we can make simple models work better with more data. Add more data, you really don't need more than, say, something like a Bayesian probability to discover interesting things, to make recommendations, etc. So what I learned, or what we learned during this period, was kind of how to torture this data, like Ronald Kosu said. You can, if you have large enough data, you can torture it enough, and it'll confess to anything. You can learn things from it. And during this period, it was fun time. I was at eBay. There was tons and tons of data. There was behavioral data. There was transactional data. There was search data, etc. Worked on a lot of interesting topics, And one of the first things I worked on was, again, search and recommendation systems here. And these were very simple algorithmic systems, right? It was mostly like nearest neighbor, Bayesian systems, k-means clustering kind of stuff. And we could deploy products at scale, which really, really worked well. And I even kind of had the fortune of working with, I set up a computer vision team. And I'm not a computer vision person. I have no idea. But at least by the time I'd learned how to work with data. Now, we had to build vision search. And the interesting thing is, I had a team of computer vision researchers who kind of came up with these algorithms, but they were not used to looking at data. So for example, one of the things we built was visual search, right? So if I take a picture of somebody's clothing, can I recommend clothing similar to that? So for example, if you are taking women's clothing, what kind of style dress is it? Is it a sleeveless dress? Is it a full dress? Does it a collared dress or collarless dress, etc.? What colors does it have? What patterns does it have? What texture does it have, etc.? Now, identifying all of this at that time, computer vision, this was, we're talking about 2010, 11, deep learning had really not taken off. And most of the vision work was being done with small amount of data. So, again, coming from this way of training, I kind of said, well, why don't we look at the data and see what does the data tell you? So we mined all of the data. Being at eBay, you had access to a ton of vision image data. And we looked at all the women's dresses. The nice thing about that was about 70% of the dresses were black. So, okay, so you're at least going to be right 7 out of 10 times if you recommend a black dress, loosely speaking. Now we can superimpose this images one on top of the other, and you can figure out what different shapes come up. So we could identify like sleeveless dresses and full sleeve dresses and so on. And another thing we discovered was that just by projecting along the RGB dimension, adding another dimension to RGB, we could also determine what colors they were. And another thing we discovered from the data was that certain color combinations automatically gave to certain patterns. So just by beating up the data enough, we could actually do texture search and image search and pattern search without actually identifying any of those things. That was kind of the magic of data. Even the way economics was done changed. So I had the wonderful opportunity of working with some very good economists from Stanford. And till that time, what economists used to do was they would take they would run a lab experiment. So for example, if I want to know certain consumer behavior, do people like to pay taxes on things or not? They would call 20, 50 graduate students, they will make them sell something, and then they will identify the properties and literally have 50 rows of data. They will run OLS on it, and they'll come up with some conclusion. And what we learned was we got these tons of data of user behavior. Why don't we automatically mine what economic incentives people have when they decide to whether sell it with free shipping or with a shipping cost, or whether to list an item as an auction or as a fixed price, or whether to ship internationally or not. So I used to call this economist in a box. So we could mine this data and create an index and answer all kinds of economic questions. In fact, we would take every economics paper and say, can we automatically answer the question answered in this paper? And there is a pattern to the way economics research is done. Those of you who are familiar with it, typically economists want to know what is the consumer welfare of one change of one variable in this thing. If we increase taxes, or if we change the price, or if we make something free, or if we offer a certain incentive. And there are certain standard patterns they look for. They look for elasticity. What does 1% change in something do to the user's behavior? And what does it do to the consumer welfare? So because we had this template or these patterns, we could mine that automatically from the data. And we could answer many questions. And especially at that time, for example, internet tax was one of those things, huge thing talked about. People shopped on the internet because they didn't want to pay taxes. So we wanted to know what will adding internet tax to items that are being sold over the web cost to consumer behavior, right? And we could find in data, for example, one of the things that happened at that time was if you ship within the same state, you didn't pay a tax. If you ship to the next state, you have to pay a tax. So you can take like a state like California to California, you don't pay a tax, but the next state is Nevada. If you ship to Nevada, you pay tax. So you kind of pair them up and you kind of say, well, the shipping time is about the same. So people kind of decide whether they want to buy from Nevada or from California, because in one case you pay a tax, in another you don't. So wonderful things we could do with data, and we could do things that you couldn't do before. So literally data became the backbone of everything that we did. And again, during this time, there was a third wave that was happening. The way software was being developed was changing, right? So we saw more and more open source software. Now, platforms like GitHub, platforms like Stack Overflow, like Reddit, etc., showed up, where it was people used to make money in software. You build software and then you sell it, but software was not being offered for free. They were being hosted publicly. They were being commented on publicly. It was being developed by the community, checked in, corrected, bugs fixed, etc., etc. All started with Linux, but now if you look at there are 50+ million developers who have their software on GitHub and related platforms. They talk about them. Hey, I want to fix this problem. How do we solve this? Here's a snippet of code that worked before. It doesn't work anymore. How has the API changed? So there's a ton of data to be mined. There's a ton of data that is out there that you can look at. And we have trained ourselves to work with data. So the next question is, what can we do with this kind of data that's out there? Now, you can also see the theme changing. I'm coming back to where I was before, kind of coming back to the system of programming languages and systems and software, etc. Right? So the way because I had done work on the internet space, I kind of looked at data and says, oh, code can be looked at data. Now, years ago, when we did this translator back at TRDDC, while we translated millions of lines of code, we didn't even have the thinking, or we didn't have the tools to kind of look at these millions of code, index them, and do something with them. But suddenly, these millions of lines of code look like data to us because we were trained in using data. So that was one thing. That was a big thing. The flip side of that is we can also look at data as code. So the way modern software is developed, right? So it is kind of almost always AI is a part of code development. So in some sense, certain logic is not hard-coded into the system, but it is driven by data. So basically, those of you who know about table-driven code generations, there's a table and there's a driver. Here, the table is replaced with data, and there's a driver to that data, and that gets plugged into the software. I'm not going to talk much about that. I'm going to mostly talk about code as data, right? And at the same time, artificial intelligence was also entering its third phase. If anybody who's done AI in the 80s, we knew about rule-based system, expert systems, et cetera, et cetera. And with big data in 2000 and 2010, we had the probabilistic systems. And then we had the big data systems where we had feature-based machine learning and statistical techniques that are applied to this big data. And we built systems on that. And just about this time, deep learning was taking off. The first work was, I think the Microsoft researchers showed that deep learning really works in their speech synthesis system. Google adopted it. A bunch of folks from University of Toronto kind of demonstrated that deep neural networks actually are practical, right? And then if you fast forward to today, this whole technology of transformers, which I'm going to talk about today. So there's a huge evolution that has happened in artificial intelligence, this is literally the third or the fourth iteration of getting AI right. Now, what has happened is that we got data and we asked the question, so what do we do with this data and how can machine learning or how can AI help? Can we build tools that will address the need for this community? So my target as working at Microsoft, which is a software company, it's like we got 20+ million developers. Can we make them more productive? It's kind of going back to day one of how do we make developers more productive? But a very different setting, very different platform, very different way of answering the question, but coming back to the same thing, how do we make people more productive, right? Now, when we have a large number of sample of code, can we teach the machine enough to either do the work that a developer does or assist the developer in doing these tasks with reasonable accuracy? So how can we make the developer more productive? And again, think about it. The people who write software are quite skeptical about this. Very much like when we did automatic program generation, companies, tools, you can't automatically generate tools. You need people to do it. That was kind of the thinking then, and this is the thinking now. So AI is not very easy to just ingest into a software system. You can do research on it, but when you're in a product division, it's not very, very easy to do. So that was kind of where I was. And the other thing was, can we teach the machine once and repeatedly use it for many tasks? Because machine learning, I'll show you, is kind of expensive. So how do we do this over and over again? But the good thing is that because there is a developer in the middle, you don't have to be perfect, right? So which means you can do something reasonably well and leave it to the developer to repair it, fix it, or provide tools to repair or fix it. And literally the goal is, how do we automate the mundane tasks? And when you have complex tasks, how do you assist with the tasks? So those were kind of the two big goals of using AI into this whole software development process. So now if you look at software development life cycle, there is a whole bunch of things you do, right? You go to an editor, you write code, then you compile the code, you build the code, then you check it in, then you run it, you debug it, then you deploy it, then issues get reported. You have to write documentation. There's code reviews that happen. You have to write tests, and with CI/CD, you have to do continuous deployment. Then you have to deploy it to production. You have to monitor it in production. You have to scale it, and so on. So this is the entire life cycle of software. Now, this is kind of also the footprint of my division and my group. So any automation or all automation we can do in this area would be wonderful. So that was kind of the big blank canvas I was given. Can we do something, right? But again, to be modest, we really, really wanted to start small. So in fact, so small that you might say, is it even AI? So if you have used modern IDEs for writing code, right? Typically what happens, if you look at today's software, about 30% of the code that you write is API calls. Right. So, for example, here is on the left-hand side is some Python code, and it's doing some machine learning work. It uses TensorFlow, and if you look at line 13 on the left-hand side, it's basically saying optimizer is I want to train and what kind of optimizer I want to use. So if you use any of the IDEs that's available today, you get a long list of API calls you make at that point. You say tf.train. And then you get a list of function calls. And those are typically listed alphabetically, right? So we asked the question, can we make it better, right? Almost nobody questioned this before. People have been using this forever, but this was something that came up in one of the scientists' minds. It's like, oh, can we make this better? And what would be the easiest way to do it? So all it is basically a ranked list of API suggestions. And if you want to write kind of a mathematical formula for it, this kind of here's a code snippet, and the code snippet is in some vocabulary. I'm using these terms only to kind of take you to the next step. And then I want to recommend an M star, or I want to figure out an M star, which is basically an argmax or probability of finding that M, which belongs to a subset of this vocabulary, given the code snippet or given the code context. So what is that going to be? And can I make it better than a traditional alphabetical sort? And I have to tell you, it was very difficult to even convince the development team to ship something like this, because the moment they hear AI, they kind of freeze saying, well, it doesn't work. So Of course, the zeroth model is basically saying, well, why don't we promote things that are most frequently used and move them to the top? And so that gave us our baseline model. So it's like, okay, anything that beats that baseline model is a decent enough model. Now, if you're kind of ever done program analysis or ever written a compiler, you kind of know that the program flows from top to bottom. Things are defined, then use. A call that is made later depends on a call that is made earlier. So for example, if you have a file open call, that will be followed by a file read or write call, depending upon the file. And then you will have a file close call, right? So there's a dependency in the if you were to turn the program into a graph. So what is the best way to kind of represent this? Again, we don't have the tools to do an entire program graph. We can at most mine it and create an index out of it, because there is no room, there is no space, there is no memory inside an editor to do any of this stuff. So you kind of say, well, I'm going to chain these calls. A call to, let's say, close was preceded by a call to open, and the call to close was, call to close was preceded by a call to write, and call to write was preceded by a call to open, and the call to write was inside some kind of a loop. So just having some minimal structure of this, you can mine a lot of this code that I talked about before, and we can create an index, and you can say, okay, now that you open the file, you're inside a for loop, which means you're going to read a character at a time. You are going to probably do a read call or a write call, depending upon the type of the file. So this is a typical, I mean, it is a Markov chain, works really well. And now, you can mine that, you can kind of try out how long should your chain be, how far back do you want to go in your flow for it to be really useful, and how correct you have to be for a programmer to accept this kind of a recommendation. And, so this worked. We deployed this worked, and actually it worked. If you look at the offline metric and the online metric, and then you do the user study, typically we do three things when you build a machine learning model. You evaluate it offline, you get some metrics like accuracy, precision, recall, then you deploy it online. Almost always the online metrics are much worse than the offline metric. Then you go to talk to the customers and you ask them how much do you like it. Customers usually hate it. This was probably in my entire career the first time when we actually deployed a model like this, and customers were like, where were you all this while? This made my life so easy, made me more productive. And what I thought was a very small thing we did turned out to be a very useful thing. Also gave us encouragement to do more. I mean, this was about 5 years ago. Almost nobody was working with code and AI at that point. And so this gave us encouragement to do more things. But one of the downsides of this was that the model was getting bigger and bigger, because as new kinds of call, new kinds of packages, new kinds of API come in, we go to index all of that stuff. It grows. If you want to improve the accuracy, the model grows. And the restriction on us was that the model can't be more than 30 megabytes. It can't, the response time has to be less than 10 milliseconds. So there's a whole bunch of engineering constraints that get put on top of it. I can write a nice paper on it, but at the same time, I can't deploy it to production, which makes it fairly useless. So what is a natural next thing to do? I mean, deep learning was getting popular, and in this kind of a sequence-to-sequence situation, you got a program that's flowing left to right, and you want to predict the next keyword, or you want to predict the next call. The best thing to do is something that fits a sequence-to-sequence model. So, you can start with an RNN, but RNNs don't have any memory, because basically all they remember is the previous state. And if you try to overload the memory of the previous state with everything that it has seen before, basically it's going to have accumulate a large error gradients, and it's going to make the neural network unstable. So then we said, well, maybe we can use LSTM. So what are LSTMs? LSTMs are basically long short-term memory systems, which is an RNN, special kind of RNN, where each of the cells takes input, whatever output by the previous iteration or previous transition of the cell, and the current input, and also kind of the cell state of the previous. So it can, and the beautiful thing about LSTM is that you can make it remember things from before, and you can make it forget things from before. So instead of carrying everything or trying to compress everything into some small number, which causes a gradient explosion, you can kind of make it remember and forget things. So we use a sigmoid function, which maps to a 0 or a 1 to basically either to forget or remember. And then you use a tangent function to avoid the gradient explosion. So these kinds of models, sequence-to-sequence models, or encoder-decoder network models are good for kind of doing time series kind of evaluations, where you've got a time series data, you got to remember some seasonality, you want to forget the fact that it is growing at a certain pace, et cetera, et cetera. It is very natural for doing anything going from left to right. So remember that we are looking at programs as something that's written top to bottom. So if there is any purist who says programs should not be written that way, I totally agree with you. Programs are not sequences of words, but that's the best we could do at this point. So, you know, if you want to double click on that, what it's really doing, you take basically a program's parse tree or an AST or abstract syntax tree and convert it into some kind of an LSTM consumable form. So what you do is you take the nodes and the tokens and turn them into some numeric vectors. And in order to represent them in some low dimensions, you use something like a word to vec, which is basically some kind of a neighborhood matrix, which says, I am a word here or I'm a token here, and I'm expressed in terms of whoever is my neighbor, whoever I'm around, right? So the equation we had before, which was, you know, predict M star as R max of the probability of M given C, where M is in the subset of the vocabulary, right? Now can be modeled nicely as a stackable LSTM or a stacked LSTM, where, you know, your X or your context is really this word embedding matrix. And, you know, and you can use a stack LSTM to take the current state and the previous state and predict the next state, right? So really what this thing is basically is softmax of WHT plus B, which is basically the output projection matrix and then the original bias that you might have. So I don't want to go into the details of this. You can go read the paper, but this was really the system that we built. Of course, the end goal, the success is not the paper. The success is it deployable? Is it actually, can we create a better model, make it more useful? So now instead of just predicting an API call, we could actually write complete lines of code automatically. Because remember, LSTMs have capability to do more things than, you know, what the earlier model did, right? So one of the challenges, one of the challenges with LSTM is that it won't work for very long inputs. So it cannot capture the essence of long input, even though we have this forget and remember thing in LSTM, you know, because what happens is all of these tokens, they get captured into these lengthy vectors and you don't know what to attend to, right? So basically, one of the challenges we found was that at any step T, you have to wait for all of the steps up to T-1 to complete. So when you have large corpus of data, this is extremely time consuming and very, very, very expensive, right? But right about this time, there was a paper written from Google. It is called, you know, attention is all you need. So this whole idea of self-attention, go read that paper. It's a wonderful paper that's written by Vaswani and folks from Google. And they basically said self-attention is all you need. So the whole idea of self-attention is basically you try and understand the importance of any token with respect to all of the other tokens that is around that. So now this becomes a highly parallelizable operation. So you don't really need recurrent units. All you need is weights and sums, which means you can parallelize it, which means that you can actually do a lot more than you could do before. You can have a lot more scope than you had before, right? So now when you have the encoder and decoder, the decoder has access to all the past states of the encoder. It can look into all of those states and pick the ones that, you know, the attention is required, right? So, and this allows the decoder to look at a particular state of the encoder, and this attention mechanism actually gave us something wonderful. Of course, this matters. Now we can look at a lot more data. We can train a lot bigger models, etc. We can do a lot more things. We can actually write lines of code. We can write entire sections of code automatically using this. So that was kind of the general idea of this. Now, how we got these models? So before I go to that, let me kind of give you maybe one slide on what are these transformers. Now, for those people who are used to compilers, you know, there is a source and there is a target, and there is a high dimensional representation. Think of there's a source language, target language, and intermediate representation. In transformers, we have a source code or source encoding. There's a high dimensional representation, and there's a target encoding. And the one that goes from the source to the high-dimensional representation is an encoder, and the one that goes from the high-dimensional representation to the target is a decoder. And typically, you have an encoder and decoder together, and that's called a sequence-to-sequence model. So something that's used in code translation. So if I have code in, say, C++, I want to translate to Java, then typically I would go, use a BART model, which is basically an encoder-decoder model. I could also have a decoder-only model, which is kind of called autoregressive. So it's kind of a generative model. So, if you used Outlook, or if you use Gmail, or if you use Word, these days, it will tell you what the next word is. So it's kind of knows the context of what you're doing. It tries to complete it for you. So it generates the next piece of code. These are called GPT models. And then there's also the encoder-only model, which is basically uses auto-encoding. It says how much of this code does it understand. So it's a language understanding. So if you're doing natural language, then the decoder is basically a natural language generation model, or an NLG model. And the encoder is basically an NLU model, or a language understanding model. It's a BERT model. I would also kind of put a caveat here to saying when these models get really, really big, when I say really big, it's tens of billions or even hundreds of billions of parameters, actually there isn't much difference between an encoder decoder. We are kind of talking about artificial general intelligence. I'll touch upon that in the following slides. So what do we have with all of this today? We have some, amazing amount of capabilities to process data, wonderful GPU hardware, great innovations happening in the hardware space, and great algorithms in the machine learning space or the deep learning space happening. All these have come together. So literally, we have the unreasonable effectiveness of data, hardware, and algorithms coming together. Now, what can we do? So if you think about where we started, a lot of this started with the NLP space, right? Elmo and BERT were kind of using the NLP state for natural language generation and natural language understanding. GPT-3 is about a year old. We have even much more larger and more efficient and complex models available today, which, we went from like a 100 million parameter model to 200 billion parameter model. And this was 2021. And if you ask me, this slide is kind of outdated. I deliberately did not change it because I'll have to talk about a lot more things and I won't have time to do that. All right. Now, because we have these large models, you can ask the question, this is like an oracle. This is like that Baba who's sitting under that tree who knows everything, right? You can go have a conversation with that Baba. In this case, happens to be GPT-3 or a large language model, and have a conversation in a way that you can adapt this to whatever you want to learn or whatever you want to do, whatever downstream task you want to do by having this conversation. So this is kind of like called prompt engineering or prompt hacking, which basically means I start a conversation with you and I give you maybe a couple of examples. I speak in English, then I give a translation in Japanese, then I say something in English, then I say something in Japanese, then I give you something in English, you start responding in Japanese. You as in this GPT-3 model. So you don't even have to train it to do anything. It knows everything. Or I can give you, a title of a book and say, what is the abstract of the book? I give you one title, I give you another, an abstract for it. I give you another title, I give you another abstract, and I give you the third title. It might spit out an abstract. Again, this was kind of the magic. If you go browse to the internet, or if you've read, either MIT Technology Review or Wired or any magazine, they talk about the magic of artificial intelligence, its capability to write poetry, its capability to, write haikus or give you a recipe or paint a picture or, write, write software for you and so on. Because these were demos, they were, obviously they would impress, but there are a lot of details we will talk about to make them work. Right. So now we are in this generation where model is the foundation, and this covers data, this covers hardware, and this covers all of these new wonderful models we have in our hand. Can we make developers more productive when we have something like this in our hand? So what do we have? What kind of opportunity do we have with this? These models have the ability to capture the universe of domain information. They can learn from different data modalities, which means I can give you data in English, I can give you data in Japanese, I can give you data in code, I can give you data in Java, I can give you data in C++ or Python, and it will absorb all of that stuff. It can encode this knowledge in very high dimensional form. And you can adapt this thing to the specific task you want it to do. For example, write code for me, or translate code for me, or fix bugs in my code, or automatically generate tests for me, etc. And we'll talk about that in the next few minutes we have. And we can also extend the knowledge through this conversation, and you can tune it further as well. And the wonderful thing in all of this is actually there is no grammar. So obviously that will come with some skepticism, right? How does it learn all of this stuff where it doesn't even understand the grammar of the system, right? So obviously, is it innovation or is it hype, right? Is it really learning or is it really memorizing? Because if it has a capacity to absorb so much of data, whether it is code or English or language or any images or whatever it is, let's say just focus on code for now. If it has seen all the programs that it's ever to see, has it seen everything? Is there no new program to write? Is it able to spit out? Is it just spitting out what it has seen before? Is it like a code parrot, or it's kind of, we call it stochastic parrot. Is it a stochastic parrot? But then the question is, does it even matter? If the n plus first piece of code you have to write is going to be like something like you have seen before, why do it all over again? Why not let it generate it? Is it intelligence? Is it knowledge? There's a lot of this conversation about, or does it even matter that it's intelligence or knowledge, right? And how much do you trust what it does, right? What is the cost of it being right versus wrong? So, or what are the benefit of it being right? Let's say it's right 99% of the time, but that 1% it is going to be wrong. What's the cost of it being wrong going to be, right? Now, and then there are these questions about, now, if I were to ship it, I've got to, make it into a product. The business will ask questions like, how big is 1 billion? Right? Is 1 billion big enough? And somebody else says, I've got a 10 billion parameter model. I've got a 100 billion parameter model. What are the training costs? How long does a machine need to train? What are the inference costs? What are the scaling costs? What are the deployment costs? Can I charge the customer for it, or will I have to give it away for free? And this is kind of literally the crux of, technology versus business versus, product kind of thinking that we have to go through. Now, you can kind of ask questions about the data as well as the model. So what have you fed it? You fed it everything that's available on the internet. Now, how much do you trust the stuff that's available on the internet, right? What kind of biases does it show? Have you honored the privacy? Have you honored the security? Have you honored the ownership? And then how transparent is it? So for example, it makes a recommendation. Is it able to explain why it made the recommendation? Now, if it's not able to explain it, is it just learning? Is it just parroting versus learning? Can I give it the task of extrapolating from what it has done? So these are many, many, many questions we have to answer, right? So again, as I think I've talked about this before, the constraints of actually shipping it on the cloud is very, very hard. So finally, if I'm going to sit on an editor, which is already taking up a lot of space, there's a user actually using the system, I cannot respond in 1 second. I cannot respond in half a second. I cannot respond in 100 milliseconds. My response has to be immediate, almost natural, because the user is at the most analytics phase of his or her mind when they're developing code. So when you make a wrong recommendation or when you slow them down, you're actually doing more damage than good. Now I'll talk about AI mixing with user interface in a little bit. So we got to talk about privacy and security. We'll talk about it in a little bit, right? So we deployed this model, and it's basically a generator or a GPT-based transformer model. And as I said, it had more capabilities than than we could do before. Before, because of Lstm, we could not carry on a lot of context around us, but now we can write whole lines of code, whole sections of code automatically just by looking at the current context in which the code is being developed. So just to give you an idea of the things that are possible, this was kind of the first step. We were very happy with the success of this product, and we were asking the question, can we do more now? Can we, like I showed the inner circle and outer circle of software development, can we reuse these models and fine-tune them to do more things and enable innovation in software engineering? That was kind of the question. And so I have a slide which kind of got misplaced, so I might have to come back to that. So one of the questions is, which is kind of, you'll see a lot in the demos. So if I can write something in English text, can I automatically generate code? So for example, if you're a Python code writer, can I write a doc string and a header for a piece of code? Can you automatically generate the code for me? right? And one of the things when we mined the data, we realized that only a third of the code had any docstring at all. So typically, we can, so what we found was we can train these machines in a multimodal way, which is some text, some code, some text and code, and it learns over time, and then it spits out the body of the code. So we built a system which can, take either the signature of the function or the doc string, and it can generate code for you, right? Now, if you look at language translation tasks, typical language translation tasks have, basically an encoder and decoder, as I talked about before. And the encoder part usually uses a mass language model. Basically, what you do is that you train an encoder to fill in a randomly masked input, right? So to see how much it learns, right? So you mask out regions of your code and see, is it able to learn that or not? Sometimes we corrupt the input sequence and see if the model can be trained to retrieve the corrupted part, right? And then in translation, we can also generate a corrupted or a noisy translation and retrieve back the original. So if you can train a machine to do all of this stuff, you can kind of making it stronger and more robust in the rather than just saying, okay, it's got to be exactly this way for me to translate something for you. It knows the good from the bad. And so there's a lot of techniques here. I'm not going to go into the details, but you can translate code using that. So we actually build a code-to-code transpiler. We do Python to C++. We also do C# to Java, etc. by taking this large pre-trained model and then fine-tuning. What do we do to fine-tune it? We create parallel data, which basically is give it examples of, in this case, Python code and C++ code that are equivalent. And then we also do back translation, which means if we want to go from Python to C++, we get an approximate translation. Then you also go from C++ to Python and then go back and forth many times till you get something that you like. And we built an automatic transpiler based upon that. So again, the architecture here is basically you've got a large pre-trained model, then you fine tune to do some specific task that you want to do. Like if you want to generate automatically generate test cases, again, we have this pre-trained model and we give it examples of, focal methods, a method and test that is written for it. And then we fine tune it, we give it examples. You kind of say, this is how you teach a person, right? So you teach them general subject and you give them examples of how to answer certain questions. Then we go ask a question and it will answer that question. So now we can automatically generate unit tests. We can, these are kind of deployed internally and some of them are deployed externally. We can generate regression tests. We can even generate benchmark tests. So, and there is this whole new area of software development called test-driven software development. So in some sense, testing is a hard thing, right? In fact, many companies have gotten rid of their testers. There are automatic testing. So one of the things you say, well, I cannot describe the piece of software I want to write, but if this piece of software passes all these tests, then the software is correct, kind of this approach of test-driven software development. And we can use AI here to actually do that. And another big area is bug detection and fixing. So now bugs could be something very simple like logical bugs or code hygiene. Is it well-written code or not? Or is it a vulnerable code or not? Does it cause security violations, right? Or is it bad code in the sense that is it perform poorly? So example, when we deploy stuff on the cloud, people pay bill for the cloud. And if you have things that take up a lot of time, it is not going to work very well for them. So all of these we kind of bucket under the bug detection and bug fixing. And we kind of say, how do we train these things? And again, you have kind of a pre-trained model, right? So we crawl. So in this case, we crawl, all the commits, we generate examples. So basically you have a piece of code that had a problem before. Then somebody did a commit, fix a problem, put a comment saying, I fixed this performance. I fixed the null pointer, or I fixed this was order n square, now made it order n. So we got examples of before, comment, after. We kind of use that to fine tune the pre-trained model. Now the pre-trained model typically has English and code. So that way it understands English as well as it understands code. Then we take this before, after with performance commits, and we kind of give it examples. For example, I have on the right-hand side here, a piece of code, the context, and the fix that is done for it, and what was the fix. So we fine tune it, and then the left-hand side basically gives you an example how the machine automatically generate performance fixes. For example, here I have a piece of code. This is in C#, but it kind of, I mean, if you know programming, you kind of know what it does. So it replaces a use of for each vector with actually a scalar for loop. And imagine this being called over and over and over again, causing a huge CPU load and significantly improve the performance. Again, you can read the paper. This is again a production system. It was deployed. So this architecture generally works for us, right? Now, you asked the question, I think I kind of hinted on it before. Can you use AI to fix AI itself? So one of the questions that often comes is, well, is it, if it is a stochastic parrot, if it has learned everything from the internet, then it's got to learn good stuff as well as bad stuff, right? So it's going to spit out bad stuff, which means, let's say, a bunch of people have put in their login and passwords there, and I type in password equal to, it might give me one of your passwords or one of your email addresses. So it's going to violate the privacy. It's going to write vulnerable code, right? So how do I kind of use AI to fix AI itself? Again, I can use the same architecture. I can give examples of how to fix bad code with good code or vulnerable code with non-vulnerable code, fine tune it. And now when it is about to recommend a vulnerable piece of code, I can replace it with a good piece of code. And that's exactly what it is. And one of the things I will tell you in our study, what we found was we mined a large set of data and found that about 90% or 95% of the code that's vulnerable is human written, and only 5% of the code is generated by AI. So in some sense, you can have a tool like this even for somebody, a naive person, right, trying to write code, right? And they are likely to, say, use an older protocol of HTTP or older protocol of some API, which might have a security hole, and you can correct their code right away before it goes into production. So there's huge value to actually using AI to fix itself, but also human written code, right? Now, one of the challenges is, how do you measure goodness? Now, because a lot of the stuff that we did came from NLP. Now, NLP, I think I kind of gave a hint at the beginning, is like, it's text. Everything is looked up as tokens. We didn't talk about grammars at all. It's text left to right, words from left to right. And, typically, if you read an NLP paper, their metrics are perplexity metrics, precision recall, ROC, blue score, et cetera, which are basically added distances of word. How far is one word from the other? But think of code, right? If I replace A++ with A-, or, A equal to A plus 7 with A equal to A minus 7, they're pretty close, but one is completely wrong, right? So we need very different metrics and for code. The other thing is, we have other metrics like, is the code readable? Because finally, it's going to be maintained by human beings. Is the code executable, right? So we can't produce a code that's 99.9% correct, but that 1.1% bug that it introduces takes a lot more time to debug than somebody would have written from scratch, right? So does the code pass a certain set of tests? How efficient is the code? How risky is the code? So these are all the metrics we take into account before we kind of call the metrics good, right? And so there is a lot of work that is going on in this area of finding the metrics, good metrics for code translation or code generation. Another thing we found was offline metrics and online metrics. I hinted about this before. One thing you'll see when you read machine learning papers is, often almost all the papers will quote offline metrics, which would be beating, state of the art by 10% is kind of a typical metric to get a paper accepted. That's not good enough when you deploy a product. So you will go through a whole series of tests, internal tests, what we call dog fooding, to actually online deployment. And almost always we find that algorithmic correctness or algorithmic goodness is not good enough, because now there is a human interaction that happens. So which means that HCI, or the way these things are presented to the user, the way they're recommended or the way they're completed, even a keystroke here or there makes a huge difference. And it's good and bad, because sometimes we have a good enough algorithm and we can mitigate any kind of gaps you have with good UI. Alternatively, you can have great algorithm, but if you have bad UI, then it's going to take away the benefits you get from the algorithm. So you have to kind of be careful to combine both of these things, right? So, so all of these things become really, really important when you deploy to the production. Like I said, the last mile literally for AI is the human experience. Now, the interaction versus interference is a very important thing. So you're writing code, somebody interacts with you, the system interacts with you. Is it slowing you down? Is it breaking your thought process? Or is it actually helping you, right? So the other thing is also, when we call it shifting left, in the sense that why fix the bug? Why don't you write good code in the beginning? So we try to bring all of the AI more and more to edit time than at build time or than at PR time, etc. But at the same time, we also have to worry about what is the cost of prevention over cure. If you have to take 25 kinds of vitamins in order to not fall sick, does it even work for you, right? So that's the opposite of taking 25 kinds of medicine when you're sick, right? And we got to balance the two out, and it's very similar to that, right? Now there is this whole new area with AI, and you must have read articles or seen discussions about it. Number one, the question is, is it going to replace human? Is AI going to replace human beings? And frankly, I mean, this probably questions have been asked over 100 years. Are machines going to replace human beings? And the answer is maybe in some cases, maybe it helps humans to do more intelligent things or more powerful things, et cetera, et cetera. And the way we think about AI, at least for software developers, is automate the mundane things. And there are complex things that you can't do, right? Especially if you're a new developer, you may not know all of the API changes that have happened. So it guides you through that. And that's a huge benefit of AI. Another risk we have is with AI, if you look at all of the metrics, typically when you see with an AI product is, we almost always produce majority metrics. So when I give you a score, I'll say accuracy of 90%. So what does that 10% mean? Who is getting disadvantaged here? It's kind of like if I were to say, there was 90% admission to this program. But if you were to break it down to say gender, male versus female, or majority race versus minority race, you have to ask the question, what percent of the majority race got accepted and what percent of the minority got accepted? And the answer might be very different. And now in software, what is the cost of that? Because that minority would be that vulnerability I talked about, which might cause a lot more problem in your system than the benefit you got from the majority, right? So in some sense, focusing on the majority metrics can introduce this kind of homogeneity in your system that can have long-term negative effects, right? So one of the things we talk about is how do we introduce heterogeneity with, that helps us understand these diverse effects of this, right? Now, other thing is that, quite often when we deploy this system, especially when we deploy to enterprise customers, the question get asked is, okay, I'm not going to share my data with other customers, right? So my data is mine. So how do I deploy a model that learns only from my data, only benefits me? How much of the privacy do you guarantee? And how much of the privacy do you guarantee during inference time in terms of leaking my private information, et cetera, et cetera? And how much misinformation are you going to share about me or with me because you learned poorly? And so we constantly have to answer these questions to our customers who do not completely understand this, right? So again, we repeatedly see in hardware is that the minority risks are very, very important because there is possibility of models and data being poisoned when they're out there, right? So with that, I think, I want to close this talk by saying this is, in automation in software or in bringing developer productivity or software productivity, we are at an important juncture, right? We have models, we have systems, we have AI to our benefit. We have few answers, we have some promises, but we have a lot more questions, but we have a lot of optimism, which is really what Professor Nori used to say, right? Try it, do it, and then see what happens. In fact, years later, when I took my wife to introduce her to him, he kind of said, he was 22 years old at that time, and I asked him if he can generate this piece of software in 4 weeks, and he was stupid enough to say yes. And I'm glad that he was stupid. I think sometimes stupidity does help because you trust something that's bigger than you. So with that, I want to close the talk. And I don't know if you have time for questions. I've not been watching time, but I really want to thank you for the invitation. This is quite an opportunity and honor to be speaking at Professor Nori's memorial workshop. Thank you.
So now the time for question answer session. So if anyone has any question, please. Are you going to give my mic? Otherwise, you can come down here, right? They can come. Questions? Please. Mic.
My name is Amod Sane. I was in Yahoo Search the architect of one of the pieces. And a few years back, I came to India and we started a new department at Flame University. So my question is, does Microsoft have in place any kind of data sharing agreements with academia? Because we used to do that in Yahoo Search, and without such things, academics are essentially permanently blocked from contributing to the kinds of stuff that you do, even if we think of ideas.
Mm-hmm.
The data simply isn't there, right? So you can't just generate it. Add to that the complications of being in India, not being in IITs, blah blah blah. So all those difficulties are there.
So actually, if you can hear me, I hear a lot of static. So frankly, this question used to be relevant 20 years ago. It's not relevant anymore. In fact, almost everything that I showed you today is not from internal data. It is external data. Today, you have so much data that's available outside. It used to be, 15 years ago, people would come to eBay and say, oh, can I have your data? And because it was behind, this walled garden and, you don't have the data, we can't really do work. There are two things I want to say about data. Number one, data is not a one-time thing. You never get a clean piece of data and you're done. Like we often say in data science or in machine learning, 80% of the work is actually iteratively getting to the data. And only 20% is really the algorithm of the work. The second thing is today, pretty much all the data that you want to work with is available on the internet. You really don't need to go to a Microsoft or a Google and ask for the data. In fact, all of the papers that get published from these places are also on public data. There is nothing that's private anymore. And that's kind of why I said, it's a wonderful time to be doing large-scale AI research because there is data that's publicly available, there's code that's publicly available, there are systems that are publicly available, and there are models that are publicly available. Hardware is one thing where you might actually have to struggle some. So that somebody has to fund you. Nobody's going to give you hardware unless you have the money. I'm pretty sure it's a matter of time. And one of the things we have done is ship some of our platforms because internally to ship products, we have to do a lot of work to shrink these models. So we can't afford to ship a model that comes directly from OpenAI or something. They're nice demos, but at the same time, when we ship it, these are pretty expensive inferences. You can't afford to do an inference on a 16 GPU machine for every call. These are super expensive. Our customers won't pay for them. So we have to translate everything down to a CPU, something that can run on your laptop. So there's a ton of work that is done in shrinking. I didn't talk about those things at all. A ton of work that is done in shrinking the model sizes to something that's acceptable in a way that you don't lose accuracy, but actually it works for you. So I think I will also tell you a lot of innovation comes from the open source world, from the outside world. It doesn't come from industry. In fact, there's a catch-up game today between the industry and the outside world because of availability of free availability of APIs, free availability of models, free availability of data. Wonderful things are happening actually at universities and even, small companies, frankly.
Okay, so your papers, many of them are with the university people without any benefits of hardware and all. Is that what you are saying?
No, most of our papers are written by our researchers, right? Or if there is an intern who has come and worked with us, or if there is a partnership with the university. But really, it's driven by our research. But at the same time, there are a lot of equivalent papers that are written by folks from universities which are very good papers. In fact, we refer to them, they refer to us. So it's almost like we're equal partners in research. I don't think today universities are at any disadvantage in doing good work, frankly. Hardware is still an issue, but you can still do a lot of good work with just standard GPUs you have on your desktop.
I see. Okay.
Any other question from audience?
Namaskar, my name is Ambuja Sagavkar. I work in natural language processing and machine translations. So maybe this question is a very naive program translation, but then what I felt is if we are translating program from one language to other language, then it may be for exploiting the potential of the target language. Is that so? Then how the translation will be possible if something was not there in the source and that we are trying to bring it in the target language. So what kind of things would be required to look into? And then back translation that you said ki it is near back translation, probably that could be imagined like in the natural language also what we do, the things that are not available in the source language, we exclude them, or some near to that could be added. But this exploitation of the target language potential, that part, could you speak something more on that?
Yeah, sure. So there are a lot of parallels. It's a wonderful question, actually. I didn't talk about it very well, but thanks for the question. So one of the things is that there's a lot of parallels between natural language translation and programming language translation. The big difference is that natural language translation is mostly for human consumption. So for example, my mother came from the south, she moved to Bombay, she got married to my dad, she spoke only Tamil, then she learned a little bit of Malayalam, then she learned a little bit of Gujarati because our neighbors were Gujaratis, then she learned some Hindi because she had to talk with the shopkeepers and the radiwalas, and then she learned some Marathi because she had to speak to the maids, etc., etc. So she knew one language, and she kind of expanded because even though these languages are not the same, they're similar, so there are structures they could exploit. And these things, the machine translation is very similar to that. Now, what you're talking about is something called idiomatic translation. So which means that, so that's why if a native Marathi speaker would be very different from when I speak Marathi, right? Because I'll be extra careful, and you might use some slang, you might use some phrases which are very which will identify you as a native Marathi speaker and me as not a native Marathi speaker. And that's, in programming language, you call it idiomatic translation. So while I can translate all of C++ to Java or Python to C# or whatever it is, I may not be able to produce idiomatic C# code. So this back translation is mainly to produce correct code, right? It is not to produce idiomatic code. Now, if you want to produce idiomatic code, and you're right that in NLP, number one, because languages are sequential left to right, and one thing I don't know if I mentioned or not, transformers are good at, because they look at things sequentially, but programs are not sequential. They have a parse tree, they have a semantic structure, etc., etc. And in fact, Nicholas Wirth talked about a stepwise refinement. I mean, we have done a bunch of work on gram formers, etc. We say, how do we take advantage of the grammar, etc. also. So you can also attach to that, how do we take advantage of this idiomatic way of writing Java? I wouldn't write Java this particular way. For example, let's take Python. In Python, I might say A equal to A plus 1. But in Java or C++, I will say A plus plus, right? So now to translate, but I can also say equal to A plus 1 in Java. It will be correct, but it won't be idiomatic. It is not like human written language. So that's where we bring in fine-tuning. So fine-tuning says you have general intelligence of how these languages work. You know enough C++, you know enough Java, you know enough about the translation between the two, but I'm going to slap you with some more examples of how idiomatic translations are done. And in that fine-tuning process, now think about you know these general languages. Fine-tuning is like special training for you to produce good code. And it is a very important step because otherwise we can't create these systems from scratch. These are very expensive to create. So today, like the gentleman before me was asking about what can researchers at universities do? You got a lot of pre-trained models available out there. The endpoints are available and you can do fine-tuning. Okay, I'm going to make this translation better by teaching how to produce idiomatic code. I'm going to make this translator by teaching it how to write, codes that use good design patterns, etc., etc. I can do that. And you can do the same thing with languages as well, in natural languages as well. You could say, I'm going to teach this thing while it is doing, say, English to Marathi. I'm going to teach it how to use the words that, or the phrases, or the way it's written, say, in Pune versus, some other part of India where Marathi is spoken slightly different, right? So you can do stuff like that in the fine-tuning step. Hopefully I answered your question.
Any other question?
So, Neil, this is Adi here. A very nice talk, so thank you. So just taking this idiomatic translation a little forward, at times it's not just from C++ to Java, but people wanting to move from, like say, imperative to an object-oriented language, okay? Even in the case of C++ to Java, the requirement could really be that the C++ hasn't really exploited the object-oriented concepts, okay?
Absolutely.
So bringing in sort of the domain knowledge into this translation, okay? So is there any work, especially using AI techniques, to figure out what the code is doing and then exploiting that knowledge, the domain knowledge, to do the translation more effectively, exploiting the object-oriented features that potentially were not exploited in the source language? So are there some comments that you would like to make on that part?
Oh, yeah, absolutely. I mean, it's very similar to the previous question. There's a ton of work that's going on in this area. So there are two things, right? So one thing is that, I mean, you worked with me, you know about grammars and you know what we did with grammars, and super rigid, right? You go to write these tree transformation patterns and you take the source pattern, translate to target pattern. Either you match or you don't match, there is no in between. The nice thing about AI is that anything goes. You could be half correct, you could be almost correct, you could be somewhat correct. It gives you that freedom. So that allows you to learn what might be the patterns in the target language and map it back to the source language and kind of say, oh, if I see this structure, complicated structure, it could actually translate to this other thing. Because I don't have to be correct all the time. I don't have to be correct half the time. And the more complex a thing, the more forgiving the system is. I'll tell you my experience deploying this system. Professor Nori would never agree because he wanted complete translation. And we have deployed translations where we can translate only 30–40% of the code. And developers love it because, I mean, I don't know, people who are writing a lot of code won't believe, I mean, we don't take pride in writing a lot of code because if you write a lot of code, quite likely you're writing a lot of mundane code. So they're so happy that the mundane code part is taken care of automatically and they can focus on stuff that is more complicated. And so anytime you give them something that translates a design pattern in a nice way, they're super excited about it. They're more welcoming even if it makes some mistakes, right? So it's work in progress. We are not done yet. As I said, just 3 years ago, we started with 10 million parameter model. Today, the state of the art is 200 billion parameter models, right? So we've gone like literally, from 10 million to 200 billion. But when we deploy things in production, we can barely deploy a billion parameter model unless we use a lot of resources. So there's a lot of back and forth that's going on, but there is a ton of work, even my own team, but there's also a lot of work happening outside in kind of making them better as we go, right? How do we, like another example I didn't give is, like what we do is that because we train them in multiple languages, so because it sees all the code, it sees code in Java, it sees code in C++, in Python, so on and so forth. Now suppose, there are these majority languages, so you see a lot of code in Java and Python in the web, but take something like Scala or Scheme, you won't see a lot of code in the web. But now you want to generate or translate code to those languages. You get something out of the box for free. you will get an accuracy of say 45, 50% for free. It's kind of like saying, I speak Hindi and I speak Marathi, and then some Punjabi person shows up. I can speak some broken Punjabi, right? I can manage, but I can manage a small conversation. So you get things for free without actually trying to write a translator or a parser or a translator generator, etc. So that's a wonderful thing about it. That, and this has been used again in the NLP world, where they have been managed to translate, minority languages like tribal languages. So you take even African tribal language, or we can do it even for Indian languages, which have small mappings to some other larger languages, and you don't have a lot of data on these languages. It's okay because you have seen so many languages that you can do some reasonable amount of mapping. So it's a combination of humans and AI that come together to help you do this.
Anyone else?
There is volunteer at the back side. If anyone has question, please raise your hand so that I can give. Sir, volunteer is there back side.
Yeah, it is not a question or query, but I would like to add a comment on what you said. Mundane task is also taken care and it is welcome. One of the other experiences is I worked on scriptology. So there also the people say, yeah, generally transcriptions and all 90%, 96, 99% also are expected. But in some cases, like say we are working on Modi, so even if it is 40%, then also it generates context for the reader. And the remaining part could be added there very easily instead of starting from scratch.
Yeah.
I think the same thing you told about the translation also, which is, of course, that's the experience. But it was very nice to listen to you. Thank you so
absolutely.
much.
That is the whole point. Yeah, that is the thing. So don't expect 100%. You will get something, and that something is reasonable. As long as it is less wrong than you expect it to be, it's good.
Any other question?
Hi Neil, this is Vivek here. I have one question. So actually we have grown up with a computational thinking in mind actually, and okay, on the way we learned that okay, data is important, and the data thinking started coming into picture. Now there are a lot of academicians here also. So, and we face these challenges in recruitment sometimes, that how basically this both computational thinking and data thinking can be inculcated into the minds of the new students and the new generation, and what can be taught and what can be basically how it can be in fact improvised rather, because generally it's more of a challenge in fact I have seen.
Absolutely. I think that is a challenge. In fact, I was listening to a panel just last week at Stanford, and somebody famous said, universities are about a generation behind, what the industry needs. So what you learn in the university is always a step behind what you actually need for the industry, right? Which I don't completely believe. I think what the universities provide you is the foundation. So foundations are really, really important. So for example, even in the US, you get students who don't understand linear algebra very well, right? Now you cannot do really good machine learning without understanding linear algebra, right? Because sometimes, they go to either take classes which just, use some packages. Say, tf.train, tf.test, tf.validate, you're done. I've built a machine learning model which does, sentiment identification or, That's really not training. In fact, some of the best, in my own team, I can kind of say this in public here, the best scientists are people with physics background. Because they understand statistics really well. They understand math really well. And if you really want to do AI, and also they build systems, they can write code well. So in some sense, I mean, this might be my opinion and I might be completely wrong. I really do not know about the curriculum anymore, is that I think computer science is kind of lacking this foundation. There's a lot of universities now offer data science programs because data science is a hot field. It's a quick way to make money as well, but also quickly train because we are always short of people. And one of the things is they don't get trained in these areas. So we kind of tend to ignore. Let me quickly, in fact, now There's even a rush to teach in high school, teach machine learning in high school before they've even done the first calculus course. Right? Just because you can use the package doesn't make you a machine learning person. I think foundations are really important. But I would say if I were to hire all the graduates you produce, I would hire somebody who has a stronger foundation over somebody who knows NumPy and who knows TensorFlow and who knows, whatever other package, right? Because that's really essential in all of this stuff. Like knowing the foundations is really important, and rest can be taught, right? That's the point. So I would say, and other thing I would say, training. One of the other challenges you have with data scientists is like, particularly computer scientists, is they want to very quickly build models, right? If you talk to somebody, they'll just say, oh, I want to build a deep learning model. Frankly, you should say, stop, look at the data. You should spend most of your time looking at the data. You are not, it's kind of like when they teach music, right? They don't let you play certain things before you learn certain other things. So it's really like that. Spend enough time looking at the data, come up with the simplest model that will work, and then improve upon it. And that discipline has to be taught in schools. Right? I've had interviewed candidates who come and say, I just want to do deep neural networks. Without, why do you want to do deep neural networks? It doesn't solve all your problems, right? Or you may not need it to solve all your problems, right? So that kind of thinking has also to be encouraged.
Thanks, Dean. Any other question? Yeah. So I think there are no questions now from the audience. So I, on behalf of Pune Professional Chapter, ACM, I take this opportunity to thank you all for taking out, thank you for taking out your time and spending this beautiful evening with us. So it must be evening for you. So thank you for sharing your ideas about program synthesis from grammars to AI. It was really the nice tour for all of us. And even the memories of Dr. Nori and the Damdare. So we are still, I'm from academic background and we are still using Dr. Damdare's book for many subjects as the best to learn the basic. So thank you for all your contribution. And your team has done, along with you, wonderful job in conversion of the languages, interconversion of the languages. And definitely it has very great impact. So thank you very much. Thank you.
Thank you so much. Yeah, appreciate the invitation. I again
Small
apologize for
token
not
of
being there.
appreciation from our side. Sir, please repeat, your voice was not audible.
Okay, I just wanted to thank you all. Again, it's a lot of work. I again apologize really miss Pune and miss being there as part of this thing, and especially Professor Nori's celebration. It would have been wonderful to be there, but maybe in the future, come visit you folks. Would love to continue this conversation if anybody is interested. Again, I know a lot of you, worked with a lot of you, and would love to meet more people and continue this conversation as well. Thank you again, and thank you for inviting.
Thank you. Yeah, thanks. Bye. So now this is break for the audience who is present physically here. Breakfast is organized outside the hall, back side of the hall. And for online audience, they can enjoy tea, coffee at the place. So break is of 15 minutes. 129 participants have joined online to us.
check, hello, 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 check, hello, hello, check, check, hello, 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 hello.
Hello, 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 check, hello, 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 test, check, hello, 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 check, hello, 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 check, hello, hello.
हे अमित आएगा ना टीवी कर रहा है ना
Hello, hello, hello. Check. Hello, hello.
तो उसने चेंज किया था
Hello.
लेकिन ये तो डायरेक्ट है ना
वो डायरेक्ट है यदि उधर ना एक केबल उल्टा पलटी हो गया तो ना इधर आएगा ना उधर जाएगा
क्या भी आ रहा है
बराबर आएगा क्योंकि मैंने ना सेपरेट दिया है क्यों
बघ हे बघ कुठं जाते ते रे हे बघ गेलं मशीन सोडतोय काय हा
हेलो 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 इसका वायर चेंज करके देखने का क्या फिर वायर का कोई इश्यू नहीं रहेगा मग तो हाँ हेलो 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 चेक हेलो 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 डिले लगेगा हेलो 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 हेलो
ये में दिया है तो ये जोड़ा ना तो कैमरे को इको जा रहा है
क्या
Hello everyone. Hello everyone. So next I invite Executive Director ACM India, Mr. Hemant Pandey, Dr. Hemant Pandey rather, and Umesh Puranik to talk about ACM India and ACM Pune Professional Chapter. So please Hemant and Umesh, please.
Good morning, everyone. I'm Hemant Pandey. I'm with ACM India. There is some effort to bring up a slide presentation. I won't need it, so I can do without it. So if not, that's okay. Otherwise, by the time Umesh comes in, if it's up there, that's all right. Okay. So good morning, everyone. I'm really feeling privileged. Am I audible? Yeah. So I'm really privileged to be here participating in this KV Nori Memorial Workshop, and kudos to ACM India Pune Professional Chapter, TCS Research, as well as SPPU for organizing a really fitting tribute to Professor Nori. Well, I say Professor Nori, but I remember when I joined TRDDC after my master's, my boss obviously was Professor Nori, and you know the way and man is everybody knows tall personality, right? And you are in awe of somebody like this, but he would say, "Call me Keshav." I said, "No, how can I call you Keshav?" So okay, KVN. So I think that stuck. So I call him KVN. Right? So I had the honor of having KVN as my mentor for 8 years, at least while I was at TRDDC. And of course, his contributions are well known, individual contribution to computing are well known, but also what made him a great leader by creating leaders of us through his passion, which rubbed off on people, his sense of humor. I mean, everybody would remember his laughter, okay, when he appreciated something, and also his willingness to debate rather than argue, okay, at even keel. I mean, he didn't look down upon you. Okay. So all those things made him a wonderful leader for us. And I think everybody, whether it was RD, Venki, Neil, everybody talked about his passion for generating generators. So I was part of the team which created program analyzer generator. So it was a high level language which you specify which would what kind of program analyzer generator you want, and then lower level language which would instantiate the program analyzer. So in some sense, we, the team, were the program analyzer generators. And since KVN was our inspiration, he created that of us. I think he was the program analyzer generator. I think I'm getting lost right now, and probably you're getting lost. Okay. So nevertheless, that's the kind of person he was, and that's why I'm very happy to be here. I can spend a long time to talk about ACM India, and things like that. But this is about KVN. So all I would say is that ACM, world's largest organization of professional society of computing, out of that more than 12-13% are in India, and should be more actually. Okay, but simply said, ACM is of the members, by the volunteers, because they are the ones who do the work, and for the community, for the computing community. So if I were to describe ACM, that would be it. And the activity that goes on at ACM or by ACM, it's under a few categories, which is promoting research, promoting education, promoting being actively helpful in professional development of individuals, and recognizing and encouraging contributions. Okay? And underpinning all this, of course, is the principle of DEI, which is diversity, equity, and inclusion. And this mission would have obviously gelled with KVN because he stood for all of these things. Okay? And rather than talking much more about ACM and ACM India, I've just given you a glimpse of it and how it translates on the ground. I will invite Umesh, who represents ACM India Pune professional chapter, which is a very active chapter. And I'm sure a lot of things that I've said or given the categories of, lot of that work is happening through Pune chapter. So I'll hand over to Umesh now. Thank you.
Thanks, Hemant. It was a pleasure to have you talk about SEM. And I'm sure many of you here already know about SEM. So what I'm going to talk about is not exactly really for you, but those who are not really aware of what SEM is doing, and specifically what SEM India and SEM Pune is doing. So there are various chapters in SEM. There are student chapters, there are women chapters, student women chapter, professional chapters, as well as special interest group professional chapters. So out of these, you would see that basically the concept behind these chapters is these are local neighborhood chapters. The idea is to get all people in the closer vicinity in the region together, have them exchange ideas, discuss various topics, and see how computational computing can benefit, how the exchange of ideas can benefit each other. So worldwide, there are more than 200 professional chapters and and more than 860 student chapters. Out of these, actually 10% of professional chapters are in India, and these numbers are slightly older. Obviously, you'll find more updated numbers on ACM website. The student chapters are thriving very much in India. Almost 25% of chapters worldwide are in India, and that's more than 200 chapters. The benefits are a lot, and that is for students as well as professionals. You get access to a variety of ACM communications. There is a fantastic digital library that is available online, and you get that access along with your membership. Importantly, you get access to events like this, where you can go interact with people, interact with professionals, interact with academicians. And that helps you expand your horizons rather than just studying one single topic, working on one single isolated domain. ACM facilitates these things by providing a variety of venues and events. For example, there had been lecture series, there are webinars, there are learning forums where people can come and exchange their ideas. They can start building some how-tos and proliferate the knowledge that they have. And then each of these events, they obviously go without saying that you get opportunities to network with peers as well as experts. For example, right now I know many of the experts here. I have never interacted with them before, but now I know what kind of work they are doing, and that gives every individual some chance, some boost to go and learn something new beyond their comfort zone, which is one of the biggest benefits. About these chapters, you can find a lot more information at the website, or the ICM website, and you are highly encouraged to come and join those things. Coming to the professional chapter that we have here in Pune, our mission is basically to focus on academic, educational, and scientific purposes. Goes without saying that it is still focused on programming, computational thinking, and then it's a variety of activities that we put together, like enhance the knowledge, share the interest of the community, as well as applications of modern computing, various topics that you don't really get to see every day. For example, you heard Dr. Sundaresan's lecture about AI and how to use it in a variety of domains. That's not a run-of-the-mill topic. And that's, again, I would like to highlight here that these are the things that you really enjoy when you become part of this local community. Right now, this Pune professional chapter, we have access to every resource that ACM has worldwide, but we still call it as a Pune professional chapter just to emphasize, highlight that we are focused on the local community. The sole goal, I'll repeat, is to bring people together and then benefit from each other's knowledge. So I'll keep it short. Here are the set of people who are kind of driving the current activities. We have elections, we change the committees every year, every 2 years, and so on. And it's very thriving community. I'll just say that with this, I'll stop and encourage, invite each one of you who is not a member of this community so far, be a student, be a professional, come join us. Together we can do many things. And I'm glad that we are getting this opportunity to meet after this pandemic. At least we can see face to face. In terms of past events, what we do, we had recently organized some programming related sessions, a webinar, where academicians, industry veterans, they came together, they discussed a lot of topics where the gap between the industry and the academics is. As Dr. Sundarshan mentioned, it's kind of the universities, academics, they are kind of a generation behind the industry. And that was one of the ideas, that what we need to teach in the universities, in the colleges, so that people are up and running without losing the anchor in their fundamentals. And this idea of exchange definitely helps in the bigger run. We also had some lectures and sessions about really upcoming topics. I'm sure you would have just heard of unified communications, which is a lot more than just your 5G or wireless or mobile communications. And how do you use those integrated approaches for the bigger benefit? One good example is disaster management and relief. So, or even the places where your mobile 5G network doesn't reach easily. An example would be mines, underground, a kilometer down behind under the earth. Obviously, you don't expect any signal to reach. But with this unified communication, what you can do is really interesting, wonderful. So I just highlighted these two activities we carried out recently, just to give you a flavor of what we do. And I will stop with this appeal once again, that come join us, we'll do something really good together and keep doing it further. Thank you, everyone. And with this, I'll pause, stop, and request Professor Sahasrabuddhe to come and join us. Thank you.
Well, I stand here to slightly modify the subject that has been given to me. I'm not going to talk just about Keshav Nori's contribution to the Pune University Department of Computer Science, but personally, his contribution to me. Because I knew him from the time we lived in the same wing of the same hostel in IIT Kanpur and learned Jujutsu from the same professor of chemical engineering there. There is a lot about Keshav Nori in, I think, the third issue of a resurrected student magazine called The Spark. You just Google for IIT Kanpur, The Spark, you will find the magazine. There's, I think, one complete issue, more or less, dedicated to Keshav Nori. Because we had two extended visits from Keshav Nori in IIT Kanpur. First, he was there as a student, when I got to know him closely. And subsequently, he went to TIFR and Carnegie Mellon and so on, and came back to us some years later as a teacher. But he had not forgotten his student days. One of the features of student days is that you learn to hate the food that the hostel is serving you. Keshav Nori was friends with many undergraduate students. He had almost a circle of students. He had hired a cook, and in his house, the cook came in the evening before Keshav Nori arrived, counted the number of spoons that were there on the dining table and cooked for that many people. And any one of his circle of students, if they wanted a break from the hostel food, all they had to do is go to Keshav Nori's house, add one more spoon there, and they had a place they could eat there. That was the level of generosity of Keshav Nori. This is only an example. I mean, just giving you dinner is a trivial example. But whatever you wanted, if Nori knew your need and if Nori could help in any way, he was always there to help. And this is in essence what we got from Keshav Nori in the Pune University Department of Computer Science. We were fledgling new Department of Computer Science, short of faculty. That goes without saying. If you are trying to run a computer science department, you are short of de facto faculty. I mean, you may have people on your roster, but who is going to teach course X, course Y, course Z? There is always a problem. We were frugal. We didn't take on anybody who could not contribute to that list. So we were really short of staff, 3-4 people department. And if Keshav Nori did not have the time to teach a course himself, he would find us one teacher. But I think that even that contribution is overshadowed by his more important contribution of giving direction to the department. As a young department that needed a lot of planning to go from year to year and decade to decade, we held frequent curriculum committee meetings. The curriculum committee was essentially the faculty. But we always invited Keshav Nori to these meetings, and he always made himself available. The number of ideas that he has given to the department, our curricula, our progress as a thriving computer science community is immeasurable. He was always there when we wanted. And this is in spite of the fact that he was working full-time for the Tatas. He had no prescription of any kind to work for us. In fact, one of the teachers he provided us with, whom I just talked to in the morning today, I didn't even remember that incident. But we needed a teacher for a programming course, and he provided us one. And that teacher was working in TCS for him. And he said, "But sir, my job contract says clearly you cannot work outside TCS while you are in our employment." So you know what Keshav Nori said? "I am your boss. I am telling you to go there and teach. So it is TCS work." It is a well-known fact that anybody who strikes out a new path, does something revolutionary, has to break rules. But which rule to break when is the great art. Keshav Nori was not just technical, he was not just computer science. He saw beauty, like somebody said, in abstraction, in structure. And he seeked beauty wherever it was. He taught many of us at IIT Kanpur origami, the art of paper folding. And one evening I clearly remember he was at my house He brought a load of red and green paper squares already cut with him. And he had my children sitting there folding origami strawberries, which looked very real. Because he had himself folded a bowl and he wanted strawberries to fill that bowl. So Keshav Nori was not just computer science, Keshav Nori was not just philosophy, Keshav Nori was not just charity. I think if you look at that issue of Spark, you will find a lot of material that perhaps is not known so well outside IIT Kanpur. And IIT Kanpur was the nursery from where PUCSD came. Because when I was approached to start the department, I said, well, I'll try to build a department like an IIT Kanpur department if there is an opportunity to do that. And I was promised by the then Vice Chancellor, Professor R.G. Takavle, that yes, we will, as long as you're building a good computer science department and we see that, we are willing to bend whatever rules conflict with your goal. And he did that. He did that and his 2 or 3 successors did that. That is why we were able to bring, I was basically, in my mind, I was just thinking, look, this is a transplant. I have brought this from IIT Kanpur and I'm going to try and grow it here. I got great help. I mean, God sent me assistants no end. Professor Shankar, who was my senior by almost a decade, came and joined that department. One day a lady walked in and she said, I have a PhD from Department of Computer Science, IIT Delhi. What can I do here? I said, well, join us. What else? So there were people like that that came to the department to help us. And I think Keshav Nori's name stands very big in that list. It was because of people like him who shared the vision. We probably spoke a very similar language and who had personally seen what IIT Kanpur could be and helped me in this transplantation job. So it is with great emotion that I remember Keshav Nori, not just as a computer person, but as a person, as a human being who had a large heart, and he opened that heart to anybody who needed to get help from him. With that, I think I'll end my talk. I'm feeling guilty when Venkatesh said we have a great, highly technical content today, and my talk is not technical at all. So I was feeling guilty about coming and giving this talk here at all. I hope that I have conveyed in whatever little time I could convey to you something of the personality that was Keshav Nori, something a little more than like a pillar or like a wall or like a rope. I've attempted to try and complete that elephant. And I hope to some extent I have succeeded. Thank you very much for listening to all this nonsense. Thank you.
Thank you, Professor HVS. In fact, he has taught us so many good technical things, theoretical computer science, then the database systems. In fact, I was on board of one of this particular college actually. And that time I asked them what books you use. And everyone said XYZ, XYZ. But no one has actually used or are using Ullman. That is, I still remember actually, because that book actually of database, of our principles of database system where Professor HVS taught us is one of the best book I found in fact. So thanks a lot, Professor HVS, and I will invite Dr. Mehta, to, Ravindra Mehta to invite Saurav for his talk.
Good morning. So it is my great pleasure to invite Professor Saurav Bansal from IIT Delhi. Saurav holds a PhD from Stanford. His primary research interests are in programming languages and operating systems, especially in super optimization based compiler design, something that Professor Nori was also very interested in. He's also a CTO and co-founder of a company called Compiler AI, which builds lots of tools for super optimization based program translations. So I invite Professor Saurav to now talk about his extremely exciting talk about database looking at compilers as a database of transformations.
Okay. Assume you can hear me? Yes, I think so. Thank you, Ravi. Okay, thanks a lot, Ravi, for the kind introduction. Thank you to Venki and Ravi and all the TCS team and the organizers for having me here. It's a really huge privilege and honor to speak at this occasion of Professor K.V. Nori's memorial. I really enjoyed listening everything I heard about Professor K.V. Nori since the morning. I mean, honestly, like I haven't spoken at a better venue about my work than this venue, because I just feel like what Professor Nori's thoughts were. Unfortunately, I never got a chance to meet him or even interact with him. But you know, whatever I hear of him, I just feel unfortunate to not have met him. So great. And also I want to, I feel like there's a very, very great audience here. I especially want to say that Professor H.V. Sahasrabuddhe was, I recall, on my interview committee when I was applying for assistant professor at IIT Delhi. And my work was actually similar to what I'm going to present today. I'm just extending that, and I'll refer to it a little bit. And I remember he asked me like, oh, so you ran out of time. And that made me really nervous, because he was basically saying that, looks like you ran out of time, your PhD work doesn't look complete. So, I mean, as an interview candidate, I was, I didn't know what to say, and he was right. And, I just thought, I hope it's not going to work negative. Eventually, I guess the committee decided to take me on, and thank God for that. But so it's a really privilege to actually speak to this audience. And once again, thank you for inviting me. So the title of my talk is The Compiler as a Database of Code Transformations. I'm a faculty member at IIT Delhi, and I'm also doing a startup called Compiler AI Labs. This is joint work with my PhD advisor, Alex Aiken, and my PhD advisees, Manjeet Dahiya, Shubhani, Abhishek Rose, and several other past members of our research group at IIT Delhi. So at the turn of the millennium in the year 2000, there was surveys done on what are the top 10 algorithms with the greatest influence on science and engineering in the 20th century. And you will find some interesting names here, like the fast Fourier transform, the quicksort algorithm, etc. But one of the entries that is especially relevant for this audience is the Fortran optimizing compiler. Now, this paper was published in 2000 in IEEE Computing in Science and Engineering. And here is an excerpt from this paper, which says that John Backus leads a team in 1957 at IBM in developing the Fortran optimizing compiler. The creation of Fortran may rank as the single most important event in the history of computer programming. Finally, scientists and others could tell the computer what they wanted it to do without having to descend into the netherworld of machine code. So, I mean, this is what people thought about compilers in the year 2000. We are in 2022, so we're already 22 years hence. And I think today the need for compilers is even more important, and it's going to become even more important in the next few decades. And that's probably because we have an increasing number of languages, because we want both things that are easier to program and are kind of amenable to high performance, and also increasing number of architectures, because Moore's law has kind of died and maybe or at least saturated, and we need more innovation on the architecture front. And this gap between easy to programming languages and high performance architectures is supposed to be filled by this tool called a compiler. And this problem is that compilers are really slow in adapting to these increasing demands, both at the language level and at the architecture level. And so this picture basically kind of tries to capture that, because all these architects are bubbling with new ideas on how they can add more cores, how they can have accelerators, complex instruction sets, new abstractions on how you can program the machine. But the problem is, who's going to program these machines? Because unless compilers support those abstractions, very few humans will be able to descend into the netherworld of assembly code. They need high-level abstractions which are easy, intuitive, that lots of people can program. And unless compilers catch up, we are not going to get there. And so architects are just forced to wait for the compiler to catch up, and that's the unfortunate reality of the world today. Now, the question is, why are compilers so slow to catch up? So the answer is in the complexity of a compiler, I think. So this is the number of lines of code in GCC over time. On the y-axis, we have 1,000 lines of code, or KLOC, and on the x-axis, we have time, starting from 1992, from which data was available, and from 92 till the end of last year, which is 2021, December 2021. This chart shows the number of lines of code in GCC. It's astounding to see that the number of lines of code is continuously increasing over the last 2-3 decades, right? And it's actually increasing at the rate of 2 million lines of code every 3 years. Today, GCC stands at 18 million lines of code, when at 1992, it was less than 100,000 lines of code. Now, some folks get curious about why there was a dip here. This is just because some garbage collector for Java was deprecated. Nothing fundamental here. The point is that the compiler complexity is increasing. In fact, if I was to wager a guess, I would say in the next 10 years, you can just extrapolate this line. And if anything, that line will only become steeper. The only reason this line has a slope is because that's the limits at which humans, the human civilization, can basically push complexity into the compiler, because we actually need much more. And you may wonder that if it's something that's specific to GCC, but that's not true. Here's LLVM. And in case of LLVM, because I understand slightly better, I just took out the code generation or optimization parts of LLVM, and this plot did the same plot. And this LLVM started in 2001, and you can see a similar rate of growth in LLVM as in the optimization part of LLVM as well. So it's really the optimizer that's basically taking most of the time, most of this complexity. So the problem is that even with all this complexity, compilers remain fragile in what they're able to do. And so the question is, what is the solution? And is this even a sustainable solution that 10, 20 years down the line, we just keep going along this curve and we have 30 million lines of code in GCC or something like that? Well, there is one proposal of a solution, which is also called program synthesis and super optimization in the research literature. And here is a way to explain that. So currently, the way we do compilation is we have a program, which is which we can call the problem, and we have a solution, which is the optimized assembly implementation for a given architecture. And this gap between the problem and the solution is currently covered by compiler algorithms carefully developed by expert programmers. And that's all the complexity that I see in the compilers like GCC and LLVM. Now, here's the alternate architecture that's proposed by researchers in program synthesis and super optimization world. And this is similar to the generator kind of philosophy that Professor Nori is being credited with. And so I think that's why I feel this is a very good fit for this talk. So basically, the idea is that you have some set of algorithms which are going to be called the inductive synthesis algorithm, which are going to synthesize potential solutions. And they're going to generate some candidate solution. And then there'll be a validator or a verifier, which we're going to call the equivalence checker. And the validator is going to say yes or no. If the validator says no, then hopefully the validator will generate a counterexample, which can be fed as a feedback loop to the synthesizer. And the synthesizer can hopefully propose better candidates in future. If the equivalence checker says yes, which means the programs were equivalent, you have found a potential solution, and you can do your cost function to figure out whether this solution is the best possible solution that you've found so far or not. And then you basically save these problem solution pairs as a database, and kind of model your compiler as a database of these automatically learned problem solution pairs or optimizations. Now, what are these inductive synthesis algorithms? Well, there's a bunch of literature on what kinds of different inductive synthesis algorithms are there. So the earliest ones were based on enumeration, which was actually Henry Massillon's work in 1987. People have come up with more fancier algorithms like stochastic search, learning from examples, mutation-based learning, constraint solving, neural networks. We heard about a lot of AI for code thing in Neil's talk. And you can plug your favorite fancy technique here. The good thing here is that your fancy technique doesn't need to be really precise. It can do, it can just try some random things, and they just need to be candidates. And the reason this can work is because we are relying on a validator or an equivalence checker. And because all these synthesis strategies are noisy, we need to validate the proposed optimizations. And once again, even the validation job is actually a pretty difficult problem. It's an undecidable problem, theoretically speaking, but you want to do best effort. And in this best effort, the better you can do equivalence checking, the more optimizations you will be able to learn. So the better the equivalence checker, the more powerful your optimizer, or also called a super optimizer. So this whole architecture is also called a super optimizer. Now, how do you make the equivalence checker better? What does an equivalence checker better mean? First of all, the equivalence checker needs to be one-way correct, which means if the equivalence checker says that the two programs are equivalent, then they better be equivalent. There should be a proof that they're equivalent. It should be a sound equivalence checker. Because otherwise, you're basically learning wrong optimization, then the whole compiler is wrong. So it needs to be correct. It needs to be sound, which means if it says yes, then the answer is yes. But if it says no, then maybe, the validator wasn't just able to figure out the equivalence proof. So, and that's what I mean by more powerful. The more powerful equivalence checker will mean that it'll say yes for more and more correct things, and it'll minimize false negatives. False positives are a strict no. False negatives are a minimization goal. So in this approach, we can potentially change the development model of a compiler. So what's the traditional development model of a compiler that we've been living with? An engineer gets an optimization idea, she codes it up, it gets reviewed by a bunch of experts, and most of the optimization ideas are actually getting rejected. So even after all the complexity that you saw in GCC, it's just a small sliver of the work that was actually done, because many optimizations are rejected because people think that, the experts decide that it's too complex compared to the benefit that the optimization entails, or it's too specific to a certain programming language, it kind of spoils the architecture of the entire pipeline, or too specific to a certain architecture, or requires a complete compiler overhaul. The way compilers are architected today are pass by pass, and this has the famous phase ordering problem. And some optimizations just don't fit in this pass by pass structure, or require reordering of the passes and things like that. And all these are big issues, which basically mean that some optimizations just aren't, although important, just cannot fit in the GCC or LLVM compiler development model. So there's too much human effort, and it's being wasted. And even when, let's say, the experts say that, okay, this is a good optimization, let's upstream it into GCC or LLVM, we still have issues because many of these optimizations actually contain bugs, and it's well known. In my other set of slides, we also do look at how many bugs are being filed in GCC and which of these are actually true bugs in GCC. And you would be surprised that on the order of 15 bugs every month are appearing on the optimization logic in these compilers. So, and that's a very scary thought if you use the compiler for some mission critical application like your self-driving car or your fighter jet or something like that. And these bugs are common because the compiler is a very nuanced thing, and you're kind of very corner case conditions like integer overflow, memory overflows, undefined behavior, etc. So this makes the problem interesting, but it's also very, very hard. So what's the new proposed development model in the super optimization world? Well, you have a bunch of developers of inductive synthesis algorithms, and I'm using this kind of facetious picture here just to show that okay, these developers don't need to be super experts. They can just use some neural network or something like that and generate some noisy candidates. But then there's an equivalence checker which will act as a gatekeeper, and most of the things that the inductive synthesis algorithm generate will be rejected, and some of them will be accepted and cached as pattern replacement rules. And so this is the new kind of proposed development model of a compiler based on super optimization, where we use more of machine power and less of human intelligence. So what has been the work in this kind of line of thinking? So as I said, Henry Massillon in his 1987 paper kind of did this idea of enumerative search for identifying optimal code. At that time, he wanted to find the optimal code for a given architecture. So he looked at the Motorola 68020 processor, and he said, okay, let's look at small mathematical functions like the signum function, and say, what's the fastest code that I can generate on the Motorola 68020 processor that computes the signum function? And he basically did a brute force search, and his equivalence checker was basically based on execution of a random input. So it was not a full proof, but with a very high probability that would work, and then he would do a manual check after that. And based on that, he would basically, here's a solution that he came up with, which was this four instruction solution on the Motorola 68020, which is not possible for a compiler to generate because it's a very complicated reasoning that basically goes on into kind of doing this kind of thing. So this was in 1987, and I hate to bring my own PhD work here, but we kind of tried to extend this in my PhD thesis, which was automatic generation of people super optimizers. So idea was, let's try to generalize this approach. He was looking at specific mathematical functions and looking at a certain architecture. How about we just look at peepholes of instructions, any arbitrary instruction sequence, and kind of identify optimized version of that peephole instruction. So this is in traditional compiler literature, this is called peephole optimization. Because we are automatically generating peephole optimizations, we call it peephole super optimization. And the primary contributions there were that we kind of generalized, what could be learned in the sense that we supported arbitrary sequences of arbitrary windows of instructions, which are also called peepholes, supported memory accesses, supported branches to a limited extent, like the example that I'm showing here, supported liveness. So the idea was, so for example, here in this example, you will see that if you have 3 instructions, R1, you move R1 to R2, R3 to R1, and R2 to R3, but only R1 and R3 are live at the end. So you have some context information here. Then you can just replace it with a single instruction called exchange, and exchange R1, R3. And so similarly, use of conditional move instructions, etc. There were other examples that that kind of came out of this architecture, like the use of vector instructions, because we could support memory accesses and we were supporting vector instructions on the x86 architecture. There were these interesting optimizations that came out which were not kind of possible using the compilers of the day. Etc. Okay, so that was, and that's what I mean by using a super optimizer to learn optimizations and then caching them in a database. And this table is kind of a small database of things that we could cache at that time. Now, I also want to point out that we kind of supported because the code, when you scan a window of code, it can have arbitrary constants like 1, 2, 3, or 4, 5, 6. And of course, we don't want to generate peepholes for all possible values of constants. So what we supported was symbolic constants. The idea was that you canonicalize any constant to a symbolic constant called C0, and then you try to learn for an arbitrary C0 what is a people optimization rule. And our optimizer was able to do this. So for example, if you move C0 to EX and then you decrement it, then you can just replace it with a single instruction that says move C0 minus 1 to EX, and that would be cheaper. And similarly, the other one is a constant folding optimization that I showed this on the slide. Now, question is, how did we do the equivalence checking? So because we were doing this for a general setup and not for specific mathematical functions, we couldn't rely on manual scan of thousands or hundreds of thousands of these kind of candidates that are coming out. So we implemented a logical equivalence checker for which basically encoded logically every instruction sequence into a circuit. into a logical circuit, of ands and ors, a Boolean logical circuit, and then we used an off-the-shelf satisfiability solver, whatever was available at that time, to basically say that whether can that satisfiability solver prove that these two are equivalent circuits, or can it disprove that they are equivalent circuits? If it was able to prove that they are equivalent circuits, then we decide that they are equivalent. Otherwise, we have a counterexample. Now, there are many issues with this architecture, and the vision that I painted initially and what I showed you so far is kind of, there's a big mismatch between what has been achieved and what is the dream, because a biggest issue is the loops are not supported. And most consequential optimizations that in a compiler actually loop optimizations, and other optimizations are kind of the fringe optimizations. So unless you support loops in this architecture, you will never be able to meet the dream of replacing a human-coded compiler with a machine-generated compiler. And so loops are not supported, and this is an example of an optimization that will not, be able to reason about in our people of super optimizer, because if you say R equals star P and star P equals R at the beginning and the end of the body of a for loop, and you do loop invariant code motion and bring it up, then our equivalence checker is not able to kind of reason about these kind of things, because we just can only handle acyclic sequences of instructions. Also, aliasing information is not captured in this model when you do equivalence checking, because you have to conservatively assume that everything can alias with everything else. But the compiler really has a lot of information about this being a heap access, points to information, for example, and that being a stack address access and so on. And that information should be made available to a people super optimizer as well to be able to make any. So in our work, we've been working on an equivalence checker over the past 8 to 10 years, which is basically an end-to-end equivalence checker, which means that it takes the source program and it takes the optimized assembly program and checks whether they're equivalent or not. We don't make any assumption of what happened in the middle, because our goal of using this equivalence checker is within a super optimizer architecture where we don't know how the transformation was actually done. It supports loops. It supports all the general programming constructs like aliasing, function calls, etc. Importantly, it should have no false positives, which means if the equivalence checker says that the two programs are equivalent, then you have a proof of equivalence, and they're guaranteed to give identical behavior at runtime. And you want to minimize false negatives so that you learn as many transformations as possible. So that's been the goal of our research over the past 10 plus years. And while I have motivated this whole need for an equivalence checker in the context of a super optimizer, it's actually a well-known traditional problem in the context of a translation validator. So what's a translation validator? Because compilers cannot be trusted and they have lots of bugs, if you want to use a compiler in a mission-critical setting like a fighter jet or something like that, then you need to, you cannot just use a GCC or an LLVM compiler and kind of say that, okay, I'm going to put it in my, whatever jet. So you have to use some tools to, at least in the research community, there's been a lot of push to kind of check whether the compiler is doing the right thing or not. And what a translation validator does is basically it takes the source code, runs it through a compiler, gets the optimized machine code, and then run something like an equivalence checker that I just described to say whether they were actually equivalent or not. And this has been a classic research problem, at least since the 1990s in the research literature. So we are going to, because we don't have access to a super optimizer that can do all these complex things, we are going to test our equivalence checker in this experimental setting, and this very well-established experimental setting of a translation validator. So I'm going to describe how our equivalence checker works and also kind of show you some results on what our equivalence checker is capable of doing. But before I do all that, let me just start with the basics of how equivalence checking even works. So, and I'm going to use this small program to show how equivalence checking works. So let's say I have this program in C on the left, which basically, iterates I from 0 to 1024 and does AI equals BI by 2. And on the right side, we have the optimized code, which presumably is assembly code, but I just abstracted it for simplicity into C-like syntax, where instead of I, we have a register R1, which goes from 0 to 1024. And the only major change here is that instead of divide by 2, I'm doing right shift by 1. I want to prove that these two programs are equivalent. So how am I going to prove that these two programs are equivalent? So firstly, what does equivalence even mean in this setting? The meaning of equivalence is given identical inputs. So let's say there were some arguments to this function. They should be identical, and identical memory states, more precisely heap states as inputs to these two functions. Do these programs produce identical observable behavior, where observable behavior here means identical return values and identical output machine states, or output memory states? Okay, so that's a problem of equivalence checking. And how do you do that? So before I explain how we do that, the first thing I'm going to do is abstract these programs into a common syntax, which is the common control flow graph syntax, which you may have seen in some programming languages or compiler course, where basically use every PC is represented by a node. So for example, C2 is a program counter value that is represented by a node, and every edge here represents a transition of the program. So for example, a transition from C2 to C3 represents the execution of these statements AI equals BI by 2 and I plus plus. And this is called the transfer function of an edge. So an edge in this control flow graph represents the execution of some logic to reach another PC and another node. And moreover, every edge is also labeled by an edge condition, which is the condition under which that edge is taken. So for example, this edge from C3 to C2 is taken only if I was less than 1024 at C3. Right? So this is also called the edge condition. So this is a control flow graph representation of the program. And we kind of abstract both programs, the C program and the assembly program, into their control flow graphs. And the goal is to be able to show equivalence. The goal is to construct a product program that executes both programs in lockstep, such that the two program states always remain related. So what is a product program? A product program is saying, like, okay, you first program execute one step, second program execute two steps, and I'm going to decide what this lockstep is going to be, such that at every point I'm able to reason about, oh, okay, yeah, the states are related in some way. This will become more clear with an example. So let's say I have this, let's say the first program, C program, goes from C0 to C2. Now, the goal of the product program is to figure out what is the corresponding lockstep execution that should happen in the assembly program. And now this is the hard problem, but let's say some oracle tells us that the right correlation is basically A0 to A2, and that's the right lockstep. So if C0 goes from C0 to C2, then A goes from A0 to A2. And so this lockstep execution I'm going to encode using a product program or a product control flow graph, product CFG. And the first node in the product CFG is going to be the start node, which says C0, A0. And this edge from C0, A0 basically says that what happens when program 1 goes from C0 to C2, you want to know what's the corresponding lockstep execution for A0, A2. And as I said, let's say some oracle has told us that the corresponding lockstep is from A0 to A2. And this information is now encoded in this product CFG, and we have a new node called C2, A2, because the C program has moved to C2 and the A program has moved to A2. And I kind of continue this. So let's say, even before I continue, I also want to talk about what do I mean by the states being related. So first of all, at the beginning of the program, at C0, A0, we already know that the arguments must be equal and the heap states or the memory states must be equal, and that can be used as an assumption. But now, because I have been able to do the correlation, based on this, I can infer some information about how the states are related at C2, A2. So for example, I know that for the product program that I've constructed so far, when I'm at C2, A2, I must be 0 and R1 must be 0 as well. Why do I know that? Because, I mean, the only way to reach C2, A2 is by executing C0 to C2 and A0 to A2, and both of them are setting I and R1 respectively to 0. Similarly, I know that heap states are still equal because heap hasn't been modified in the program yet. Now, these relations between the two programs are also called the invariants on the product program, not on the original programs, but on the product program. And this is what I mean when I say the states are related. Now let's move on with the algorithm. So let's say some oracle again tells us then if the first program moves from C2 to C3 to C2, which is one iteration of the C loop, then the second program moves from A2 to A3 to A2, which is one iteration of the assembly loop. And we add these two edges, red and blue, to the product graph. And now we have another correlation that we have kind of identified. But now once we have identified this correlation, the original invariants are no longer valid, because now it's possible for the product program to be at C2, A2, but I is not equal to 0 because it could have taken one iteration and I would have been incremented by 1. Similarly, R1 could have been incremented. So I equals 0, R1 equals 0 is no longer an invariant of the product program. But I equals R1 is still an invariant of the product program, because that's how I chose the correlation such that the program states remain related. And that's what I mean by choosing the lockstep such that the program states remain related. And finally, let's say the oracle tells us that we need to correlate C3 to EC with A3 to EA, and we add this correlation to my product graph. And my final proof is going to be completed if, using the invariants at C2, A2, I'm able to prove that the returned values are also equal, which means the returned values ret C and ret whatever is being returned. In this case, nothing was getting returned, so it's okay. And also the heap states are equal. So for example, AIs and BIs have identical values across the two programs. So this is how an equivalence proof proceeds, and this way of completing an equivalence proof is sound, which means if you are able to complete this proof and show that the return values or whatever other observable behavior are equivalent, then you're sure that at runtime you will always get equivalent values. But the question is, the problem is that these are a hard problem because identifying the correlated transitions and identifying the invariants are both undecidable problems. And so we can only, our goal can only be robustness, which means we want to identify these invariants and correlations for as many cases as possible. But we cannot any time claim that we can do it for all possible transformations, but we want to do it for as many transformations as possible. And that's what I mean by the goal being robustness. So let's see how, and I'm going to show you how we are going to do this, how we're going to achieve this goal, and that's basically what our equivalence checker looks like. So how are we going to do this? So here's the key idea. So far I've been using an oracle, but now let's relax that assumption. I'm not going to use the oracle. And let's say I'm at C2, A2, and I want to correlate this edge, this one iteration of loop from A2 to A3 to A2. I want to figure out what is the right correlation for A2 to A3 to A2. Now I have multiple options. I could either correlate one iteration of C2, C3, C2, or two iterations of C2, C3, C2, or 1.5 iterations, so C2, C3, C2, C3, or something like that, right? So, I mean, there are all these options that are possible when I actually do the correlation. I don't know which one to pick, and that's really the problem. And so far, I was relying on an oracle. The other problem here is, how do I infer the invariants? How do I know that the right invariant is I equals 0, R1 equals 0, or is it I equals R1, or whatever? And here, I'm going to restrict my space of interest to only affine relations. So, all these relations that I've shown you so far are affine relations, which is summation Ci xi equals 0. So, R1 equals I into 1, or R1 equals I into 100 plus 20, or something like that. These are all affine relations, and I'm going to find the best affine relation that I can find using this, and that actually suffices for for a large 99+% of compiler transformations. Okay. The other thing is I'm going to use an SMT solver, a modern incarnation of a satisfiability solver, with higher order theories of bit vectors and arrays to be able to do these inferences automatically, the correlation inferences and the invariant inferences. So how are we going to do this? Well, before I explain the algorithm, I also want to point out that our algorithm is based on counterexamples. So I want to first tell you what are counterexamples. So anytime, let's say you want to, you have some kind of candidate, either guess, based on guess or something. So let's say the candidate across this edge, C2A2 to C2A2, one iteration of the loop in the product program is I equals R1 plus 5. Then I basically formulate this query as an SMT query. So I say, if I equals R1, then is it true that I plus 1 equals R1 plus 1 plus 5, because I and R1 have both been incremented by 1. So this is the query that goes into the SMT solver for all possible input values of I and R1. And the SMT solver returns happily and says, no, this is not true, because here is an example of I and R1 for which this formula will evaluate to false. And this return value, which is in this case I'm showing I equals 100 or R1 equals 100, any other value would have been fine, is called the model in the SMT solver parlance. And in my presentation, I'm calling it the counterexample. So I basically gave a candidate, the SMT solver refuted and gave me a counterexample which refutes that particular candidate that I gave to the SMT solver as a candidate proof query. So I've set enough background. Now I'm going to come to the research contributions of our group. The first research contribution is counterexample guided invariant inference. So the idea is, the problem here is that let's say, the right invariant, so I've changed the example a little bit. Let's say, the compiler has done some kind of loop unrolling, and in the assembly code, R1 is being incremented by 2 and not 1. And now the right invariant to infer at the loop head is I equals 2 into I equals R1 and not I equals R1, just to make the problem slightly more interesting. Question is, how do I infer this automatically? So the idea is that, one approach that was kind of the most predominant approach before our work was that you just guess a lot of different affine invariants. For example, R1 equals 5, 6, 7, 8 into R1. Now, but number of such guesses can be infinite, can be large, not infinite. But and then you try each of them and you give it to the SMT solver, and the SMT solver says yes to any one of them. That's the invariant. But that's not scalable, as I just said. So the idea is we are going to use the execution output or the counterexamples to infer these concrete mappings. So let us say the original invariant that we had was I equals 0, R1 equals 0, as we've been using in the example. And so what we do is we use this as as an execution, and we basically say, okay, let's execute this counterexample on the edge. And now we get a new point, I equals 1, R1 equals 2. Because we have restricted our attention to affine invariance, we try to draw a line between these 2 points that we have, 0, 0 and 1, 2, and say what's the equation of this line. The equation of this line is, in this case, 2 into I equals R1. But I mean, generally things can get more complicated, right? In general, I mean, you basically generate some points like these, for example, 0, 0, 1, 2, 2, 4, and you give it to a linear algebra solver. More precisely, we give it to a bit vector affine algebra solver, because recall that in machines, we don't have infinite integers, we have bounded integers, so we need to use bit vector affine algebra, which is slightly more complicated than linear algebra. Irrespective, it's possible to do this at slightly more cost than what linear algebra solvers will do, but you get this candidate invariant 2 into I equals R1, and then you give it again to a SMT solver. And the SMT solver either refutes again with a new counterexample, in which case you again try to draw a line between these 3 different points that you have, or it says yes, in which case you have found the invariant. So this is our counterexample guided invariant inference that was published in SAT 2018. A second research contribution is counterexample guided correlation, and this is the primary contribution of this work which has made our equivalence checker possible. So what is counterexample guided correlation? Recall that I've already been motivating the problem of correlation, which is if this is one transition of the first program, what is the correlated transition of the second program? And this, the oracle is supposed to tell us, but how am I going to infer this automatically? And recall that the problem is that there are many options here. I've just shown 3, but in reality, there are hundreds of possibilities at every step. And let's say the right choice was the one in the middle, where one iteration of A2 to A2 is correlated with 2 iterations of C2 to C2 to C2, because there's unrolling in the compiler. How do I figure this out automatically? So the idea is, again, we're going to use counterexamples, or you can also call them just examples, and we're going to just use execution output. So let us say all these 3 are candidate product programs. So the first program, candidate product program, correlates 1 iteration of C program with 1 iteration of assembly. The second one correlates 1 iteration of assembly with 2 iterations of C. The third one does something else, right? And then we basically execute the current counterexample. So let's say 0, 0, and we execute it on both of them. And we get something here at C2, A2. And we execute it once more, and we get something more. And then we try to draw a line or a plane through these points that we have got. And let's say based on the lines or points that we have got, we get these candidate invariants, sum equals R2 for the first possibility. Sorry for this overlapping text. But let's say we get sum equals R2. In the second case, let's say I got sum equals R2 and I equals R3. And the third one, we get sum equals R3 based on the candidate on the bit vector affine algebra solver. Now, which of these do you think is the most promising? The answer is it's the middle one that's the most promising, because it has the maximum relation. It preserves the maximum relation between the 2 programs. And that was our original pursuit, that we want to kind of identify lockstep execution such that the states remain related. And the middle one is best because it's relating 2 different variables, whereas the other ones are not so good because they're just relating 1 variable. And this is just a heuristic, but it works very well in practice. And so we're going to rank this higher. And this is a heuristic that basically we call counterexample guided correlation. So this work appeared in UPSA 2020, and if you find it interesting, please look through the paper or our talk videos on our YouTube channel. I'm going to show you how this algorithm works with a more complicated example. So this is an original program taken from the test suite of vectorizing compilers, the standard benchmark for very complicated transformations that compilers perform. And in this example, there is this variable called sum, which has been initialized to 0. And you have some constant called len, and you initialize mid to len by 2. So in this case, let's say 500. And then you go from I to equals 0 to len, and then you have some code. And the code is if I is less than mid, then sum plus equals CAI. So it's a double dereference. And if I is greater than equal to mid, then sum plus equals BI. So it's single dereference. Now, if you give it to an optimizing compiler, doesn't matter which one you give it to, they all do the same thing today. Some mature compiler, like either GCC, LLVM, or Intel C compiler, which by the way is largely based on LLVM today. What they do is the following. They first do loop splitting. So the compiler basically splits the loop from 0 to len into 2 loops. The first loop goes from 0 to mid, and the second loop goes from mid to len. And the bodies remain preserved as it is. So this transformation is called loop splitting. The second thing they do is that they do what, they identify that because the first loop is going from 0 to mid, I is less than mid is always true, and I is greater than mid, equal to mid is always false. So they just kind of simplify this whole thing into just the body of the second if. Similarly, in the second loop, they just use the body of the second if, and the first one it was using the body of the first if. And so this transformation is called loop unswitching. The third thing they do is, because the second loop is very regular in its access pattern, they unroll the loop, and this is called loop unrolling, and they only unroll the second loop but not the first loop. And then they do vectorization. The unroll loop gets used, they use some kind of vector instruction to implement the unroll loop in a single instruction, and so on. And this becomes really, really fast, much faster than the unoptimized code, significantly faster, maybe even like 4 to 5x faster than, depending on whether it's 64-bit or 32-bit. Now, to our equivalence checker, we don't really assume knowledge about what were the exact transformations. We only have the original program and the fully vectorized and register allocated program. And I haven't even shown all the transformations that happen. I mean, just some of the major ones. And it's supposed to figure out what is the equivalence proof automatically. And the good news is that it is able to do this in a reasonable amount of time, on the order of a few minutes. And in this case, I'm also showing the product CFG that comes out of the equivalence checker at the very bottom. If you look at the product CFG, it says you start from C0, A0, which is the start of the program. And if the assembly program takes A0 to A2, then the C program takes C0 to C3. If the assembly program takes one iteration of the first loop, then the C program also takes one iteration of the loop, the only loop. If the assembly program goes from the first loop to the second loop, the C program takes yet another iteration of the same loop. If the assembly program takes one iteration of the second loop, then the C program takes 4 iterations of the second of the only loop. So this is the kind of correlations that the product CFG, or the lockstep correlation that the product CFG required for the proof to go through, and the equivalence checker is able to do this automatically based on the heuristic that I just described. And finally, if the assembly program exits to the EA node, then the C program exits only after executing 4 more iterations of the loop. So this is a pretty complicated, and we can do much more complicated product graphs. I'm just using this as an example. Our tool can handle product graphs of 50 plus nodes and 100 plus edges and things like that, and fully automatically. And the question is, how does it do it? And basically, we construct the product CFG incrementally. We start with C0, A0, and then we say, okay, what is the correct correlation for A0, A2? And we use that correlation, counterexample guided correlation heuristic to identify the best answer. And it works. And so because of that, we basically get this best candidate C0, C3. And we add this node called C3, A2, and we use an off-the-shelf invariant inference algorithm to infer affine, equality, and inequality invariance. For affine, I've already shown you the algorithm that we use, which is our own algorithm. But for equality and inequality, we just use off-the-shelf invariant inference for bit vectors and memory access, and to infer the invariance at C2, E3. Similarly, the algorithm proceeds forward, so it tries to identify correlation for one iteration of the assembly loop. In this case, it identifies it to be C3, C4, C3. Continues, infers invariance at the new nodes that are being added, relaxes invariance when new edges are added on the same node. And finally, when the exit node correlations have been decided, we check whether the equivalence of return values and inferred invariance can be proven against under the currently inferred invariance. This whole procedure is basically implemented as a best first search. So if you look at the search space, A0 to A2 could be correlated with C0, C2, C5, or C0, C2, C5, C7, or C0, C2, and so on. And if I pick any one of them, then you have more options, so on. And as I said, the fan out can be on the order of 100. I'm just showing 3 here. And an exhaustive search would just take millions of years to compute equivalence, even for small examples. But as I just said, our equivalence checker is able to do this in a few minutes for even large examples. So, and the trick is basically the algorithm that I showed you earlier. So, and prior work on data-driven correlation would completely fail on these kind of examples that I'm showing you. So, how do we do this? During invariant inference, we make potential guesses for invariance. We try and guess using an SMT solver. If the guess is provable, we have found an invariant. If not, the SMT returns a counterexample. And that counterexample we use as an example to basically execute forward and identify best correlations. So this is basically the basic idea. A counterexample at a node is a potential concrete machine state that may occur at that particular node during execution. And this is important. So we are not actually relying on execution traces supplied by the user or something like that. We just use the SMT solver to generate these execution traces on demand and only for the local pieces that we need. And the concrete state would involve valuations for related variables for both C and A. And the key ideas here are, so we model this as a best first search over this huge search space. And the key idea is counterexample based pruning. So based on these counterexamples, we say that, okay, these are definitely not candidates, promising candidates. And we just remove some of these, prune out some of the search space. And the other is counterexample guided ranking. We rank some candidates higher than others. So once again, how does this work? Let's say you have two candidates, you infer the invariants for both of the candidates. Let's say these are the invariants that you got. The more promising one is the higher, the one on the top, because it has more relations, it has more equality relations between the two. And so this is ranked higher. And more precisely, we rank based on number of live assembly values correlated to the inferred invariants. In our experiments, we have taken unoptimized LLVM IR of C programs, which is pretty much the original syntax of the C programs. Run it through, and also you take the C program and run it through an optimizing compiler. And we use 3 different compilers because we don't need to know what's inside a compiler. We can use any compiler. So we look at GCC, LLVM, Clang LLVM, and ICC, which is the Intel C compiler. It's a closed source compiler. And we get some optimized x86 code. And then we use our equivalence checker to check whether we can generate a proof that shows that the 2 programs are equivalent using the algorithm that I just described. We evaluated this on programs taken from the test suite of vectorizing compilers, which involve a lot of vectorization. The example that I showed you earlier is actually an example taken from the test suite of vectorizing compilers, and the more complicated examples there. And the good news is that we are able to do more than 90% of these programs completely automatically in a matter of few minutes. Now, this is a significant improvement over anything that existed previously in this space. And this is one of the reasons we are basically, our equivalence checker, we consider it as a practically usable tool. And this is what we are actually, taking to defense and aerospace sector industries to check the equivalence, the correctness of the compilations for mission critical software that goes into fighter jets or aeroplanes and things like that. And that is primarily the basis of the commercial startup entity that we are also pursuing. We have discovered, based on our experiments, we have discovered multiple bugs over the years, and these are just some of the bugs. The bugs that we have discovered have been in compilers, some of them previously unknown, in libraries. Because it's just an equivalence checker, we can also take 2 different library implementations of C libraries and just say, that, can you show that the strlen function is equivalent of both these? And we have found bugs in heavily used libraries like OpenBSD library or embedded C system libraries, etc. And these bugs, ICC, GCC, we have found a bug in the QEMU machine emulator, which is a binary translator. And sometimes they also tip us with bitcoins when we give them these bugs because as a thank you token. These bugs are, I want to point out, very subtle bugs that are, in my opinion, not possible to catch using static analysis tools or anything like that, because these are bugs that kind of occur in very corner case situations that you wouldn't have even thought about. And the reason we are able to catch these bugs is because we are not trying to find bugs. We are trying to find proofs. And when we try to find proofs and the proof doesn't go through, then we try to investigate why the proof hasn't gone through. And when we try to investigate that, either we find that our tool has some deficiency, or we find, hey, there was a bug here, and which is a eureka moment for us. So this is what happens. And so these bugs are really subtle. Just want to point that out. I want to open it up for questions. I don't want to keep speaking, but I just want to say that this work also has more applications, and we have basically been able to use the equivalence checker to also do automatic generation of debugging headers. The problem is that debugging headers are often incomplete. So, when you run an optimized program, you want to try and investigate the value of a particular variable. It says the value has been optimized out. And this is a big pain point for developers. The reason this situation exists is because developers deprioritize the maintenance of debugging headers. As I just showed you, compilers are already so complex with tens of millions of lines of code. Compiler developers are prioritizing addition of more optimizations, and they are deprioritizing the maintenance of debugging headers. They say this is, I have more work to do, and this is not something that I'm going to invest my time on. Because of that, there's a lot of pain to the developer who is using the optimizing compiler. What is the solution that I have? Basically, the solution is that we use the equivalence checker to automatically identify the correlations and the invariants. And using these invariants and correlations, we populate the debugging headers automatically. And so this paper is called Automatic Generation of Debug Headers Through Black Box Equivalence Checking. And this appeared in CGO 2022 this year. Please look at it if you find it interesting. I'm going to skip this. I just want to show the results on the debugging headers. So using our tool to automatically fill debugging headers for the test suite of vectorizing compilers. So these compilers actually leave, 73% of the debugging headers are missing or incomplete or incorrect in Clang, GCC, and GCC, 73 to 75. In Intel C compiler, only 12% were incorrect. And our tool was able to fill up all these debugging headers automatically based on the proofs that were generated using our equivalence checker. So this is, it's also interesting to see that the Intel C compiler has better debugging headers, perhaps because they're a commercial tool and they actually pay attention to the debugging headers and prioritize it for their customers. So this work appeared in CGO 2022, as I just said. So I'll conclude, and compiler development is hard, but increasingly important. Super optimization, I believe, is a plausible solution, and I hope I have convinced you a little bit. Equivalence checking is an important prerequisite to super optimization. And our work has been investigating scalable algorithms for equivalence checking, and I would like to believe they are possible. And in fact, if you are interested, I can also do demos, on our equivalence checker. I have it on my laptop, not on the talk, but separately. And equivalence checking also has other applications like automatic generation of debugging headers, checking of C libraries across multiple implementations, and so on. This is a startup company that we are doing based on the work that I just presented. Thank you.
Yeah, hi. So if a programmer specified an invariant, actual one in the code, then could you do a much better job of optimization?
Yes, sure. If the programmer specifies an invariant that a compiler can read, then the compiler can do a better job at optimization, assuming the compiler believes the programmer. The other option is, and a compiler doesn't really want to believe the programmer because programmers make mistakes, and compilers usually don't want to believe programmers. So the other option is the programmer provides an invariant, and the compiler checks whether the invariant is correct, and if it succeeds, then it optimizes. And that's a possibility, and just that we have to train the programmers to write invariants, and I don't think we are there yet. And I personally think that we have to make programming simpler. We have to move in the direction of making programming simpler than kind of putting more load on the programmer. Already, it's a mess. So putting more expectation on the programmer is actually not the right direction, in my humble opinion.
No, that part I agree. The reason I asked is because in principle, you could then just specify the invariants and generate the code. Why bother? So is that simpler than writing the code?
It is simpler, but it has less, it has less applicability because nobody's writing invariants. So.
No, I'm saying if you don't have to write code and just write invariants.
Oh, okay. Are you saying from a super optimization angle that you just write the invariants and we generate the code for you? Sure. So the specification can be in any type. So in fact, if the compilers become smarter, compilers are already very smart, okay, to give credit to all the decades of work that happened, but they are still way behind what's actually possible, at least theoretically. Because theoretically, you should be able to just say, as we've been talking, and as Professor Nori used to say, that just say specification, and you could say that as a whole triple, and the code should just come out, and a compiler should ideally do that. And yeah, it just needs more work in the compiler space. Question?
Sort of excellent talk.
Thank you.
As far as I understand, so far what you talked about would still go under static compile time optimization. Okay. The other aspect is dynamic optimization in the sense that it would learn from previous runs of the program and things like that. Extending that concept, do you see any application of AI? I see AI in the name of the...
Sorry.
Okay.
Yeah.
Anyway, that's my question.
Yes. So the question is that, so far I've talked about static compilation and static optimization. But what about dynamic compilation and dynamic optimization? And based on the traces that you obtain at runtime, can you use AI to, make that better? Now, yeah, sure. I mean, first of all, yes, I mean, dynamic compilation is an important problem and dynamic optimization is an important problem. It was a very hot area, at least in the late 90s and early 2000s. The reason it has not kind of really taken on in the way that it was envisioned that it would take on, and we still have many more years of computer science research, so maybe it will come back again. But I think it's just because of the complexity of dynamic compilation and dynamic optimization. And already, the same machinery needs to go into whether it's a dynamic compilation or whether it's a static compilation, the same kind of logic and the kind of things need to go. And it's already so complicated that, people have just prioritized static compilation over dynamic compilation. So I just wanted to put that out. Surely dynamic compilation has its huge merits compared to static compilation. Now, I'll come to your question of whether AI is beneficial there. Certainly, I mean, see, I usually look at AI as a very broad term. So, I mean, to me, AI is basically any hard problem for which we don't have precise answers. We basically identify the correct heuristics or the correct kind of learning mechanisms to identify what the right answer is, or go as close as possible to the right answer. Now, we call our startup compiler AI, and this is the most common question I get: what is AI here, and why you call yourself AI? And my answer is, hey, I mean, why is it not AI? I mean, we are doing counterexample guided pruning and ranking, which is, we are doing best first search, which, by the way, I first studied in an AI textbook. I'm just not using neural networks. That doesn't mean I'm not AI. So AI is a very broad term, and it's basically, to my, the definition is, it's a very, very hard problem. It's an undecidable problem. It's an NP-hard problem. You don't have a handle on it. You kind of do best effort, and you use some heuristics, and that's, to me, is AI. Now, AI, of course, in natural language and such things. So certainly, I mean, even in dynamic optimization, already people are doing a lot of heuristics and a lot of data-guided things. I mean, branch prediction is, to me, branch prediction is a canonical example of something which is learning-based. You learn what happened previously to basically predict what's going to happen in the future, and based on that, you generate your code. So AI was already present in compilers, I think, and the more of it can be present in future. So whether neural networks is the right abstraction or not, I don't, hard for me to make a guess. A lot of work is happening, a lot of papers are getting published on using neural networks, but I hope they are approaching it from a problem standpoint, not from a solution standpoint. Yeah.
Hi, Saurabh. Thanks for a great talk. Having worked almost 14 years in compilers and all, I always used to wonder, in fact, this particular kind of challenge that, yes, I mean, what he was saying about the assert statement and all this thing, that if the people are using this they are using this particular invariant stating invariance in the program. That is one of the thing. But another problem that we used to come across actually for, as you were talking about the aerospace industry and all, because I was involved in ADA compiler. So that there in fact our test suite given by the maybe that committee used to always be great, and we used to spend a lot of time, but still we used to find a bug sometime after maybe 6 months or something like that. So this particular checking of this equivalence, I mean, we used to spend a lot of time testing. Actually ours was a compiler and bootstrap compiler. Even the compiler was written in ADA. Still there were bugs. There used to be a bug. Now this testing of this particular thing used to take 6 months almost. So how much time this equivalency testing takes actually?
Yes, if I understand the question correctly, the question is that compiler testing used to take 6 months, and still there used to be bugs that used to escape. So how much time does the equivalence checker take? Is that correct? Okay. So yes, I mean, the equivalence checker, when it works,
finishes in a few minutes time. For large programs like, thousands of lines of code, it can take few hours. And the problem is that, it may not work all the time, but it works for a large set of transformations. So, I mean, given that we are trying to commercialize it, it's definitely practical to be used for a large set of optimizations. In fact, from what I found, based on our initial explorations of the commercial venture, many people are actually just disabling optimizations just to make sure that they get rid of, they don't introduce bugs. So if there's a mission critical system, they'll just kind of disable optimizations and then ship it, which is a very bad solution. And for those kind of things, our equivalence checker will just work in minutes because the transformations that are happening are very small or non-existent, or the optimizations that are happening are very small. So yeah, this is definitely an automatic solution. So it definitely, it's on the order of hours or minutes and not on the order of months or years. Okay, so that's not the question, sorry.
So the question is correct, actually, you have interpreted, maybe I have not stated it properly. So testing of this particular equivalence checker itself, if you have written, let's say, how much time it...
Okay, wonderful. So the question is, what about the testing of the equivalence checker itself? Is that the question? Okay, terrific question. So what about, why should I trust the equivalence checker? The equivalence checker says that the codes are equivalent. How do I know the equivalence checker is correct? It's a great question. So the answer is, when you say something is verified, then how do you know that the verifier is correct, right? So the answer is that you basically say what's the size or the complexity of the tool that you suspect. So in the case of a GCC or LLVM compiler, this is called the trusted computing base of that software. The trusted computing base, or TCB, of GCC or LLVM is on the order of millions of lines of code. Whereas the TCB of our equivalence checker is just on the order of, let's say, 10,000 or 20,000 lines of code. Because I want to point out that even all the best first search and the counterexample guided pruning, all that logic is outside the TCB. The only trusted computing base of our equivalence checker is the logic that actually checks that the invariants are inductive and that the entire correlation space has been correctly done. And that's a small piece of code. Now, it can have bugs, in which case our equivalence checker would be bad. But of course, we have been testing it over lots and lots of different examples over the past, at least 6+ years, etc. And so that's what we rely on. So the value add that an equivalence checker adds is basically that it's a much smaller trusted computing base, orders of magnitude smaller, heavily tested, and the probability actually that there will be a bug in the equivalence checker such that an incorrect code will escape is very, very small. So that's what, that's the argument. Actually, that's the argument in every verification effort.
So overall, basically, if you look at the large code that is there, generally aerospace industry, there's a huge amount of code. You have taken a simple example maybe, but for the large code, equivalence checker will run for hours, that's fine. But how much is the guarantee that I will get a good suggestions of, has it been tried? Some experiments have been tried. So what are the chances of getting a good amount of suggestions to improvise or optimize the code?
Or suggestions for optimizing the code from the equivalence checker? So first of all, I want to say that the results that I showed you are on small snippets, and we have been working on making the improvement, make it more scalable and so on, and we have made significant progress. So we can handle like hundreds of lines of code easily, and and there's still scope for improvement, and we are going with that. Now the other question is, can the equivalence checker make suggestions for performance improvements? So that's an application of the equivalence checker, and we have found instances where we manually identify, because the equivalence proof said something, we can identify optimization opportunities based on that. But that's something that we haven't really spent too much effort on yet. But I definitely think that this is a very fertile line of investigation once we are fully done with the equivalence checker. Thanks.
One small progress along the lines of asking, programmers to do better, so to speak, is the Rust programming language, right? It eliminates a bunch of standard bugs. Do you think that simplifies the life of?
Yeah, so the Rust language actually requires, basically, especially for memory ownership, it basically allows programmers to specify richer type system and richer types, and that kind of enables compiler to do more optimization, also enables safer code. And it's being touted as one of the competitors to C because it's both safe and performant. What is my opinion on that? I haven't done much of Rust programming, but I have read about it, and I have tried to form an opinion about whether this is going to be succeed or not. once again, and this is completely opinionated answer because it's just, so I feel like once again, I'm not in the favor of asking programmers to do more work. I think, the compilers ought to be doing more work and not the programmer. And Rust is working counter to that argument. So I personally don't think that maybe that's the right way.
So few years back, I mean, there is also a lot of research been happening in the area of abstract interpretation, which is also AI, but it's not the one that we are talking here. And that was more tied up with denotational and axiomatic semantics, right? So the problem that typically, I mean, when we say about compiler construction, it's all about operational semantics. This problem of equivalence checker is falling in the era of, or other area of denotational. So have you tried anything on abstract interpretation to get this problem?
So if I understand the question correctly, equivalence checker is more denotational semantics and abstract interpretation is more operational semantics.
No. So abstract interpretation is typically about, it deals with majorly denotational and axiomatic.
Right.
Right, to get more of an abstract solution because of the halting problem and there are things. So this equivalence checker looks to be a more program analysis kind of a way. While
Which internally uses abstract interpretation, right?
Correct,
I mean,
correct.
So for invariance, for example, it's basically abstract interpretation. We do a lot of analysis like the points to analysis and the liveness analysis. I mean, all those are basically, you can call them data flow analysis or you can call them abstract interpretation. We don't use very complicated domains right now for abstract interpretation, but I mean the basic, and invariant inference is a great example of that kind of thing, right? So.
Okay.
Yes.
Hello. So you mentioned about the time it takes, right? I mean, some hours, few minutes and hours. And I was just thinking, I mean, the complexity of the programs, size of the programs or complexity in terms of nested loops or recursion or whatever, that has some impact on potentially the equivalence checker.
Sorry, I missed that.
That could have some potential impact on the equivalence checker, the time it takes, basically. So, I mean, in your observations, have you come across a situation where the answer is not just yes or no, but cannot decide? So, and so what happens in such situations or in such cases?
Cannot decide the equivalence, that's what?
Yeah.
Oh yes, so I want to just say that the equivalence checker has only two answers. Yes or sorry. Sorry means I couldn't decide. It doesn't say no. So, but we have a follow-up work to this, which is equivalence and inequivalence checker, and we run both of them in collaboration. What I presented today is only the equivalence checker. But what we do is we run the equivalence checker till a certain timeout. If it fails, if it succeeds, we are done. If it fails, we run the inequivalence checker, which tries to find a distinguishing input. We also run that till a certain timeout, which is on the order of hours. We usually use 5 hours. And if the inequivalence checker also fails, then we say, sorry, I couldn't decide, right? So that's, but what I described today is basically yes or couldn't decide, basically. Okay, looks like done.
So any of you who want to speak to Saurav, you can do so during the lunch. It will be here around the summer time. Thank you once again for such a great talk.
Thank you. Thank you so much for having me. It's a privilege.
So now while the processors are like getting very fast, the compilers are like not.
You can come here.
Compilers are more like tortoise and the architectures are speeding up like the hair that Saurav had shown. If you guys don't act like hares right now, you will miss your lunch. So now is the time for lunch. Quickly get up and have your lunch. But
Yeah.
before that, there is one more.
Before lunch, no, we will go for group photo. So this is very beautiful occasion. So I request everybody to gather at stage, and I request volunteers to arrange for it. Please join for photograph.
Hello. Check. Hello. Check this. Mic check. Hello. Hello.
It's office laptop. Maybe we just let it come to the mic.
Let's try it out. Don't mind.
Check this.
Hello.
Hi. So we will be starting a panel discussion now, and we invite panel moderator Suhas Joshi and panel members Vivek Kulkarni, Vinay Kulkarni, and Dr. Uday Khedkar. Please come on the stage. Let me introduce Suhas Joshi and Vivek Kulkarni. Others too, Ravindra Mehta will introduce. So Suhas Joshi is has also worked with Kesav V. Nori in 1986, almost 1985 till many years, and he has been working earlier with on compilers, and then after that many other things. Now he is a part of Harbinger Systems. He is guiding the team and driving multiple things, including some part of the AI. But programming language has been definitely his passion. Vivek Kulkarni is now with HP. He was with Persistent earlier, and I have met him in one of the talk where he was talking about a Turing machine, and how this Turing machine works, etc. And I was really impressed, in fact, because many of us study such things in colleges and then forget actually. So this was just few years back actually at Persistent Devang Mehta, and thanks actually. It was a good talk, and overall. Vivek Kulkarni has also worked on compiler, and he was taught, he attended one of the workshops of Keshav Nori also, Professor K.V. Nori, and he was quite impressed actually, and he had a good alignment with his views also. So he has written a compiler when he was with Tech Mahindra, and one of the interesting part is that he has actually proven that compiler is correct. So that's a very interesting part, actually proving the compiler is correct. That's one of the things that he has contributed in that particular area. So thanks to both of them. Ravi.
So firstly, I warmly welcome all the panel. I would like to say a few words about first Professor Uday Khedkar. As some of you might know, Professor Uday Khedkar was a professor here at Pune University Computer Science Department many years back. Ever since he has been working at IIT Bombay in the Computer Science Department. He's an expert on all things related to program analysis. He had mentored so many PhD students, master students. In my office, some of us collaborate with him, work with him. We attended some of his sessions on program analysis. So I very warmly welcome such a distinguished guest among us. Next, Vinay Kulkarni. Vinay is one of the persons in TRDC who worked with Nori Saab from the very beginning. Earlier today, this concept of generators had been talked about at water level. Generator for a generator, for a generator, for a generator, and so on. So Vinay has been the pioneer of those kind of ideas and implementations. He very successfully built and researched ideas related to that, tools which are being used widely in the industry today. He has authored many research papers. And currently he is the distinguished chief scientist of TCS. Recently, some of the work he and his colleagues have done that was also used for predicting COVID spread in Pune and all this. So, and all this through just modeling using that meta-modeling kind of formalisms. So, I'm looking forward to a very exciting discussion from all the panel members. Over to the panel. Suhas, over to you.
Thank you, Vivek and Ravi.
I forgot one. I'm supposed to hand it over to you. Can you display the slide? So, welcome. And on each of your name, one thing would be planted with your name next to you. The initiative from ACM India, and the details are over there on the slide. Finally, 4 people.
Yeah, thanks, Ravi. Welcome all. We started the day with the latest in terms of grammars to AI, and we had a lot of discussion on AI and how it can be used. We also heard from Saurav about compilers, and so essentially language translation technology and how that has evolved and what is the new thing there. Now in this panel discussion, we are trying to actually go through the journey from then to now and try to understand aspects in the context in which the evolution has happened. So for example, we have seen right from mainframes and workstations to the newer cloud-based services, cloud-based deployment. That is one evolution. We have seen methodology evolution. We have seen languages coming and getting adopted. So at different points of time, we would see applications developed in different languages. So all of that evolution, how does it affect the programming community and what programming community needs to do. And I'm happy to have Vivek, Uday, and Vinay as my panel members, because they will really walk us through multiple dimensions of this evolution. And I'm going to try and see how I can bring in external drivers at different points of time to see what was the evolution at that time and why it happened, how it happened, and what were the consequences, which will actually help us relate to different points of view. So rather than going historically like this was in 1990s, what I thought is, because they have different backgrounds, as Ravi said, Vinay has done a lot of work in tools and technologies. Professor Uday has been in compiler. He has a book written on data flow. So he would have a compiler's perspective also on programming, and of course the tools of the programming, which includes languages as the starting point. And Vivek's experience in the industry, he would have also seen some of the things that the programmer does and how their challenges have evolved. So I would like them to sort of first draw their canvas picture in this discussion, and then we'll take cues from there and dig deeper into some of those stages in evolution. So Vivek, if you...
I hope I'm audible. Great. So I mean, when the topic was given to us, I always thought of three things. I mean, that's what we had initial discussion on. One is the evolution on the programming languages per se, how the languages evolved. The second is more about the allied, which is programming paradigms, how they changed over the period. The second or third, probably I would say, is more about environment evolution, or rather the ecosystem, the whole programming ecosystem, how it has been changed from mainframes to now cloud is what he said. And the fourth, which is important as well, is about the process, overall processes that have been followed, how they are changed over the years, right? So just to, probably I'll not go deeper into that because that's what I think the panel discussion is all about. Programming languages, I mean, typically we started with Fortran, right? Probably Fortran, COBOL, and then the recent ones that people are discussing, Rust and Go and other languages. But essentially, what we have seen in the paradigm shift is we were closer to machines, and of course, we are software developers. We are there to actually build more abstractions. Essentially, that's what mean we are taking people away from the core machines or the bare machines. Now with that, what is the loss or what is the gain is what probably we'll continue discussing that. Programming paradigms, I think there is a lot of shift from imperative procedural block structured, pure block structured, impure block structured. People keep talking about, right? People used to compare C versus Pascal. What is the difference? Pascal has around 63 dialects, right? And then suddenly I think people eventually come up with languages like Python, which is completely a Swiss knife, right? It's like a multi-paradigm language. But if you look to the reality, I think we have moved from imperative procedural, then object-oriented was so glorified in between. Now it has lost its heat, and now suddenly we are back to just writing some orchestration using some bunch of APIs and libraries, right? That's where we are. So are we going back in circle is the question. Probably we'll discuss debate more. Process front, I would say we were like started following Microsoft project, right? Typically that time we have MPPs and we always were thinking more waterfall. Now people have moved from bigger teams to smaller self-managing teams, scale agile, that's what philosophy is. I mean, there are more things which probably we shouldn't be doing, but people are still sticking to those as well. We will discuss more in detail as well. Ecosystem wise, I would say, typically, I mean, when we go back, per language typically has to have their own IDE, which is stick to it. There are a lot less support in terms of communities. There were more proprietary tools, languages, more licensing versus open source, right? Nowadays, I think That time, I think we didn't have Stack Overflow. Now I think we have everything which is open out there. So we are moving from proprietary to open source. That is a bigger shift, right? And every knowledge is out there now. So that is a big shift. We have seen days when we actually used to wait for getting the time of the machine on which we can code. So we used to code more on paper, rather now we look at that the clusters are actually unused or underutilized, right? And I have seen even the research organizations within India, because I did lot more collaborations. I've seen that even the clusters are closed at 5 o'clock. So they work 9 to 5. So the bigger clusters have been actually switched off at 5. So this is a story. I think these are the 4 angles I want to discuss more on. Maybe Uday can add more pointers, of course.
Thanks a lot, Vivek. So I am going to take a slightly different viewpoint, slightly abstract viewpoint of the evolution, rather than talking about specific things that happened. I would like to abstractly look at what happened and why it happened. So I see a certain trend. I see that there have been several developments in programming languages and programming which have excited me. And then there have been developments that have pained me. So I have seen both. I've seen things that I feel are great, and I've seen things that I feel are really not great, but they are there. So I was trying to just summarize when the idea of this panel discussion came up. I was trying to look at how can I summarize where we are today when we look at where we started from. So we started from somewhere, we are here, and what has happened along the way. So that's what I'm trying to summarize. So, in the earliest days, and no need to talk about the earliest days when we did machine programming, but even if we start talking about programming in conventional high-level languages, such as C, Pascal. So when I was a student, I read a very interesting book by Nicholas Wirth called Algorithms plus Data Structures is equal to Programs. So we can take that as a starting point, as a definition of what programming is. You're supposed to write some algorithms, you're supposed to write some data structures, and when you make them talk to each other, when you make them interact with each other well enough, you have a program. That the same thing remains even now, but the way we specify algorithms, the way we specify data structures, that has changed significantly. And in my opinion, the changes have been in the 4 different directions: changes in the way we write algorithms, changes in the way we specify data structures, changes in the way the combination of algorithms and data structures work with each other, and changes in the way all this is executed on the machine. So I'll take one by one. So when we begin with data structures, in the earliest days when people wrote machine programming, or even when Fortran came, Fortran didn't have any data structures other than arrays, for example. Okay, so everything had to be simulated within the program. But then other languages came, Pascal, C, where we had data structures, records, etc. After that, so at that point of time, people would encode data structures within the core programming language, as part of the programming language. But then there was a trend that started coming in, which is to delegate the responsibilities to libraries. So soon, instead of coding data structures in high-level languages, we had libraries to support data structures. I mean, C++ STL is the most glorious and most successful example of how libraries can support creation of good data structures. So which means that the specifications, so when we talk about algorithms plus data structures is equal to programs, the specifications of interesting data structures got out of the core language. The compiler is not aware of the library in terms of the semantics of the library calls on the program. It goes out of the program. It's an external service. Now this also happened in terms of algorithms, and we also started getting library packages which will give us algorithmic computations, not just libraries. And we see that in Python. What is Python? Python is just a collection of algorithms and libraries, and all you do is you delegate the responsibilities to certain packages, and all you do is orchestrate things. So this is a trend that has been happening, I see, of delegation. The other development in terms of library and algorithms delegation at the language level, not at the library level, that happened was the advent of object-oriented programming, where data structures and algorithms could be tied together. I could say that this data structure and this algorithm is a part of each other. You know, this algorithm, this method, this procedure can't be used outside of this data structure. So abstract data types, etc. So those are the things that came in. So I see more and more task of delegation. This in some sense is good. This in some sense is also bad. It's bad because the core program that we write is nothing but an orchestration of delegation. If I were to ask, can I verify this program? Can I reason about the properties of these programs? Can the compiler do something about this program? The answer is no, because compiler doesn't know anything. Maybe the libraries have been compiled by the compiler separately, maybe the program is compiled separately, but how do they talk to each other? What effect do they have on the computation? That is somewhere lost. So as a person with gray hair, what I miss is, what is happening is, the choreography of concepts that would happen in the programs is missing. There's no choreography. There is just orchestration. There's just orchestration and there's just delegation. So this is one part. I'm pained to see the kind of Python programs that students write. They work, right? But why they work? What are the interesting properties? Can we guarantee that they work this way? Can we talk about the resources that they take? Do we really understand the program? That part is something that I don't understand. And these days, you know, I mean, and this delegation is what has made, in some sense, AI revolution possible. Lots of people write AI programs, they just use R or they just use Python libraries without really understanding the programming, the way choreography of concepts happens. That's one part of it. Coming to the last part of it, where I said the way the resources get used. So earlier you would have a compiler on your machine, you will compile it, run it. We had interpreters on our machines, and now interpreters have become more and more glorious, and we have virtual machines. The virtual machines, we have high-level virtual machines with high-level languages, and we can run programs on virtual machines. And the delegation of execution from the hardware has gone to software. The execution is delegated to software. Going beyond that, now we have delegation executed to software on the cloud. It's not even on their machine. You have a virtual machine sitting on the cloud. Okay? You use APIs, you use libraries which are on the cloud. You make Google API call. And we don't know what's happening behind Google APIs. We know something, but we don't know everything. For example, if I call a Google API, do I know how much of data is being stored by Google on their servers out of my program? I have no idea. So these are the kind of things that are happening. So in a nutshell, programming these days has reduced to orchestration of delegation to various entities. That is my take. And I think that's where I would stop here.
Yeah, thanks, Uday. I will take a view which I can take purely because of the exposure that I have got to programming. Since I come from an applied research center, most of my work has been about trying to help enterprises address their information processing needs faster, better, and cheaper. So that's the only lens that I have, and from that let me chart out the evolution which I have seen and the problems which are there in the future. Bear with me, I might not be as brief as these two guys. So basically, as I understand, programming is all about managing the complexities, and there are two complexities: accidental complexity and intrinsic complexity. Accidental complexity is because you have chosen to use a particular execution platform, a particular programming language, a particular architecture, etc., etc. Intrinsic complexity is the complexity associated with the task that you want to perform. To begin with, programmers dealt with both the complexities themselves, or they had to deal with both the complexities themselves. Like when they were programming in machine languages, they needed to know what needs to be done. They also needed to know how it needs to be, how it is going to be executed. And that's how they programmed. So it was a highly complex task in those days. Then we saw with the advent of general purpose programming languages, some part of the accidental complexity got removed. Compilers took over that complexity. But in the overall space, writing a compiler now became a new accidental complexity which someone had to dealt with. And as Saurav said in the morning, you really needed good programmers who will come up with good compilers, for example. But now the focus of a developer was reasonably reduced. They just now need to deal with expressing their understanding using the abstractions that are being provided by the general purpose programming language. Unfortunately, general purpose programming languages provided abstractions that were execution centric, not necessarily problem centric. So this impedance mismatch between what and how is what the programmer had to deal with almost always. And it was not too much of a problem as long as you were developing one program that was to be executed on one machine. With the advent of distributed architectures, now you had to deal with minimum 4 different kinds of execution environments: the database, the server, the graphical user interface, and the middleware which is connecting things between them. And each of these execution environment had their own intrinsic and accidental complexity, which needed to be dealt with. None of the general purpose programming language really address this issue. It was the right time when the book on design patterns came. It tried to address this very issue, but it stopped at saying what it needs to be done. Finally, the design patterns still needed to be implemented by the programmer in each of these different patterns. Some of the design patterns actually spanned the entire layers of distributed architecture, right from the graphical user interface all the way to the database. And that the developer had to program and a reviewer had to check whether things are good or not. So though it was a right step, it was not a scalable approach. So we then saw the need of revisiting the compiler. So now you say that, okay, these 4 execution platform is the execution platform which I am going to use as my target. And now can I have a specification language from which I can compile that specification onto these different execution platforms, delegate it to the right GUI manager, right database management system, right programming language, and the right middleware, which was a significant advance, at least which we have seen over last 15-20 years, which came to be known as model-driven engineering. So now the focus shifted from programming in textual language to programming at a more abstract level. And that led to a different kind of accidental complexity. Who is going to program the compilers from those abstract specifications down to the execution platform? And it would be nice if the specification language is such that you are now able to specify these compilers rather than programming it themselves. So think of it as your specification is a data and you have a generic driver, and that generic driver just interprets this data, and your application specification gets compiled, so to say, into these different languages. So that's a significant advance which we saw. And modeling, model checker, SAT solvers is a very rich field which could then be used to address some of the validation and verification techniques. So much of the guarantees which compilers and program analysis provided you at a programming language level is now available at these higher level of specifications also. That's another advance which we saw. But if we now take a step back and say, okay, why were these systems were developed in the first place? Enterprises, they are essentially an open loop system. I am taking some input, I am producing some output, and I need to do as good a job as possible. Automation was the key. Programming helped to address that automation space. But increasingly, especially over last 10 years, we are now witnessing that enterprises are not just a static world. Take an input, static environment, produce an output. But enterprises are now becoming a dynamic entities. And when you are in when you are a dynamic system, one of the biggest problems that you need to solve is what should I do when? Which means now decision making is a hard problem that needs to be solved. There is a lot of literature in multivariate optimization, unfortunately, which doesn't work in enterprise kind of a space. So you now need to go in for simulation based approaches, which is again very close to programming. But over here, you are specifying a system not for execution, but for simulation. And once you know what the right decision an enterprise needs to take, that decision now needs to be implemented into the software systems. Today, most of these software systems are designed to deliver a fixed requirement. But in this dynamic environment, that requirement is going to change almost always. So which means your software systems now need to be architected to be customizable first class. None of the programming languages, programming techniques support that. The probabilistic programming language come closest, wherein they help you specify stochasticity. So these are some of the challenges when in meeting the needs of the enterprises as we see today and tomorrow. Increasingly, programming or computing is being used to address spaces which nobody ever thought computing will be addressing. Like we never thought that we could actually help in doing something when it comes to pandemic control, or we never thought that we might be able to do something when it comes to flood control of Krishna Basin, or we might be able to help Pune Municipal Corporation when it comes to shift from fossil fuel based to green evolution, etc. So all these are now, these kinds of problems are also now falling under the realms of programming, and they need different kinds of viewpoints, different kind of approaches, which the classical programming and programming language community is not taking a look at. But I believe that's a very rich and a highly satisfying space. If we could focus on that, it would be quite impactful, both socially, business-wise, as well as scholastically. Apologies for a very long monologue.
Okay. Thanks Vinay, thanks Uday, and thanks Vivek for sharing your perspective on the evolution. And the way I see it is, programming language is our tool to sort of create solutions. And Uday walked us through algorithmic like responsibilities of algorithms going to libraries and frameworks. So let's go through this from the ground floor of the building to the top floor that you have already taken us, Vinay. Like you have sort of showed us multiple layers that if you see the same thing from ground floor, and if you see it from third floor, if you see it from fifth floor, it looks different. And in doing that, you also took us from a simple program that I as a programmer am looking at, and you want me as a programmer to be able to also see things, how things are at fifth floor. So for the first part, I'll say that the first abstraction, for example, which Professor Uday talked about, that some algorithms got abstracted in terms of packages. So in practice, yes, we have seen that happen. And with, for example, Python example that you gave, with the kind of facilities you have in those packages, or one of the examples which Neil showed us, like this is the Python program which says this is my TensorFlow model, TF dot this, TF dot that. Then does that mean I have become AI programmer? Not. Which means to become an AI programmer, he pointed to some of the fundamental things. So let's try to also figure out some fundamental capabilities that that programming community may need to acquire in trying to sort of reach these various levels So I would see, for example, the set of libraries that that uh, uh, that Vivek you mentioned, no, not Vivek, so that you mentioned. So that abstraction, I felt that, for example, programming languages took certain responsibilities upon themselves. But even if you look at COBOL, it left the responsibility of I/O, like index I/O or whatever that was the thing. It left it to the runtime. And what you have pointed out is runtime has started becoming bigger. With open source, I can also get those components. Like I can choose something to take care of a particular aspect. Like for web server, if I want to do it using design patterns, I can choose Spring Framework, I can choose, say, ASP.NET Core, I can choose JSP. So there are multiple options that evolved. So what I see is, for a programmer, those options pose newer challenges. So one part of the challenge is to know the language syntax and semantics. Luckily, at the lowest level, because control flows were iterations, decisions, and sequence of statements, assignments, that part of abstraction was easier to understand, which is how we learned to understand different languages. Your paradigms, procedural, object-oriented, brought us into something else. So if I'm a teacher and if I'm a student, what should be my mental process to be able to grasp? Because when you come into industry, you come with some language that is hot today. Maybe it is Java, maybe it is Node, maybe it is React. Depending on which college you go to, also things will change. When you go out there, after 2 years, things are going to change and you are asked to relearn. So in this evolution, if you have some examples of how you learned when those things happened, because I know you yourself also would have gone through programming, especially you were in part of industrial research, you have seen other programs. So how did this evolve? If you can throw some light on that. Because that challenge, eventually as you grow, also throws up as a challenge to consulting with my customers. Which abstraction should I use, essentially? So I need to understand that abstraction at the lowest level of detail to be able to be an advisor. But I can still advise the person at a different level. So now that particular transition up and down is potential difficulty that programming community is going to have. So if you have some experiences to share on that, that would be useful.
That's a very good question. I think because we have to deal with abstraction day in, day out. So there is a subtle change. I mean, like what Vinay was saying, that the programmer was overburdened that day, I would say, to do with what and how as well. If you look at now, I think it's primarily you can focus more on what to do. In that case, if you're done with, because the language now doesn't remain a language, right? A language comes with the entire tooling. So you have all sets of libraries, all APIs are ready. You have all environments set up. Essentially, don't have to worry about whether this would actually require more memory or do I need which EC2 instance. I think all those setups are typically been taken care by some other team. With that, you just have to focus on the business problem, essentially. And which means the intent is to know the domain well. So today's programmers, if they can have sufficient skills of orchestration, what they need to learn, I would say, is to understand the requirements from the customer perspective and try to map that to a software requirement. I think once that piece has been done, no matter which language tooling is using, because the language tooling nowadays also I have seen, because being in the industries, see the language tooling has been fixed based on some partnerships. Okay. So if you decide to go for AWS versus Azure, or you fix on some vendor, right? You fix on some tooling which you need to use. And mostly the programmers, the end developer doesn't have really the choice to make which tooling to be used. Again, when I say tooling, it's not just language. You have a lot of libraries, IDEs, specific. There are forums been attached. There are supports been provided. I think all that ecosystem is already been in place. You just have to play a role, which means nowadays when people are getting recruited, there are two steps process. One, of course, we always go and look at the foundational knowledge, which means what universities do provide. But the other piece of knowledge, which is about how do you well adapt to and understand customer problem. And that's, I think, is a skill to adopt over the years. So the abstraction from that perspective, because dealing with libraries and having API orchestration is not that fundamentally complex now, because like what Uday sir has said, you really don't know, or rather nobody tries to get what is happening on the other end. When you're calling some API or the routine, okay, it is expected to work. Neither you have a local setup where you can test, you always test on cloud nowadays. You have ample resources been present. So what you focus from the working perspective is about whether I'm actually doing what customer has asked me to do, rather than going and probably looking at low level problems which we used to do a few years back, which is whether it is generating any memory leaks, or whether this is going to cause me a problem, is it scalable enough or otherwise. In this case, unless, of course, there are some limitations with some languages where you can still write some bad code, and with auto scaling, you actually incur more cost. So the optimization nowadays to understand whether my program would work and how much cost it will be to the organization which I'm actually. So typically you optimize to save the cost is what the thing is. Secondly, when you code, it is all about, nowadays it's not about coding, it is about majorly the decisions are about configure versus code. Because of the tooling support, the more decisions, even the architect's decision, I mean, if you go back, say 15 years back when we actually were working on, let's talk a little bit about databases and data warehousing solutions, where we actually keep thinking about how this, whether this will be star, whether this will be snowflakes and stuff. Nowadays, I think people more concentrate on the sort key and the distribution key because of the way the things have changed. So people, though, are worried about the resources and the data management, they really don't give it a damn, to be precise. They rather give a damn to only performance aspect because they have ample resources. And that's where you actually ease out on data modeling skills, rather you actually focus more on performance and at the cost of some tooling support which is out there. Okay. So if you ask me, at the end, when the schools, actually the universities are teaching students, yes, of course, the fundamentals need to be strong, because unless you understand how this probably could cost me more, whether it will spawn 4 more EC2 instances while I'm writing a bad algorithm, that needs to be known. But at the same time, I think the more focus should be given on understanding the requirements and translating them into the software requirements, is what I feel.
Yeah, so I think you are also still at a higher level, but then maybe enterprises are seeing it that way.
Hello. Yeah, so coming back to the question that Suhas asked, how did I learn programming? So first of all, I have to make a confession. I'm an odd man out here. You know, they say that those who can do and those who can't teach. So I teach rather than practice programming. So my learning of programming has been, I mean, these 3 experts have been doing programming. They've been practicing programming. So my take on programming therefore comes from that perspective. So how did I learn programming? So I learned programming by asking the following question. This is what I see as happening. This is what I see on the surface, but what really is happening underneath? Can I explain what is happening underneath? If I write a program, it works, it doesn't work. Can I explain why it works? I thought that this one single, it just troubled me a lot. It's taken me a long time to learn programming. It's taken me, so many people write programs very quickly. They write very good programs, but I generally take much longer to write perhaps the same piece of program. But that's because I'm stuck at, can I explain it? If I can't explain it, then I remain uncomfortable with Because I don't know whether there will be a situation where my program won't have the intended behavior. And this explainability is not necessarily formal. I would like ideally to be to be formal to the level of formal verification. But even if we keep aside that, at an intuitive level, can I explain what is happening? That has been how I have learned programming, and that has helped me a lot. Now, coming back to why I said that, of course, use of libraries, etc., is a very good thing. But the problem is that explainability goes away. Look at any machine learning program. Can you explain why it's producing the result that's happening? No. So therefore, explainability has become a very important angle of research in machine learning now. People have started realizing that there's a need to be able to explain what is happening. Use of libraries is wonderful, provided they're standardized. I mean, I use STLs all the time. Okay? The trouble with Python is the following. Every other day, there is some library that comes in, somebody publishes a library on the internet, and people start using it. No one knows who wrote it, no one knows how it works. They just see that sometimes it works. They see. So what is happening underneath is something that is not known. So I am not at all against libraries. I mean, it's a wonderful thing. We have to build those abstractions. I mean, as Vinay said, we have to manage the accidental complexity. We have to bury it. We have to remain at the intrinsic complexity, and we can bury it by well-chosen library. The question is, are we choosing libraries well? That is where I don't have a clear answer.
So I'll take, I'll comment on your explainability thing. Actually, that's what I was coming to, because when I want to make the choice and when I want to justify those choice to my customers, that this particular library suits your requirement, because Vivek talked about requirements. I still need to lower my level to the level of abstraction of that library and understand that, and then say, this is your requirement for which there are 5 implementation choices, and this library makes it better. Now, if that is the skill I am required, because eventually things are in some situations, with some customers, it could be at a level fairly higher, like Vinay explained, multiple levels. With some other customers, we may still be working at a different level. So which means, if I am a developer, I need to be curious enough to be able to argue about existing programs, because in open source they are all there. So now, if my overall learning has been such that initially I wanted to talk about my own programs, then while reviewing I want to talk about others' program, whether it works or not. Now I want to talk about the same thing about the choices I make. And if it is a black box choice, then what do I do? Now, if I wear only a programmer hat, programmer as in because of the word program, programmer hat takes us to the programming language only. If I wear that hat as a developer or engineer, nowadays we call people software engineers. So in that situation, I need to now learn about how to monitor, how to measure things. And the measurability, for example, you mentioned about whether this algorithm works. One is looking at using inspection, I can do that, or by measuring, I can do that. Because sometimes if the performance is good, functionality works, whatever is given, then whatever Vivek said is true, because then the customer doesn't care whether it is provided by AWS or whether it was a purchased option or open source. But that becomes an additional responsibility on the programmer now at a particular level. So whatever level I am interacting with the stakeholder, I need to have that capability. And how to build that capability is the question. So the first part of the foundation is, once you know how to go from, we have to learn from lower to higher level. How do we reach those levels? And the other aspect about the behavior change, which Vinay sort of mentioned in terms of, Vivek mentioned about configurability. Now that is where things go to, again, one additional level of complexity. If we use Vinay's term, that is another accidental complexity. After I have chosen Spring, how does Spring work with authentication mechanism? If I don't know that, I cannot solve that problem. So in order to do that, so how do you see, Vinay, in your hierarchy, how these things have emerged. For example, algorithms at one level, it allowed me to choose something rather than writing. So for a business, it is good thing because you can churn basically the application gets delivered faster. So they would prefer choosing some library, licensing some library. That's where it all started. And now with cloud, they say you don't have to do anything. You don't have to have your machine. You use Azure Workspace, you use Amazon Workspace, you write your code there, you deploy there, do everything, like what Vivek mentioned. Now, if these people have still offering services at that lower level of abstraction, many of us will still have to work at lower level. So from your experience in the model-driven development, what kind of approaches you had taken to, for example, when you mentioned about the UI part and the backend part at a different level of abstraction, how did you go about articulating understanding of windowing system, say? Because I think if you are able to tell us about that, like, because at that time Windows was there, X Windows was there, and in internet era now we have got these interactive web applications and mobile applications are added to that. So if I take those as 4 ecosystems of, say, user interface management, at your level of abstraction, how do you really see them as execution platforms? And in doing so, what characteristics do you capture as essential characteristics for you to be able to generate code? If I'm assuming that you are going to use that as a generator, but even if you use that, because that will go a long way in getting a programmer to start associating things right from lower level, which is a programming language, which I think people who are just graduating will still need to understand. But then comes a time when somebody will ask them to now choose this or over that, and that decision doesn't require any approval, and it could be wrong. So for that part, how do you take that Windows or X Windows and all that example? And if you were to do that, and in my mind, what is going on is I am looking at similar low-level thing that happened in mainframe. So you had BMS maps, then you had forms in the Windows earlier. So they were trying to abstract that. And Java said, okay, if you have that, then you can write once, run anywhere. So different evolution points were trying to get to your, so how do you explain that? Because I can then apply that as a programmer.
Yeah, so basically you want me to be Uday, kind of teach instead of writing.
No, I want you to.
No, I'm just joking. Yeah. So
we have teachers also here. So I think all of us, as a professional, I'm having that challenge.
I was just joking. Yeah. So let's take a concrete example. Okay, let me make a preface of what I'm going to say. We still seem to be believing that future is about there are going to be users and there are going to be programmers. It's only programmers who need to know programming and the users need to know how to use the system. I think those days are fast going. Okay. Very recently, for some work which RD, myself and Venki were doing, we had to do a lot of literature survey. And the striking statistics that came up is, even to meet current needs of software development, I'm not just saying programming, software development, the number of STEM trained people available out there are about 50% less. And this number is only going to grow. So, which means saying that there are these domain experts who are going to give the requirements and there are these developers who are going to transcribe that requirement into a language which the execution platform understands, those days are, I would say, gone. So, which means developer now really has to worry about how to express the requirements in a manner that is as intuitive to the domain as possible, and then figure out a way of bridging the gap between the what and the how. Okay. Now let's take a concrete example. Venki is here. Yeah, okay, Venki is here. This is actually Venki's example, but let me take it because he was the one who has built this front-end part of the tool. So, commonly faced requirement is, I want to know, I want to display a list of people, list of the people who meet some criteria. So typically it is done with a screen wherein you will have couple of text edit fields wherein you will mention some information, and then you will have a drop down wherein you will see a lot of records. Now obviously you don't know how many records are going to be fetched. So you cannot, and you have a finite real estate of the screen available to you. Second, the data which you show or display must be current. So there is a currency angle to it, because this is a distributed system, data is somewhere else. So which means you really can't fetch the data, store at some intermediate server, and then keep on pulling it from there. That's not going to work, because the currency problem, currency won't allow it. And B, if you say, okay, I'm not going to have it intermediate, I'm just going to take a lock on the database, then your concurrency gets hit. So now you need some innovative solution of how to manage it. So, and for that, the only thing that you can rely on are the primitives which these three distinct technologies provide. So the way to do that would be, okay, I will have a page down button. So I will fetch a query. That query will return me a result set. That result set will be bounded by the number of rows that I can display, which is going to be a configurable parameter. So I'm not going to hard code it. It is going to be in some .ext, .lni kind of a file. And now I now need to write my query. It now needs to have an additional where clause, which will take into consideration the continuation key, which means now it says that I'm going to fetch you 20 records, and there will be some data fields of that 20th record, which is now going to find a form as a continuation key, so that next time when I fetch the next block, I start from that place. So now, just to implement this simple functionality, you now need to have a design pattern that cuts across the display, the programming, the querying, and the database management thing. Okay, so you think of this as a solution architecture. This is what I want to implement. Once you know what needs to be implemented, as you say, bottom up, then you can think of, okay, how do I make this abstraction available to the GUI designer in a most intuitive manner? How do I make this abstraction available to the query fellow so that he is able to write the query without really knowing to know the nitty-gritty details of different syntax of different databases? He doesn't even need to know how should my schema be organized so that the plan that will get generated will be most optimal, etc. All that accidental complexity can now be hidden by the code generator. So if you are going to use DBX as your database, then all your varchar fields must be on the trailing edge of the schema. If it is SQL Server on the other hand, they better be at the beginning, because that's how the plan gets formed. Now, you know that, you make use of it, but you don't pass it on to everybody as a coding standard, coding guideline, and then help a reviewer to say whether everyone has coded it like that. That approach never scales. So the best approach is come up with a domain specific language, allow the developer to specify the solution in that domain specific language, hide the entire complexity in the code generator. And now, I'm just sticking my neck out to be beaten by everybody. Increasingly, that domain specific language is going to be, I will say, natural language. It will just use a particular domain ontology as an additional dictionary, and people will just specify what in that natural language, and saying that, okay, when I say customer, I mean bank. When I say customer, I mean whatever, telecom company, because they have slightly different nuances. And in that context, you please interpret what I have said. And then we will have a successive refinement stage of how these specifications in natural language will get eventually implemented into the code. Through domain specific languages, we have shown that it is possible. Now we just need to see if using the current code completion, AI-based code completion techniques, we can still go from natural language to the domain specific language. So, I mean, I'm at least for those students out over here, the days of them programming very close to the execution platform are gone. They better know some domain.
Yeah. So, so Vinay, thanks for that example of a UI showing something, because I think that definitely sticks better, because that is a real thing, right? And so, as you were explaining that, again, I'm playing a role of a programmer here, from then to now to future. So you have also given me a picture potentially from now to future. And if I was the final year student, I would start thinking, now what should I learn? Because I'm stuck with computer organization. I have to learn compilers. I have to learn programming languages, databases. So how do I reach this level? So I think we'll need to demystify some of that. So I'll take your example, and also take our earlier discussion about algorithms coming in as packaged in a service and all that. So I think at different levels of organizations, if we don't yet have the tool which generates everything, then if I wear that hat, which you mentioned, what it will help me as a programmer at that level. Suppose I'm an architect or a designer who is essentially laying down those principles. I do my homework of all the target platforms that need to be supported, and I sort of guide the team in such a way that, so basically as a team, we define a way of doing things so that some of the junior programmers can continue to be closer to the lower levels, but other people start thinking at a different level. Because I could relate some of those things in terms of change of behavior, which I talked about configurable properties. We had done probably 15, 20 years ago, software which every customer needs to have different screens, every customer needs to have different behaviors. Like it was a benefit enrollment platform, and what benefits are shown because they depends on what plans they bought from insurance company. So this software kept all the configuration in the database. So some of that information was essentially changing the behavior, and those who do not understand that abstraction would make a lot of mistakes, because they don't know with changing that knob, what all things will suddenly there will be too much of flow or something which could be treated as a security vulnerability also. So I think one of the skills, based on what you have shared as a typical way of looking at that, going from then to now to future, this traversal between various abstractions is going to be a very important skill. And as you and me, for example, we started our career with Professor Nori. So we learned those abstractions because of the questions that he asked. So which means for the seniors in organizations, they need to be able to ask these kinds of questions and engage with the developers to really take the status quo to a next level. Because I see some of those things implemented in many APIs. For example, suppose you are integrating with, say, any of the learning systems like Udemy. You ask for something, it never gives you, because there are thousands of courses that are available. It will give you page wise, it will give you a total count. So the response format actually represents the abstraction that you talked about, which comes based on that thinking. And once that is taken care of, you are okay. In latency case, if I'm not doing that, I have to face a challenge of, if I'll use cache, but then when should the cache be refreshed? That becomes the problem. So your problems keep coming. How to navigate at different levels probably is something to learn from then to now. And I think I've been sort of trying to always do that. And I think if every one of us learns how to do that, we'll continue to be a good set of programmers, if I still use that term, but essentially problem solvers. Okay, coming to the methodology part, one of the thoughts I had is, what is the business driver to do things agile today? And Vivek, for example, even talked about safe agile, right? So if you can tell us more about from then to now, what environment changed, and because of which how we have moved from the waterfall to the current model. And actually based on that, I have some more questions, but that is also something, the methodology and the process to be followed is something important that I think if we become aware of as early as possible, it becomes very easy for us to work.
So yeah, a waterfall, I think if you go back, how it has been probably brought in computer industries from mechanical industries, typically driven by the assembly line, where you perform this followed by this. So it typically has a dependency. And that was because that was the only model of tracking or management, I think, typically been started following by computer industry too. Was it bad? Was it not? I think agile and scaled agile, I would say it's been hyped too much, if you ask me. Does that mean what is the essence of agile is? Okay. Essence of agile is basically your customer should be informed about what we are doing, and more frequently, or rather you make customer be part of your development process so that you seek the feedback more often than few months down the line, right? So that's the only cycle which is getting I would say lower and lower. So the durations by which you ask the feedback is been lowered, and which is good because your customer can give you early feedback. So early fail, and again you can do early rise so that you can actually learn from your mistakes and probably implement them well. Now, was it this philosophy not there earlier? I think it was not the case. So just to tell you one example, when we are dealing with transforming the entire billing system for Ericsson way back in 99, it was majorly DEC Pascal, as I mentioned to you, and Pro Pascal embedded SQL extensions to ANSI and ProC pre-compiler extensions. Again, the versions of Oracle was way too different. The thing is that when you are actually been asked to deliver 18 digits of precision beyond after a decimal point, and that's the only acceptance criteria which has been given by the customer, I think your customer has to be with you all the time. So right from the specifications, I mean the compiler specification, Lex and Yak specification, we actually keep that person involved. And not just that, that person was actually a PhD in compiler, so he could actually relate. And for knowing that and for doing that, we actually studied our customer before. So even before submitting the proposal, we studied that he is the person who has done PhD in compiler. So that's the way the proposal was put. And I was in MBT that day. I mean, not TChem, it was MBT. And we won that proposal as against, and MBT had no such history of delivering any software in compiler or language processing domain. We actually could do that because we could study the customer well. Now, that's the only essence of Agile as well. You study your customer, you provide him what he wants, keep him up to date on what is happening, correct? Now, what changes beyond that? I mean, that's one or two aspects, but beyond that, I think Agile also imposes more manageability or self-manageability on each team member. So that whatever that Scrum thing happen every day for whatever minutes, though again, it's not well implemented many places, but why it is to be done? Because then every person feel empowered, feel responsible for what he or she is doing. And that is known to all so that they will actually then collaborate well. If there are any dependencies, they can solve among themselves. And if there are any blockers, they actually can project it out and get it solved as a team. So it's more of a self-manageability that has also been imposed. So I think the process change which you see, it is not something drastically different. It was much needed then. It has been given a name. That's what I would say. Okay. So that's the process change. If it is a process change, it is for good. Of course, it is badly implemented, then that's the problem. That is also one of the aspects. Most of the companies or other, there is a habit of doing that ritual every day, but nothing is probably earned out of that because nobody knows why they are doing what they are doing. So that is something which is a question anyway we have to ask, whether it is following the processes or doing software.
I agree that the quick feedback that you get is something which is really the main benefit of that. And from an evolution perspective, it all started with getting user interface feedback in JAD sessions and all that way back in early 2000s and all that. And so I think it's 3:20. What we have touched upon really is going from programming language, that lowest level of abstraction. We touched upon some aspects of whatever was abstracted in terms of libraries or even services. So if you just use that as a cue, saying that, okay, I need to become a better solution provider, I need to be able to understand what that particular piece is doing, whether it meets my functionality requirement, whether it meets my resource requirements, whether it meets my performance requirements, which would probably require me to check it out in a different way. Other thing is from if I go to another higher level, which we had a discussion with Vinay, now that helps me have a good picture of the systems from the topmost layer, which is the business part, to the bottommost thing. And the interesting thing is the then part of our working style used to have those process diagrams, which were hierarchical in nature. So I think conceptually it would meet that, but operationally it will require something different, because you need to have that domain expertise in understanding that. And that is again one of the key kind of skill that has emerged through our discussion going from then to now. In the morning, Neil already talked about AI, that just using those libraries is not good enough, and you need to have some linear algebra and statistics kind of knowledge. So that becomes good foundation, which becomes a good takeaway for me. If I want to become an AI programmer, then I need to go beyond something which makes me announce myself quickly as I am AI programmer. So I think those are 4 or 5 at least key things that we have been able to accomplish in our discussion. I would like to invite some questions from audience, so that they may be thinking about something either from teaching point of view, learning point of view, or some professionals out here want to have some comment or question. Please go ahead.
Two years ago, I had to face this problem of curriculum design, and I took one concrete instance, and I'd like to hear 4 different answers from each of you according to your lens. Should we be teaching linked lists?
Why not?
So why not is basically one argument is Vinay's thing, right? Maybe you are never going to do that in your real life thing. So should you teach that? I mean, what's a different? I mean, I have my own answer,
Okay.
but
okay. Let me elaborate on why not. I mean, I agree that what we teach, not everything will be used. What we teach, not everything will be used directly, and what we teach, very little of it may be used in future. That still doesn't stop us from teaching things that exercises the mind, teaching things that allow students to learn the practice of building mental models. I mean, if you have something else that exercises the student's mind, sure, why not? So my point is, let's not look at teaching only as something because it's going to be eventually used. Let's look at teaching as something that flexes their mental muscles. And linked list is one of the useful things to do. Maybe they'll never use it. Maybe they'll use STL. Maybe they'll never write a program, but it's still a good mental gymnastics to do with linked list, circular linked list, and why not? That's my answer.
Okay, I'm not sure if my articulation came across as you really don't need to do any deep computer science at all. That was not what I said. What I said was you just staying at the nitty-gritty execution details is not enough. You need to also know how to have purposive abstractions at the right level, and also know how to build, how to bridge the gap from those abstractions to the execution level automatically. Today, that abstraction gap is bridged by saying these are the coding guidelines, these are the reviewing guidelines, and that approach never scales. They are design patterns. Design patterns are also just word of faith. Use it this way, use it this way. Someone has to use it. Someone needs to check that it has been used. Everything manually. That also doesn't scale. And when you are going to bridge this gap in a purposive manner automatically, you better know both sides equally well. So I didn't say that you don't need to know details. No.
Okay, answering a simple question, I think linked lists need to be taught primarily because of the data aggregation techniques, right? And it is very close to implementing message queuing, which has been used today as well, right? So I would say that is definitely has to be taught. So there are different ways of aggregating data or managing data and has to be taught. So why not just linked list? Maybe, I mean, we were already discussing this over lunchtime. So I think you should. That's the simple answer.
Yeah, actually you have got list answer from him, that two answers saying yes. If you allow me, can I choose an algorithm, say depth first search or breadth first search? That could be a question.
Oh,
Saying that
alright.
should I teach depth first search? So on the list thing, what I would say is you teach the concept, next, previous, and all that. Ask students to solve problem at a completely different scale. If you can do that, and as you mentioned, you were in Yahoo, so obviously you know how maintaining lists of large volumes, what all challenges are there. You are indirectly also helping him, not just one list, that now you have to create a hierarchy of lists, because your problem domain data, it's so I think if you are able to visualize something like that, so just one single list you teach and forget, that same student will come to me in interview. I would probably want him to solve a different problem. So for example, breadth first search or depth first search. If you just ask people, people are able to reproduce the algorithm because it is also there in the in the books, BFS, recursive, and all that. But if you teach them with respect to a problem or the problems that they solve, or a project, in project you have those situations. I think if we are able to create those situations where you have to actually apply that knowledge, but it becomes a much bigger problem. For example, for search, I used to tell search and these things, I used to, for graph, I used to tell people an example that you go to kayak and you are doing for flight search. Now, there are so many knobs over there saying that I want to, or even a Google map that we use here today. So you have a graph that is underlying data structure. But the edges, when we do depth first search, we are just traversing, picking up an edge and going down the road. In real life, all edges have weights. All that weighted thing is there in the book. But if I take this problem and I say, okay, now when you are doing this, now this is the weight. Okay, so if, now, but this itself is also not static. Now, if we are able to take that concept and if it allows, of course, in the university education, how much is allowed is the question. But I think the project situations, if we impose in such a way that all this gets tested, then they are already ready with the algorithms and data structures when they come in. And then industry can start focusing on all other things about the choices and all that. Now, I may not have directly answered your question, but I have just sort of touched upon things. And some of these things I myself have gone, as I'm so passionate about computer science that I took a partial break at some point of time where I said, I'll go back and teach students. Now, which students should I teach? So I had only 3 or 4 people I actually engaged with. I did not really teach them, but we solved problems which required algorithms. And those were the informatics Olympiad problems. Because many times we don't even understand that graph is a data structure that should be used to model a problem. And we are in search of something. I might do Google search and all that, but I still don't get answer. And that's where, from an industry perspective, I felt that if we are able to teach them these things, and I do my part of it in engaging with the projects that I work with. After solving the problem, I encourage them for a sort of a session afterwards, saying that here is what happened, this was the problem, this is how we remodeled it, and this is how we solved it. And that essentially stays. Because the experiential learning is also important, right? And I think all of us are essentially sharing the experiential learning that we got.
This is very good, because now we can take this excerpt and show it to skeptical students and say, look at what these guys think. Right? And by the way, the funniest answer I ever gave to this question was, do you want to pass interviews or not? I mean, that was a joke. But...
No, that's why I told you what kind of interview I would be conducting.
Oh, somebody has some more questions?
Ketkar sir, you said you spoke positively about STL, and I think you effectively grumbled about Python, or the kind of code which modern students, current day students write in Python. This is kind of matching my own experience that I must have been one of the earliest people to start Python in 2000 teaching. And I don't know how many of you are familiar with this notion of blub language from Paul Graham, that there is a kind of middle level language which is done by everybody, but which makes everybody mediocre. So today I find Python is becoming more and more everybody's mediocre language. But I would just like to hear, what are your experiences of how Python makes students mediocre, if that's what you were implying?
Thanks, Modi, for asking that question. I should be calling Modi sir, because he has taught me. I was a student. I never got good marks in his courses. That's a different question. But yes, I mean, thanks for asking this question. I had to throw away implementation of my student, which he had done for 2 years, all done in C++, all nice classes, everything. The only trouble was all data items were stored as strings. So, which means that all comparisons were happening on strings. And one of the simple principles that I tell my students is, no decision other than input output, no decision should be made by string comparison. String comparison is the worst way of writing programs, not just because of resources, but it makes program less reliable. If I were to say, I have to check direction, is direction left, I'll do this. If direction right, I'll do that. I write that program and I code it as a string. Somewhere I use capital L, somewhere I use small l. Compiler has no way of knowing what you're saying. Compiler will just compile the program will execute, and it won't do what you want to do. So therefore, never use strings is my first cardinal principle that I might tell my students. And Python says use strings and only strings. That is my problem with Python.
And I think we know that numerical computations are very slow in Python compared to Fortran. So just a reminder of that.
I have a WhatsApp question from Bangalore. Somebody messaged me, a friend of mine. His question is the following. So basically now when you are teaching kids, when you are teaching students, should they be encouraged for learning core skills so that they can do innovate and research upon in like startups or companies, or should they be encouraged to prepare for immediate business needs by studying Python kind of languages? Basically, the question is, what should we rather teach or encourage the students for? To learn the core computer science skills or those which are in need at the moment, Python libraries and so on? What is it?
Can I answer that question? As I said, I'm going to answer that question from a different perspective. You know, those who can do, those who can't teach. So I'm going to talk about that perspective. I think what we have to teach students is to feel excited, no matter what we teach. I mean, that's the take that I have. You may choose topic X, you may choose topic Y. Get the student excited. If we can't get the students excited, we are not teaching. We are only conveying information. And for conveying information, Uncle Google is there. Teachers are not needed for it. Teachers are needed for getting students excited, no matter what. I mean, if we can get students excited, if we can, they can see what excites them, how they get excited, they will find their own path. I don't need to teach my students, this is good computer science, this is bad computer science, this is good business, that good business. What I want to teach my students is enjoy what you do and you will find your path. I don't know whether that's a very orthodox answer or whatever it is, or roundabout answer, but I have seen that working quite well in practice. Keep usability aside. If you're excited, you will find things and do things well.
Right.
Yeah, if I may have to add to that, reiterate probably, university should focus on enabling or imparting foundational skills to the students, and also a skill which is rather difficult to pick up, how to learn on your own. So I think that's what university should focus. University shouldn't try to train their teachers, train their students so that they are a better fit for industry.
Any more questions are there online or here?
I guess that's about it.
Okay. Thank you, audience, for your questions, and of course you can ask us more questions when we come on that side as well.
I'm learning now. I'm prepared with the rose for the next speaker, which is Dr. Anand Kumar, my close friend and my fellow researcher at TCS Research. Anand has done his PhD with Professor Nori. We all know that Professor Nori worked a lot on programming languages, compilers, programming and all that. But what did he do after that? So Dr. Anand Kumar is going to talk about that beyond programming. What can you do beyond programming? So with that, I welcome Dr. Anand Kumar. Anand? Please play the slide. So there will be a tree that will be planted on your name.
Thank you. Good evening. Am I audible? Thank you. What I try to cover here is the work that Professor Nori put me on for the last 17 years, 17, 18 years. Known him from 2004. Was a mentor, was a guide, a teacher, a kind of uncle, friend, and you can say all kind of relationships to me and my family. So when Professor Nori moved to Hyderabad after a successful career in TRDDC and playing the role of the CIO of TCS, he came with a very interesting observation. He said, we built the best tools in TCS. We built the best tools in the world, the best modeling tools in the world. And when I was initially very surprised that not everybody is using my tools. So I became the CIO. I thought I have the power to force everybody to make them use my tools. Then he said, but when I became the CIO, I understood the problem is completely different. The problem is totally different. And I have to figure out, middle of the night, what is the revenue from one particular geography. And I'll call up that regional manager, I'll call up this manager, I used to call the president to figure out what is the revenue. So it is no longer about tools, no longer about software, because a tool is nothing but it is providing a service in a process. People use it for hardly a minute, maybe 2 minutes. That's what the entire software, entire work that I'm doing is useful for. So he said, okay, so now I need to restart my thinking with regard to what should I really do. So at that stage, I think he was 59 or something like that. He said, I can afford to do it. I can take whatever risk I want. So that is the starting point for us. It was the journey that we are started together, which I am continuing now. I have a bunch of friends. All of us are working on it now. So basically the idea is very simple. You always see this slide in his presentation. He says, I'm like an ostrich. My head is stuck inside silica. I started as an amateur programmer. I was thinking only things inside the machine because I can play God to the machine. Then I got experience about how to become a better God to the machine. So what did I do? I started with a simple set of tools and I had a bunch of toolboxes which I used to use. Then I became a professional where I know how to do it end to end. And once I became a professional, I made many people behave like an ostrich. I made everybody stick their head into the soil. All of us were stuck inside the mission. We are trying to see how to make the mission perform better. Yeah, we got into models, but still the question remained, am I clear? Did I know what is my customer trying to do? Did I know why are they doing it in this particular way and not in that particular way? Did I know what is the business of my customer? What is he really doing? I have no idea. So after all these years, I don't know what little aspect of banking. I did so much work in banking. Mastercraft was done for banking, but I don't know what is banking. So that's when he woke up. He said, there is a real world. I need to look at the real world. What I see inside the machines are reflections of what is the real world. And it's only after he woke up that we met. So I was very fortunate because he woke up in 2003, end of 2003. And then he said, we started interacting very closely. It was like morning, I wake up, I was staying opposite to his house. 6 in the morning we start. Till night 10, I was in his house. Always like that. So always continuous interaction and asking questions about why should things be done in this particular way, not in some other way? Okay. So he helped us transform. I came to him as a programmer. I had been programming from 1989. So before I joined TCS, I built the first CAD system of India. More than 2 million lines of code. One person did everything. We sold 1,500 installations all over the world. It was there. So I had a big of arrogance in me saying I can program anything. So when I came here, first year, he said, okay, let's do some tools. We built some tools. Second year, he said, do you know why you did what you did? Do you know why you are doing all this? No idea. So a person who has been programming for so long, he said, this year there's a rule for you. I want you to think for 11 months. The entire 2005 said, think why you are doing this. I'll give you 1 month to implement. So 2005, 2006, the financial years, it went on like that. Every year, the journey is to only think. The journey is not to do. Why should I do this? What should I do? How is immaterial? We can get it done. So it helped us, you can say, look at the world. Okay, we are no longer tied to the mission. We believe that mission is used only to, let's say, bring some difference. We are no longer tied to the mission. Okay, so now why did we look at it like this? Because there are various perceptions. First, the programmer. The programmer starts with a perception. The customer knows everything. The customer will give all the requirements. We are only responsible for taking the requirements and putting in a specification and then solving the problem. So this is the perspective of any programmer. He says, okay, no, I don't need to know anything. I need to only satisfy the requirement specific to the machine. And then you jump to the project team because you cannot work in isolation. There's a project team. The project team says, I know everything. We know everything about the customer's business. Otherwise, why is the customer coming to us? We know everything. And then we also know more than the customer because we have experience with programming software for different domains. So customer doesn't need to tell us the basic things. They need to tell us only the extra. Right, now what did this mindset lead to? I don't know if you remember the first smartphone that came way back in 2008. There's a Nokia N97. I don't know if you have used it. It was the first smartphone. It's a touch screen. You can send email. You can send MMS. There was maps. You can have Adobe Acrobat, Office, everything was there. Okay, everything was there, and it had 32 GB of inbuilt memory. It's a powerful piece of machine. But when you have a phone, what is the basic thing that you would like to do? You would like to make a phone call. You can never do that on a Nokia N97. You can never attend a phone. You can never make a phone. If somebody is calling you, unless you remove the battery and put it back, the phone will not work. I mean, you just keep scratching the screen. You can scratch it on the floor also, nothing will work. It's because of this mindset. We say that we know everything. We cannot have that mindset. It's a problem. So then we speak about providers, organizations that's providing the solutions. Their perception is we can automate anything. But what should you automate? What have you automated over the last so many years? We know the technology problems, but do you know what is the customer problem? Do you know what is the banking business? Do you know how the bank is making money? It's a very critical thing. I mean, we automate, we get into the banking system. I was there when the core banking system was implemented in Central Bank of India. So it was right across my premise, my office. And we used to go and speak to the manager just like that. Okay, because lunch hours are after lunch we feel very sleepy. So we have to spend some good time. So we go to the bank manager, we spend time talking to him to figure out what is happening. So he said, sir, You've done a great job. Very nice system. But let me tell you a problem. I said, okay, tell me what is the problem. See, before your system came into place, I'm not telling you your system is bad. Before your system came into place, my customer who is having a current account, he will come to the bank, he will present the check to the teller, okay? And if there is not enough money in his account, the teller will ask him to come and meet me. I will talk to him. I will figure out that he is getting some inputs, his businesses, he is going to generate a lot of revenue. So understand what is the general state of his business, his industry, so I can make a decision as to whether I can give him money or not. Generally, I honor it, I sign it, it is passed. Now you have implemented your system, fantastic system. What has happened? The person comes to the bank, he presents the check, the teller receives the check, he notices that there is not enough money. So what does he do? He puts it in the system. That is a transaction ID. So this transaction ID is noted. He writes it in a piece of paper. It is confidential information, should not be shared with anybody. So he calls a peon and gives that piece of paper to the peon. The peon comes and hands it over to me. Then the customer comes here. I cannot discuss with the customer because this is very top secret thing. So what I do, I look at I have to log into the system. I have to search for that ID. And then I have to go and approve. On what basis do I approve? So you see, what have you done here? You have not understood, help me understand my business. You have not understood the banking business, and you have created a system that is a mess. Okay. So now what is the customer really looking for? He's saying, okay, what are the silos in my business? Does this provider know enough about me? What is the difference I can bring to my customers because of this new solution? What can I do better? I know how to run my business, but what can I do better? What should I do better? Okay. So now the thing is, we are very good programmers. It's very natural to us. So for us, it's a hammer. So for us, everything looks like a nail. We keep hitting it with a programming solution. Do we really understand the domain? So that was a challenge Professor Nori brought to us way back in 2003, 2004. Okay, so now I'll ask a very practical question. Do you use Office or LibreOffice Writer? Word or LibreOffice Writer? How many features are there in Word? Or how many features are there in Writer? How many do you use daily? 10, 50? What is the cost we pay to Microsoft year on year? 7, 8,000 rupees. How many modules are there in Office? 12, 16? So out of 16, we are using 3, Word, Excel, PowerPoint. Word, Excel, PowerPoint, each one of them has more than 100,000 features. How many features we use? 50. So you look at the economic value of the solution that you are using. It hardly turns out into 5 rupees or 10 rupees. And why are we using all this? You see, this is the problem that has been depicted here, which is called as the Fisher-Ritchie curve. Okay? When we start with a system, very happy with the minimal set of features. Yes, it's nice. Can you give me more? I'm very glad you added all this. Very useful for me. Cool. I know everything. Okay? Now you'll reach a stage where I have to look at the manual. I bought a new car. I have no idea how to drive the car. Apart from the steering and the brake and everything, I have no idea how to use the car. So many new features. It's crazy. Then I say, okay, now look at the new Windows operating system. I've been using it from 1990, 1992. Windows 10, it's a crazy. I don't know where things are. I don't know where the output things are. It's crazy. So I buy the machine for something. I start using the machine after 6 months, 1 year, because it takes time for me to deploy it. And I don't know how to utilize it. What will happen? I'm not going to use it. I have an initial feeling that whatever I am worthless. Then I say this fellow is useless. So how many features are there in Word? LibreOffice. Why do we use Word? We are using it to write a paper as researchers. How is Word helping you write your papers? It gives you a blank screen. Other than that, how is it helping you write your papers? Right? I mean, just take a blank Android phone, buy a new phone, 128 GB Android phone. I come from, and I've been programming for 33 years. I know the value of memory. Buy a new phone, okay? I start using it. Initially, it just sets up. It says some 10 GB, 16 GB is gone. Where is it? Missing. I can't even look at the drive to figure out where the hell is my data. I paid so much money, 128 GB, I see only 100 GB left. Where is the rest? Windows 95 was 14 MB. Now what is there inside that 8 GB? All I'm going to do, or my grandmother is going to do, is make a phone call, maybe see WhatsApp or YouTube, that's all. And do I need to spend this much for that much space? You see the problem that is coming in. So what I want to imply is that human-made entities as a whole, there is significant growth in complexity. We are no longer dealing with things that one person can understand, one person can comprehend. You see, today morning, he was talking about GCC, saying 18 million lines of code. Is there one human being who can comprehend the entire 18 million lines of code? Where are we then? We are building something and we are going to go forward into something else which people cannot understand. It's a very, very complex situation. And that is there in every aspect of human creation that is happening. Every human entity that we are dealing with, it's so complicated. Okay? And some of the complexity is because we introduce it. We keep adding junk after junk after junk and nobody knows how to use it. Okay? So, how do you deal with it? So Professor Nori worked out a very elegant way of dealing with it. And initially we called it as a TCS way, but I think it's Nori's way. Because we like to call it only as the Nori's way. Nori's way is very simple. To build anything in the industry, at an industrial scale, you need processes. You cannot shy away from processes. You have to follow process steps. To build quality into things, you have to follow processes. So do process. Every process step leads to some quality in the offering. And because of the quality of the solution, there is some benefits experienced by the customers. It leads to satisfaction. Okay, so this is a general norm. This comes from Deming. It's a process step. There is product quality. Because of that quality, we get some benefits. Customers are satisfied because of the benefits. Now, let's look at it from the reverse. We need to satisfy our customers. Okay, so what do we sell? We don't sell quality. We sell what is the benefit we get from using this particular phone, particular device, particular product, or particular service. Benefits are the one we sell. What do we produce? We produce things that are with quality. Quality is the one that is in our control. And we know processes are important. So start with benefits. Don't start with code, don't start with infrastructure, start with benefits. Don't start with requirements. What are the difference you would like to bring in? What are the benefits? The benefits form the basis for what are the quality characteristics of your system. Quality is what you can control in your production. The quality forms the basis for your process step. Simply stated, you engineer quality into your offerings so that the customers can experience, customers or other stakeholders can experience value out of the offering. So value is worth of something from their point of view, not your point of view. Quality is the thing that is an attribute that shows whether something is inferior or superior. Wait, very simple question. Why do you buy an iPhone or an Android phone? There's some reason why you buy a phone that is very slippery. If it drops, it breaks. There's some reason. You see some quality in it, some value in it. Okay. So he said that is the basis. The value quality thing is the basis. So quality is the distinguisher and customers appropriate value due to qualities. So now why is this shift necessary? Because earlier they were focusing exclusively inside the machine, inside the system. We're focusing exclusively on the system. Understand, get the requirements, envision the system, architect the system, build the components, test the system, check if it is ready, deploy the system. Okay. Now what has it resulted in? We keep getting automatic updates every day from Microsoft and even from Google for the Android operating system. Keep getting so many updates. Okay, we are talking about all this quality testing, etc. It's a crazy game. Okay, so let's focus on something. I'm going to use something for some particular purpose. I'm going to use a system for some particular purpose. So focus on the purpose. Okay, But focusing on the purpose is difficult because I may be using it in a BPO engagement. I may be using it for doing research. Very difficult. You have to get into the private details of an individual. So let's not get there. Let's go above than that. Look at what is the difference it can bring in. Focus on value. So value can be different things. There could be societal values, there could be economic values, there could be business value, okay, there could be price, there could be so many values that is there. Start with value. Understand what is the problem that is there that needs to be solved. You have to understand the problem, analyze the problem, and then say what is the solution we'd like to create. Then encode that solution as a software system. Okay. Now what do? We just start programming because our solution is only in the program. So don't do it. First look at the solution, then you can look at encoding, because the how is always easy. How is not difficult. Programming is not difficult. So then you will know, you go through the normal engineering process, then check if the system has been utilized properly, whether it has been adapted to a particular context, see what is the value the system can generate. And this cycle keeps happening again and again and again. So instead of focusing on the system, you have to look at the real world, because when you say value, you have to put yourself in the shoes of your customers or other stakeholders. Okay, how is somebody going to use your system? So in this process, there are different things. You have to look at the life cycle of the entity, because there is going to be a birth of a new system. There's going to be some values. There's going to be growth. There is maturity, where there's some things that are going to be done. There is decline in the system, and then there is death of the system. At any point in time, who makes the decision whether the system should continue or it should die? The architect, not the programmer. Okay. So the life cycle of an entity is a very critical thing. And then comes, okay, so if we are going to make this change, we can't make this change at the programming level. We have to look at a very, very higher level. So what professor said is, he said, for any problem, it is possible to do good engineering if you have the right set of engineers. You don't need architecture. Okay, you can meet any requirements. But why do we need an architect? We need an architect because you have to bring some difference to the stakeholders. You have to imagine what is going to be the future. So he said architecture is a very, very critical thing, and this is where we will step in. What is architecting? You have some thought, whoever is a customer or the other stakeholders, they have some conception about what is their problem. The architect connects the dot and says, this could be a possible solution to your problem, or this could be a problem. The engineer is going to implement it and then create this entire ecosystem around it. So architecting and engineering, this is the journey that is happening. Okay. So what is the paradigm shift that Professor Nori brought in with regard to architecting? Now these are all encoded in ISO standard. It's not a local initial thing. There are 3 ISO standards on architecture, and all of this is based on the fundamental ideas comes from him. This concept of value, quality, everything comes into the standards. So if you look at it, the state of the art with regard to architecture is predominantly in terms of frameworks. People have to follow different frameworks. Based upon the domain, there is architecture for, say, IoT reference architecture, cloud reference architecture, automobile reference architecture, any domain, any discipline. Banking, you look at quads architecture, so many architectures that are there. Okay, but the problem is, this architecture is going to result in a huge set of documentation, huge. And there is going to be not architecting effort, but predominantly modeling effort. People have to sit and put together models, and that is what is called as a modeling hell or a description hell that is happening. It's complicated to deal with. And there is no process here because architecture is still practiced as an art form. So he said, okay, let me try to deal with it in a very simpler way in terms of value and quality. I will start with the problem. What is the problem? My offering is the problem. I'm trying to create an offering. The offering should have some quality characteristics because the customers are interested in the value that the offering is creating. So start with the quality characteristics, start with the value, and then I say, I'm going to architecture. What are the architectural characteristics that needs to be addressed? Pass on to the engineering and say, what are the engineering characteristics that needs to be addressed? What are the construction level characteristics? What are the deployment characteristics? What are the initialization? How do we configure it? What are the operational considerations that we need to take into account? You break down all this, and then what you have is a rich set of quality characteristics that should be embedded into the system that you're trying to build. Okay, Then you say for each level, for every quality, what is the difference it is trying to bring in at every level. So you see the value. So when you start, you say, this is the potential value of the system, and this is the quality characteristic of the system. These days, what we happen is that when we go and deal with the customers, we build a system and go to them, they ask the question, okay, now that you are done, you build the system based on our requirements, can you please tell us what is the difference the system you are bringing or the system is bringing into the table? We spend 6 months to try to figure out what is the value we can bring in. Okay, and then we say, yeah, we have built, okay, you see, I have built something called as the gaming system for Microsoft Connect. Okay, I built this system. Now what you can do is, since there are sensors which tells you, which captures all your interactions, the same system can be used to figure out whether you are sick or not. You are playing games here. Where does sickness come here? You are playing a game. There's no requirement, there's no match. Just because you can capture some sensory information. Do you understand everything about the signals? You understand everything about what is the good, what is the wellness characteristic? You don't know. And don't say that this is value creation. Okay. Look at the difference that you can bring into the table. So then, we encoded this in the ISO standard. It was published in 2019. This is the architecture conceptualization process. You see, the problem that we fundamentally started with was, you started with programming. You find programming is difficult. So you raise the bar and say, you do modeling. Now the problem is, even for modeling, we need to have modelers, good modelers. Otherwise, how do you know the model is correct? Okay. And how do you know the model that is encoded is correct? Does it meet the requirement? You have a fundamental problem there. So that gap is never addressed. So we said, to address this gap, let's start from the beginning. Why are we doing this? Because there is some problem that needs to be solved. So what is the problem that needs to be solved? Understand the problem. Analyze the problem. Okay. Not the software problem, but the real world problem. Analyze the problem. Synthesize your solution. It's not one solution, it's always many solutions. Okay. Because the solutions, when you do enough analysis, you will end up deciding what is the technology you need to utilize. So you should always have many solutions. We call this as a candidate set of solutions. And then analyze each of the solution to figure out which solution is appropriate. And then formulate an architecture. What is architecture? Architecture is like a plan. You formulate a plan. How am I going to realize this solution? But then it is not enough if you formulate an architecture. How do you know your architecture is correct? You evaluate your architecture. Then this is a cycle. You keep going back and forth because you may have missed something. Keep questioning yourself. Then you say, okay, now I have reached a stage where I know my architecture is correct. Then I go and describe it. I say it could be described as a component model, it could be described as an architecture model, it could be described as architecture views or anything, any such artifact. Okay, so this is a transformation that was brought in so that we don't get stuck in the programming hell. Rather say, what is the real world problem that we are trying to solve? How do we solve it? Okay, so there could be the different transformation that is there, problem space analysis. Right. But now what you need to understand is that whenever we talk about architecture, there are always levels. That could be level. There is technical architecture, there is information architecture, data architecture. In all these cases, people say, okay, you do all this, you put a business function, put a business service. How do you organize it? How do you arrive at it? How does it stick with the before layer? No idea. We just put it in. So there is a very clean way of doing it. You say, okay, at every level you follow the same process. You want to do enterprise architecture, you follow this process. Then you want to do business architecture, you are trying to architect, we understand what is the business problem, analyze the business problem, synthesize a business solution, analyze the business solution, so formulate a business architecture, evaluate the business architecture, create a business architecture description. Now there is going to be correlation between the layers. Establish the correlation. There is traceability. Extend it, and then you have it for the entire enterprise. At any level, you just follow the same process. And that is why this is the best practice. And there are more than 120,000 adoptions of this idea the last 2 years. It is a widely used standard. It has been adopted by anybody who talks about architecture, anybody who talks about reference model, refer this particular standard. But now you see the problem. I'm only talked about as an architect, what is the methodology, how do you architect, etc. How do you take quality to value, etc. And now we have to look at, from the programming point of view, what is the difference we can bring into the field. The difference we can bring into the field is globally more than 95% of architectures exist only as PowerPoint slides or some static models. Models in Archi or something like that. Very little technology support. Okay, if I have this model, can I generate a system? Doesn't happen. Okay, today when Neil presented a slide, he said this is the architecture. Can I have a system? Okay, because when I say architecture, imagining the feature 2 years, it's going to take 3 years to implement the system. So you see the problem, there is a big gap between what we imagine and the time it takes to implement. Then if you look at what are the other things that is there, architecture is the oldest discipline, more than 5,000 years old. There are technologies for creating architecture models. Okay, we can use model system using SysML, using UML, can use Archi, PowerPoint, etc. But what is the IDE for architects? You have an IDE for programmers. What is the IDE for architects? What is the architecting environment? I mean, the architects is not only about diagramming. You have to understand what is the problem, how do I analyze the problem, so many things are there. So you see the problem. So this is one of the challenges that Professor Nori thought about, and we worked on it for the last 15, 16 years. I leave this as a challenge. It has been addressed to some extent. I don't want to cover it here. So the way ahead are the grand challenges. He felt at some point in time in the future, the situation is going to be such that software is ubiquitous, software is everywhere. Services are everywhere, knowledge is everybody knows everything. Computing is available, ubiquitous, processes are ubiquitous. Best practices, everything are taken for granted. In that situation, what will we do? So he said, what does it mean to enhance the quality of life? How do we enable knowledge workers? Who are the knowledge workers? Teachers. When we were in the pandemic, teachers were teaching online. What is the thing that was at their disposal? Teams, Global Meet. Are these the tools necessary for them to teach? Can we make the teaching job better? And then how do we make the enterprise sustain its being its benchmark? How do we harness knowledge? What is the working environment? Can we have a working environment? Can we conceptualize? Can we implement a working environment for teachers, architects, managers, engineers, anybody? I mean, programming, you need to find new avenues where your programs can utilize. So he said, can we have something like this? Thank you. So this is usually his last slide. So I thought in this occasion I should put this in. Thank you very much.
I thought I'll just make a comment here because you must have worked with Nori sir much more recently, but when I was closer to him in the 90s, he used to say, let me try and recollect, he used to say something to the effect that programmers have logic, programmers have reasoning. It would be good if programmers had more conscience. I don't know if you heard him say this or something like this. The other thing which he said in this regard was, and this is very strange because Nori was so much after doing these tools like things and so on. But he did say excessive focusing on tools without understanding actually spoils programmers' conscience.
Yeah.
So that is relating, I thought, to your last slide of when you have all those ubiquitous become taken for granted, what remains our work? I think Nori's main point was we can still keep our conscience intact.
I agree.
about this enterprise architecture. Actually, there is a lot of work on TOGAF that has happened actually, and we used to use this system architect, and then used to connect to the development architecture, which used to be a 4+1 model. Now, when this ISO was evolved actually, what was the year?
2019.
2019.
See, the problem with TOGAF is it's been frozen in time from 2008. Version 9.2 is the last one.
Yeah, I know.
And after that 10, they are releasing for the last 13 years. Nothing has come out. And the sad part is, if you look at the definition and you ask the question, they speak about business architecture. Say, go and ask the TOGAF trained architect, what is a business function? A software function is called as a business function. A business service is nothing but a software is providing this, so business is also providing the service. I mean, you have to look at it, the separation of layers, such that you understand, put yourself as a business person and look at it as a business problem. They don't do that. It seems to be predominantly teaching a bunch of templates and filling up the template. That's what it turned out to be.
That is made between the overall, because the adoption of the TOGAF 9, when I worked on is a component business model of IBM actually, but that also always is to differentiate appropriately. What is how basically the enterprises should be viewed, and how you can map at each level, how you can map it to the maybe the application that you develop or the overall system you develop connected with each other. So
yeah,
that's actually maybe the adoption of TOGAF 9 is left to you. I mean, it is not it's a more of a framework, right?
Yeah, see, this is all things that you can say this is a framework, you left to you, etc. But what is the underlying process? To adopt something in the industry, there should be a process. Okay, and the process that is there inside TOGAF is architecture development methodology, which is only to create a description. See, we create the specification of the architecture, not to do architecture. When I say architect, I will be evaluating the architecture, I will be describing the architecture, I will be reviewing the architecture, I will be conceptualizing the architecture. There are so many activities that is there. It's not only description. And architects don't know any of these technologies. The technologies are used predominantly by modelers. I mean, the same problem is faced by model-based engineering also. We don't have architects using it. We only have modelers using it, and the modelers don't understand anything. And you need a special translator to tell them what you really want them to put in. So that is a fundamental problem that we want to solve across different industries, different roles. So that was one of the grand challenges that Professor Nori was talking about. And entire 17 years we spent talking about it. We have filed many patents, a lot of publications, everything is there. But still it is one of the grand challenges that is still there for us.
I heard you speak a lot about, mostly about architecture and about models. I don't know if I missed it, but where does ontology fit into this?
I'm not quite sure. Simply because if you look at it, you have to look at it from various perspectives. If you look at it from the systems engineering perspective, then ontology gives a vocabulary for how you are going to model, how you are going to describe the system. But if you look at it from the architect's point of view, they say, I would require the domain ontology because the domain is going to teach me what are the basic things I need to know about the particular domain. Now, since it is not that clearly established, so there is some kind of mess there. And that's where I would leave it. Thank you. Thank you very much.
Thank you, Anand. Thanks a lot. It was a very illuminating talk about what Professor Nori thought about after he left ARDC. So with that, I guess we have come to the end of the program. I invite Vivek Buzruk to give any closing remarks.
See, I know that I have been given slot at the end because I should, otherwise you wouldn't have been able to hear anyone else. But once I started talking, nobody else speaks actually, or I don't allow anyone to speak. That's why I'm at the end. Anyway, thanks a lot. Thanks all. And let me first appreciate. So I am supposed to in fact summarize also as a part of this, but I won't be summarizing that much because all of you must have summarized in your mind. But I may take 1 or 2 minutes for to just take an overview of what we have been actually in a day, what we have done and all. So definitely there has been a interesting talk by Neil in the morning, and then after that we had also had a sort of talking about the overall idea. Sorry. We are always learning, yes, but I wanted to be very. Where should I click it? Ah, yeah. Okay. Okay. So what was, in fact, one of the important thing that I learned from Professor Nori is retrospection. And obviously that, I don't know how many of you have read his white paper on this retrospection of PQCC compiler, but overall this, whenever we talk about the innovation, actually all these things require introspection and retrospection, and that's basically the way we can innovate better. So obviously this has led, today we have been talking about this influence of AI on programming and the programming environments and programming in new era. That was one of the things that we talked about. So that's before I close, actually I will just like to show one slide in fact that I prepared. This in fact is taken because the topic was more on the programming side, and there are a lot of students here. So programming, in fact, whenever this guy actually, I was quite influenced once when I read 2-3 of his articles. And one of the place that he mentioned that overall standard language can be seen as consisting of these major parts: fundamental syntax, semantic state, kernel built-ins, non-kernel intrinsics. I will leave it to you to understand that. I will not get into the description of each of them. But syntactic sugar, global convenience libraries, and the standard convenience libraries. Now, in fact, this is a good way of looking at the overall standard language. And if you imbalance certain things, the other comments that he has given is that if you imbalance certain things, then you may land up in an issue of languages which actually fall apart. I mean, the Lisp is a common Lisp is one of the example that he took actually, that it was not balanced appropriately in a properly been actually maybe you can say enhanced in a regular way or in a proper way. And Java may go in that same direction. That's a fear that he was talking about. Anyway, so in this context, actually, today's thing that in the programming language, whenever we talk about the development environments and the compiler. Compiler is a very, in fact, topic which is near to many of us. And we saw today AI-driven improvisation models that are coming into these development environments, and even in the compiler. That's what one of the important thing that we had gone through. And last topic was a very interesting one that I really, in fact, I was taken back 10 years back when I was in IBM about this system architecture and enterprise architecture, system architecture, and the overall aspects of how basically the enterprises can be modeled and how basically the systems can be developed for each of their business units, or how the integrated systems can be developed. That is a very interesting, and thanks for that beyond programming also topic actually. And thanks everyone here. So first let me thanks first of all Department of Computer Science, Dr. Smita Bedekar, head of the department. Nitin Patil sir, where is he? He's there. Absolutely great work, and it's a really, in fact, because of him and because of Department of Computer Science, we are here. There are lots of, in fact, at one point of time, there were 400 online participants, but people should come here. Before lunch, there were many more people. Now, after lunch, I think there are few people, but we will learn on these things, no doubt. Second thing is obviously after this Department of Computer Science, TCS Research, Ravindra Mehta, Ravindra R.D. Naik, Venki, is they not there? Okay, Venki, Vijay, all these people are really supportive, and we should definitely give a big applause for them, and definitely it's a great, thanks a lot. Really, I mean, because of their support, we are also here. So first is that Department of Computer Science and the TCS Research, and obviously ACM in India, who helped us and really, I mean, helped us giving this opportunity. Let me thank Umesh, who is always supporting and be with us. Nitin Patil again, Vijay is there, then Dr. Gitanjali Kade was there in the morning. She's always busy with her own department, but whenever she finds time, she supports us. And obviously, Shekhar Sahasrabuddhe sir, who is indirectly supporting us, and other people are also there, and Arun is not there right now. But some of these people are the really those who thought that all professionals, in fact, industry and academics, both of them should in fact come together. They should exchange ideas. There can be definitely some things will be learned even by industry people from the academics. Academics will learn from the industry, but there has to be exchange of views. And that's basically local neighborhood can work in a better way. Thanks everyone, to the speakers. Thanks to all of them. Professor HVS is not there. Saurav Bansal has left, I think. And then Khedkar, Dr. Uday Khedkar. Then Suhas, Vinay, Vivek Kulkarni, and Dr. Uday Khedkar, who is not, oh, he's there. Okay, sorry. I thought that you are very sorry. So all the speakers also, and obviously Dr. Smita Bedekar, who was also there. So thanks to all of them and obviously last thanks to all of you who are here still, and great, appreciate. Thank you. Vivek, thank you. Thanks a lot.
And the biggest thanks goes to him, because without him, none of this would have happened. He was the force behind arranging the meetings and ensuring that everything falls in place, the program, the logistics and everything. So thank you so very much.
Thanks a lot. Thanks a lot to everyone. So thanks that we are done. I think.
So now we formally announce the closure. There is a high tea also.
I think I should have said also that he is the program chair of this particular event, and because of him, coordination within TCS Research has happened. Really thanks for that. Hello, please have tea and coffee, and then you can. Okay, thanks.